Hey, David here. Welcome to another philosophy of science stream. So, got a lot of research to share today. Um, Hopefully, a few people find this interesting, and it's mostly me reading from the encyclopedia. Try to explain people how we can review my content. Somewhat due diligence because I'm really trying to get these ideas right. I'm trying to formulate my multiple truth hypothesis. Daniel Friedman from Active Inference reached out to me to see if I wanted to present my multiple truth hypothesis. Thanks to Dave Douglas, who's been on my show. We can review a few times for the encouragement. But it's really complicated. There's so much to it. There's so much to get right. There's so many great names and great theorists who have various ideas, and all of these ideas are endless. Like in Torah study, when you finish a Masechta, Hadron Alach, return to you and study it deeper and understand it better. So all of these ideas just open up more and more doors of more and more research. But I feel I'm rounding the corner today on a reasonably solid foundation of the philosophy of science. And I've mentioned many times the philosophy of science is not well understood. Um, that there's only a few departments in the whole world that even have such a thing as the philosophy of science, and the philosophy of science is uh, many times disputed. Like people don't even realize it's true. Things like metaphysics. Hey, Tom, God bless. Thanks for tuning in. Things like metaphysics, like spoke with Kevin McCarran, and like thank God he was actually a little bit interested in metaphysics. But what actually is science? What do we know? What do we know to be true? What does science tell us? And then these complications that like there almost everything in science is disputed. So it's mostly just due diligence of trying to get these things right. And part of my method of learning memorization techniques, various things, is to just read the encyclopedia. I make notes. I did a whole bunch of things like to try to take notes on these issues and write them down and read multiple books. Like I've read hundreds of books on the subject in the last year or two, and I keep on getting more and more books. I'm organizing my dad's library, and but I think I'm turning the corner. This is episode 7, so I'm going to do a few more ideas today. We're going to do a deep dive into what exactly is uh, a scientific theory, and the basic history. And I've covered you have the paradigm of Galileo, Descartes, Newton. Galileo um, coming up with the concept of trying to describe natural laws in mathematical formula, and then Descartes through the creation of Cartesian algebra, unifying somewhat algebra and geometry, and the separation of dualism to theories of the soul versus um, uh, how the material realm operates, to Newton, who actually correctly first described universal material laws that were predictive with exact mathematical formulations, and creating the calculus to have connection between mass, velocity, acceleration, and that later became useful through the unification under the conservation of energy, and more stuff in the history of science. But what appeared to be that there were going to be these universal laws that could be described with um, mathematical formulas turned out to be false. Like really, physics is the only thing that has correctly been able to uh, do that, and even it's disputed whether even physics has these universal laws that describe material nature. So what you end up with is models and theories. And we talked like in an earlier stream, I think like volume 2, about scientific modeling. And you had different theories like the synthetic, the analytical, and the pragmatic. Like, what is a scientific theory? What's included in it? Can you reduce a scientific theory to universal laws in mathematical language, or like a pure symbolic logical format? And even that, like in physics, is largely impossible. Even Newtonian's laws, uh, to question whether you could actually create a pure symbolic language for Newton's laws of motion is unclear, let alone the majority of theories that are in the realm of biology these days, where most theories now come out in biology. So you have theories that include various elements, that include mechanisms, mathematic formulas, statements, definitions altogether. And most people follow what would be called the pragmatic view of science, where we just kind of do what works. We don't have a consistent metaphysics that explains everything. And so all we have really is the best we can do pragmatically. And so most scientists are pragmatic. And I also went into a lot of detail, the history of the creation of science, the philosophical foundations of the Western tradition, from Descartes to modern times, and the importance of the Vienna Circle. So philosophy of science is created in Vienna with Ernst Mach, who heads the first natural Wissenschaften, or whatever they used to call science in Germany. And that becomes the first department of the philosophy of science. Boltzmann also, and we'll talk about Boltzmann today, who was part of the unification of science under the conservation of energy laws. But this first chair of the philosophy of science in Vienna, that eventually of Mort Schleck, who God forbids assassinated, and then World War II, the diaspora of the founders of the Vienna Circle to America, and you have like Wittgenstein, and the attempt to define all these things in logical mathematic, and Hilbert and Bertrand Russell, some of the big names in the foundation of logical empiricism, realism, scientific realism, in these various things, where the hope was to create a language, a universal language of science for truth discovery, and it largely failed. So, we're going to talk a lot today about Rudolf Carnap, Ernst Nagel, some of the big disciples of the Vienna Circle that brought the teachings from Vienna to America. And Carnap is famous for trying to do away with metaphysics. They thought science had reached such a level that you no longer needed metaphysics. And that program largely failed. And it was also like the concept of the unification of science. And even the hope just to unify physics is largely a failed venture. Just unifying the laws of physics itself, let alone to unify all of the laws of physics, where the majority of the new discoveries in science these days occurs in biology. But the structure of how do we define scientific theories and scientific models, a lot of it comes from Carnap, who was the editor of the Journal of the Unity in Science, and unofficial head of the Vienna Circle's diaspora in America, and Ernst Nagel also, some of the big names that tried their best, and the logicians like Hilbert and Bertrand Russell, Frege, some of the stuff we've talked quite a bit about on Week in Review, who did a lot of work in various fields. Hilbert and his program to unify various fields, in hope, even claiming that Hilbert didn't even want put forward even an attempt to unify everything together. He had his 23 goals, and a lot of those were within specific fields, and almost the majority of those themselves failed, let alone a complete unification. But where does that leave us? Considering all of these unifications, clear definitions have failed, science goes on, people still practice science in a pragmatic way. You still have some theories that are better than others, some methods that are better than others. You have schools that people fall into, paradigms of research, technology, engineering. So today I want to go in depth into different things. First, I'm going to talk about models of science. Then I'm going to talk about realism and theory change. I'm going to look at theoretical terms and these what's called Ceteris Paribus laws, like laws of nature that are, so to say, all things being equal, meaning most laws of science are not universal. They have exceptions. Besides for some laws of physics, and even most laws of physics have issues that they're not universal, and therefore you you like say all things being equal, or even though they have exceptions, we call them a scientific theory or scientific, even though they have exceptions. And we'll talk about mechanisms and theoretical terms and all these elements that make up a scientific theory. And we're going to get a little bit in depth into some like logical notation, because they're like, well, what truly is scientific theory or scientific model is something that could be reduced purely to symbolic form, mathematical, logical language. So you can't completely reduce it to like Newtonian's laws and just like an algebraic or calculus statement. Most of them are bigger than just a statement of like Maxwell's equations or something like that, where you might have a single element that could have an equation, but to have a whole model that includes multiple laws is really going to have some logical symbolic format and statistical methods and these various things. And this is, I say, like the final precursor to the complete formalization of the multiple truth hypothesis. And people are following the multiple truth hypothesis like a metaphysical framework in its proper form. It would have a symbolic logical notation, which I've mentioned in the past, of various approaches to a symbolic logical form. But then taking things like Gödel's incompleteness theorem and problems within mathematics and logic that you're not going to be able to really make a definition. And you'll see why have all these attempts failed. But what are the various schools? So, it's kind of like Talmudic and Pilpul. So, so what, where do we holding? What do people? So, there's these schools, there's these theorists. There's so basically there's a whole bunch of schools, there's a whole bunch of models, there's a whole bunch of approaches, and reality is scientists use all of them or a lot of them. They might fall into a certain school, like a field of research or an approach, but pragmatism is the overarching approach of science where people just do what is practical. And that means that they might be within the larger paradigm of one school, but if that doesn't work for what they're trying to do, they'll use the best practices from all the schools, even though from a philosophical level, there's logical contradictions. And so, what does that mean for the truth value? And we've discussed that in the past with like scientific realism. Is science truth? What do scientific theories actually describe? Are they actually describing universal laws or truth? So it's going to be a lot of reading, a lot of in-depth. Like, hopefully people find this useful. Like I listen to content like this. Basically in my stream, I get into debates. I follow content creators, but generally that's not the content I consume. The content I consume regularly is educational. So almost all the time, like this is the type content that I would consume that I'm creating. And so hopefully people out there that find this interesting. And I went through a lot of effort. I'm going to continue going through a lot of effort. See, publicly do my due diligence for what hopefully I'll start publishing on the multiple truth hypothesis. But it's basically going to be me reading articles from the Stanford Encyclopedia. But this is pretty in depth. So if people want to learn the most in depth knowledge, up to date overview of these theories, it's definitely like a degree above Wikipedia. And beyond this, really, it's just the source material. We can review. I will read some of the source material directly, but just want to get the overview of the large, broader view of all of the main theories and big names in the field. Like for the due diligence. So if I have the strength, it'll probably be like 5 or 6 hours, and because there's so much material, it's probably be like 6 hours of me just reading this stuff because there's so much to cover. And so if you're watching this, you could come back in different times, or later I'll the timestamp, or I'll try to check the chat a little bit, but I basically just want to stick on topic of this. If you want to talk about different things, you could reach out and on social media, like join my Discord or tweet at me, message me, and we could discuss things at a different time, because I want to keep this purely to topic. So last time when I continued the series, I did reductionism, and science, and I covered a review of the first 5 parts in some of the weekend reviews, and it was rather lengthy. Then we looked at indispensability arguments in the philosophy of mathematics, just the role, is mathematics indispensable to scientific theories? And if mathematics is indispensable to scientific theories, what does that mean about mathematics? And I think that was the Putnam-Duhem hypothesis. Then we looked at reductionism, and also reductionism in biology, and the concept of are there some things more basic than other things? Can one thing be derived from the other? And today we'll look a little bit at causation, but causation is actually more a field of metaphysics. So when we're through with this, I'm going to start a series on metaphysics, and we'll see why metaphysics is so important. So things that we take for granted, like causation, is really a metaphysical precursor to science, that we accept that there is such a thing as causation, but how do we understand causation? And we look at measurement. What does it mean to measure? All the different schools or thoughts on measurement and the implications of measurement, and the philosophy of neuroscience. So that's very important also. My main field of research is the philosophy of consciousness, science of consciousness, and also the science of expertise, which I've covered somewhat in the last few weeks. So let's jump right in. And so I'm going to start with models of science, then we're going to look at realism and theory change, then theoretical terms, Ceteris, Paribus laws, and mechanisms in science. And like all of these are long, and hopefully I'll be able to get through all of them. It'll probably be like 5-6 hours. So I've tried to standardize my color coding and my highlighting. So reds are usually for titles, and if something I've highlighted in red within besides the title, that means it's another entry that I've read at a different time, or one of the, like a broader subject overview. And so it's highlighted in red. It's either the the section title, or it's an element within that I'm reading that is a whole nother entry that I've read at a different period. Yellow are usually examples. Green and purple are terms, and orange are names, dates, and titles of like books. So purple are usually more substantiated terms, more important terms, and green like secondary terms. So red, titles, sections, yellow, examples, orange, names, dates, and titles of publications. Purple and green are important terms, purple being more important terms than the green terms generally. Okay, so God bless anyone tuned in. Appreciate you being here. Hope you gained from it. And feel free to be active in the chat. I'm just going to jump right into it. Models in science. Models are essential. Oh, and also the generally I'm reading everything besides for very technical details or examples that so most of the examples I'm not reading. So so if it's not highlighted, it usually means it's an example, or it's more technical that's too difficult to read through. And to some extent, the technical stuff that I'm not highlighting in the future, that's the majority stuff that I'm going to be dealing with, because that's going to be the more technical notation, logical notation, more in detail. So want to get the more narrative, broader concepts out there, and in the future, like slides or whatever, it's going to be more God forbid, just straight logical symbolism. Models in science. Models are of central importance in many specific contexts. The centrality of models such as inflationary models in cosmology, general circulation models of the global climate, the double helix model of DNA, evolutionary models in biology, agent-based models in the social sciences, and general equilibrium models of markets in their respective domains is a case in point. Scientists spend significant amounts of time building, testing, comparing, and revising models. As much journal space is dedicated to interpreting and discussing the implications of models. As a result, models have attracted philosophers' attention, and there are now sizable bodies of literature about various aspects of scientific modeling. A tangible result of philosophical engagement with models is a proliferation of model types recognized in the philosophical literature. Probing models, phenomenological models, computational models, developmental models, explanatory models, impoverished models, testing models, idealized models, theoretical models, scale models, heuristic models, character models, exploratory models, didactic models, fantasy models, minimal models, toy models, imaginary models, mathematical models, mechanistic models, substitute models, iconic models, formal models, analog models, and instrumental models are but some of the notions that are used to categorize models. While at first glance this abundance is overwhelming, it can be brought under control by recognizing that these notions pertain to different problems that arise in connection with models. Models raise questions in semantics. How, if at all, do models represent? Ontology, what kind of things are models? Epistemology, how do we learn and explain with models? And of course, in other domains with philosophy of science. Semantics, models and representations. Many scientific models are representational models. They represent a selected part or aspect of the world, which is the model's target system. Standard examples are the billiard ball model of gas, the Bohr model of the atom, the Lotka-Volterra model of predator-prey interaction, the Mundell-Fleming model of an open economy, and the scale model of a bridge. This raises questions what it means for a model to represent a target system. This problem is rather involved and decomposes into various subproblems. At this point, rather than addressing the issue of what it means for a model to represent, we focus on a number of different kinds of representation that play important roles in the practice of model-based science, namely scale models, analogical models, idealized models, toy models, minimal models, phenomenological models, exploratory models, and models of data. These categories are not mutually exclusive, and a given model can fall into several categories at once. Scale models. Scale models are downsized or enlarged copies of their target system. A typical example is a small wooden car that is put into a wind tunnel to explore the actual car's aerodynamic properties. The intuition is that a scale model is a naturalistic replica or a truthful mirror image of the target. For this reason, scale models are sometimes also referred to as true models. However, there is no such thing as a perfectly faithful scale model. Faithfulness is always restricted to some respects. And even in the respect in which a model is faithful, representation or relation between model properties and target properties is usually not straightforward. The two quantities stand in a complicated nonlinear relation with each other, and the exact form of the relation is often highly non-trivial and emerges as the result of a thoroughgoing study of the situation. Analogical models. Standard examples of analogical models include the billiard ball model of a gas, the hydraulic model of an economic system, and the dumb hole model of the black hole. At the most basic level, two things are analogous if they are certain relevant similarities between them. In the classic text, Hess 1963 distinguishes different types of analogies according to the kind of similarity relations into which two objects enter. A simple type of analogy is one that is based on shared properties, but sameness of properties is not a necessary condition. An analogy between two objects can also be based on relevant similarities between their properties. In this more liberal sense, we can say that there's an analogy between sound and light because echoes are similar to reflections, loudness to brightness, pitch to color, detectability by the ear to detectability by the eye, and so on. Analogies can be based on the sameness or resemblance of relations between two parts of two systems rather than on their monadic properties. It is in this sense that the relation of a father to his children is asserted to be analogous to the relation of the state to its citizens. The analogies mentioned so far have been what Hess calls material analogies. We obtain a more formal notion of analogy when we abstract from concrete features of the system and only focus on their formal setup. When the analog model then shares with its target is not a set of features, but the same pattern of abstract relations, the same structure where the structure is understood in a formal sense, this notion of analogy is closely related to what Hess calls a formal analogy. The two items are related by formal analogy if they are both interpretations of the same formal calculus. For instance, there's a formal analogy between a swinging pendulum and an oscillating electric circuit because they're both described by the same mathematical equation. A further important distinction due to Hess is the one between positive, negative, and neutral analogies. The positive analogy is between two items consists of the properties or relations they share. Both gas molecules and billiard balls have mass. The negative analogy consists in properties they do not share. Billiard balls are colored, gas molecules are not. The neutral analogy comprises the properties which are not known yet, whether they belong to the positive or negative analogy. Do billiard balls and molecules have the same cross-section in scattering processes? Neutral analogies play an important role in scientific research because they give rise to questions and suggest new hypotheses. For this reason, several authors have emphasized the heuristic role that analogies play in theory and model construction, as well as in creative thought. It has also been discussed whether using analogical models can, in some cases, be a confirmatory in a Bayesian sense. Hess argues that it's possible if the analogy is a material analogy. Bartha disagrees and argues that analogical models cannot be confirmatory in a Bayesian sense because the information encapsulated in an analogical model is part of the relevant background knowledge, which has the consequence that the posterior probability of a hypothesis about a target system cannot change as a result of observing the analogy. Analogical models can therefore only establish a plausibility of a conclusion in the sense of justifying a non-negligible prior probability assignment. More recently, these questions have been discussed in the context of so-called analog experiments, which promise to provide knowledge about an experimentally inaccessible target system by manipulating another system, the source system. Dardashti argued that given certain conditions, an analog simulation of one system by another system can convert claims about the target system. Idealized models. Idealized models are models that involve a deliberate simplification or distortion of something complicated with the objective of making it more tractable or understandable. Frictionless planes, point masses, completed isolated systems, omniscient and fully rational agents, and markets in perfect equilibrium are well-known examples. Idealizations are a crucial means for science to cope with systems that are too difficult to study in their full complexity. Philosophical debates over idealization have focused on two general kinds of idealizations, the so-called Aristotelian and Galilean idealizations. Aristotelian idealizations amount to stripping away in our imagination all properties from a concrete object that we believe are not relevant to the problem at hand. There is a disagreement about how this is done. Jones, 2005, and Godfrey Smith in 2009 offer an analysis on abstraction in terms. While an abstraction remains silent about certain features or respects of the system, it does not say anything false and still offers a true, albeit restricted description. This allows scientists to focus on a limited set of properties in isolation. An example is the classical mechanics model of the planetary system, which describes the position of an object as a function of time and disregards all other properties of planets. Cartwright and Musgrave, who use the term negligibility assumptions, and Mackey, who speaks of the method of isolation, allow abstractions to say something false, for instance, by neglecting a causally relevant factor. Galilean idealizations are the ones that involve deliberate distortions. Physicists build models consisting of point masses moving on frictionless planes. Economists assume that agents are omniscient. Biologists study isolated populations, and so on. Using simplifications of this sort, whenever a situation is too difficult to tackle, was characteristic of Galileo's approach to science. For this reason, it is common to refer to distortive idealization of this kind as Galilean idealizations. Galilean idealizations are sometimes characterized as controlled idealizations, as ones that allow for de-idealization by successive removal of the distorting assumptions. Thus, construed Galilean idealizations don't cover all the distortive idealizations. Batterman discussed distortive idealizations that are eliminable in that they cannot be removed from the model without dismantling the model altogether. What does a model involving distortions tell us about reality? Lehmann formulated a theory which understands idealizations as ideal limits. Imagine a series of refinements of the actual situation which approach the postulated limit, and then require that the closer the properties of a system come to the ideal limit, the closer its behaviors has to come to the behavior of the system at that limit. Monotonicity. If this is the case, then scientists can study the system at the limit and carry over conclusions from the system to systems distant from the limit. But these conditions need not always hold. In fact, it can happen that the limiting system does not approach the system at the limit. If this happens, we are faced with a singular limit. In such cases, the system at the limit can exhibit behavior that is different from the behavior of systems distant from the limit. Limits of this kind appear in the number of contexts, most notably in the theory of phase transitions and statistical mechanics. There is however no agreement over the correct interpretation of such limits. Betterman sees this as indicative of an emergent phenomenon, while Butterfield sees them as compatible with reduction. Galilean and Aristotelian idealizations are not mutually exclusive, and many models exhibit both in that they take into account a narrow set of properties and distort them. Consider again the classical mechanics model of the planetary system. The model only takes a narrow set of properties into account and distorts them, for instance, by describing planets as ideal spheres with a rotational symmetric mass distribution. A concept that is closely related to idealization is approximation. In a broad sense, A can be called an approximation of B if A is somewhat close to B. This, however, is too broad because it makes room for any likeness to qualify as an approximation. Ruger and Sharp, 1998, limit approximations to quantitative closeness, and Portides, 2007, frames it as an essentially mathematical concept on the notion A is an approximation of B if and only if A is close to B in a specific mathematical sense, where the relevant sense of close will be given by the context. An example of the approximation of one curve with another one, which can be achieved by expanding a function into power series and only keeping the first two or three terms. In different situations, we approximate an equation with another one by letting a control parameter tend towards zero. This raises the question of how approximations are different from idealizations, which can also involve mathematical closeness. Norton sees a distinction between the two as referential and approximation in an inexact description of the target, while the idealization introduces the secondary system, real or fictitious, which stands for the target system while being distinct from it. Separating idealizations and approximations in this way does not imply that there cannot be interesting relations between the two. For instance, an approximation can be justified by pointing out that it's the mathematical expression of an acceptable idealization when we neglect a dissipative term in the equation of motion because we make the idealization assumption that the system is frictionless. Toy models. Toy models are extremely simplified and strongly distorted renderings of their targets and often only represent a small target of causal or explanatory factors. Typical examples are the Lotka-Volterra model in population ecology and the Schelling model of segregation in the social scientists. Toy models usually do not perform well in terms of prediction and empirical adequacy, and they seem to serve other epistemic goals. This raises the question whether they should be regarded as representational at all. Some toy models are characterized as caricatures. Caricature models isolate a small number of salient characteristics of a system and distort them into an extreme case. However, it is controversial whether such highly idealized models can still be regarded as informative representations of their target systems. Minimal models. Minimal models are closely related to the toy models in that they are highly simplified. They are so simplified that some argue that they are non-representational. They lack any similarity, isomorphism, or resemblance relations to the world. It has been argued that many economic models are of this kind. Minimal economic models are also unconstrained by natural laws and do not isolate any real factors. And yet, minimal models help us to learn something about the world in the sense that they function as surrogates for a real system. Scientists can study the model to learn something about the target. It is, however, controversial whether minimal models can assist scientists in learning something about the world if they do not represent anything. Minimal models that purportedly lack any similarity or representation are also used in different parts of physics to explain the macro state behavior of various systems whose micro scale behavior is extremely diverse. Proponents of minimal models argue that what provides an explanation of the macro scale behavior of a system in these cases is not a feature of that system and model have in common, but the fact that the system and the model belong to the same universality class, a class of models that exhibit the same limiting behavior, even though they show very different behavior in finite scales. It is, however, controversial whether explanations of this kind are possible without reference to at least some common features. Phenomenological models. Phenomenological models have been defined in different, although related ways. A common definition takes them to be models that only represent observable properties of their targets and refrain from postulating hidden mechanisms and the like. Another approach due to McMullen, 1968, defines phenomenological models as models that are independent of theories. This, however, seems to be too strong. Many phenomenological models, while failing to be derivable from a theory, incorporate principles and laws associated with theories. Finally, it is tempting to identify phenomenological models with models of a phenomenon. Here, phenomenon is an umbrella term covering all relatively stable and general features of the world that are interesting from a scientific point of view. The weakening of a sound as a function of the distance to the source, the decay of alpha particles, the chemical relations that take place when a piece of limestone dissolves in an acid, the growth of a population of rabbits, and the dependence of house prices on the base rate of the Federal Reserve are phenomena in this sense. Exploratory models. Exploratory models are models which are not proposed in the first place to learn something about a specific target system or a particular experimentally established phenomenon. Exploratory models function as the starting point for further explorations in which the model is modified and refined. Gelfert 2016 points out that exploratory models can provide proofs of principle and suggest how possibly explanations. Such models do not give an accurate account of the behavior, but they provide the starting point for the development of more realistic models. Massimi 2019 notes that exploratory models provide modal knowledge. Fisher 2006 sees these models as tools for the examination of the features of a given theory. Models of data. A model of data, sometimes also data model, is a corrected, rectified, regimented, and in many instances idealized version of the data we gain from immediate observation, the so-called raw data. Characteristically, one first eliminates errors, removes points from the record that are due to faulty observation, and then presents data in a neat way, for instance, by drawing a smooth curve through a set of points. These two steps are commonly referred to as data reduction and curve fitting. Models of data play a crucial role in confirming theories because it is the model of data and not the often messy and complex raw data that theories are tested against. The construction of a model of data can be extremely complicated. It requires sophisticated statistical techniques and raises serious methodological as well as philosophical questions. How do we decide which points on the record need to be removed? And given a clean set of data, what curve do we fit to it? The first question has been dealt with mainly within the context of the philosophy of experiment. At the heart of the latter question lies the so-called curve fitting problem, which is that the data themselves dictate neither the form or of the fitted curve nor what statistical technique scientists should use to construct a curve. The choice and rationalization of statistical techniques is the subject matter of the philosophy of statistics. The gathering, processing, dissemination, analysis, interpretation, and storage of data raise many important questions beyond the relatively narrow issue pointing to models of data. Leonelli investigates the status of data in science, argues that data should be defined not by their provenance, but by their evidential function, and studies how data travel between different contexts. So we see your questions of physics to chemistry and biology to other fields such as economics and economics and other fields where you could use models, but question, are they scientific? Whether predictive, you have an explanatory model. So you notice that different models are more useful for different fields. And you can even have things like historical models, spiritual models, so on and so on. And you see where this is going with the multiple truth hypothesis. So you continue with the due diligence. Ontology, what are models? What are models? That is, what kind of object are scientists dealing with when they work with a model? A number of authors have voiced skepticism that this question has a meaningful answer because models do not belong to a distinctive ontological category and anything can be a model. Contessa 2010 replies that this is a non sequitur. Even if from an ontological point of view, anything can be a model in the class of things that are referred to as models contain a heterogeneous collection of different things, it does not follow that it is either impossible or pointless to develop an ontology of models. This is because even if not all models are of a particular ontological kind, one can nevertheless ask to what ontological kinds the things that are de facto used as models belong. There may be several such kinds, and each kind can be analyzed in its own right. What sort of objects scientists use as models has important repercussions for how models perform relevant functions such as representation and explanation, and hence this issue cannot be dismissed just as sociology. The objects that commonly serve as models indeed belong to different ontological kinds: physical objects, fictional objects, abstract objects, set theoretical structures, descriptions, equations, or combinations of some of these things are frequently referred to as models, and some models may fall into yet other classes of things. Following Contenza's advice, the aim then is to develop an ontology for each of these. Those with an interest in ontology may see this as a goal in its own right. It pays nothing, however, that the question has reverberations beyond ontology and bears on how one understands the semantics and the epistemology of models. Physical objects. Some models are physical objects. Some models are commonly referred to as material models. Material objects that serve as models. Material models do not give rise to ontological difficulties over and above the well-known problems in connection with objects that metaphysicians deal with, for instance, concerning the nature of properties, the identity of objects, parts and wholes, and so on. However, many models are not material models. The Bohr model of the atom, the fictionless pendulum, and an isolated population, for instance, are in the scientist's mind rather than in the laboratory, and they do not have to be physically realized and experimented on to serve as models. These non-physical models raise serious ontological questions, and how they are best analyzed is debated controversially. In the remainder of this section, we review some of the suggestions that have attracted attention in the recent literature on models. Fictional objects and abstract objects. What has become known as the fiction view of models sees models as akin to the imagined objects of literary fiction. This view squares well with scientific practice, where scientists often talk about models as if they were objects and often take themselves to be describing imaginary atoms, populations, or economies. It also squares well with philosophical views that see the construction and manipulation of models as essential aspects of scientific investigation, even if models are not material objects, because these practices seem to be directed towards some kind of object. What philosophical questions does this move solve? Fictional discourse and fictional entities face well-known philosophical questions, and one may well argue that simply likening models to fictions amounts to explaining obscurum per obscurius. One way to counter this objection and to motivate the fiction view of models is to point to the view's heuristic power. In this vein, Frigg 2010 identifies 5 specific issues that an ontology of models has to address, and then notes that these issues arise in a very similar way to the discussion about fiction. The issues are the identity conditions, property attribution, the semantics of comparative statements, truth conditions, and the epistemology of imagined objects. Likening models to fiction then has heuristic value because there is a rich literature on fiction that offers a number of solutions to these issues. Only a small portion of the options available in the extensive literature on fiction have actually been explored in the context of scientific models. Contenza 2010 formulates what he calls the dualistic account, according to which a model is an abstract object that stands for a possible concrete object. The Rutherford model of the atom, for instance, is an abstract object that acts as a stand-in for one of the possible systems that contains an electron orbiting around a nucleus in a well-defined orbit. Barbaros and Ludwig, 2009, and Frigg take a different route to develop an account of models as fictions based on Walton's 1990 pretense theory of fiction. According to this view, the sentences of a passage of text introduce a model should be seen as a prop in a game of make-believe, and the model is the product of the act of pretense. This is an anti-realist position in that it takes talk of model objects to be figures of speech because ultimately there are no model objects. Models only live in a scientist's imagination. Ceteris reformulates this view to become what she calls the new fiction view of models. The core difference lies in the fact that what is considered as the model are the model's descriptions and their content rather than the imaginings that they prescribe. This is a realist view of models because descriptions exist. Hey, Judas, God bless. Shalom. The fiction view is not without critics. Gary, Magnini, Pincock, Portides, and Teller reject the fiction approach and argue in different ways that models should not be regarded as fictions. Weisberg, 2013, argues for a middle position which sees fiction as playing a heuristic role but denies that they should be regarded as forming part of a scientific model. The common core of all these criticisms is that the fiction view misconstrues the epistemic standing of models to call something a fiction. So do charge goes is tantamount to saying that it is false, and it is unjustified to call an entire model a fiction, and thereby claim that it fails to capture how this world is just because the model involves certain false assumptions or fictional elements. In other words, a representation isn't automatically counted as fiction just because it has some inaccuracies. Proponents of the fiction view agree with this point, but deny that the notion of fiction should be analyzed in terms of falsity. What makes a work of fiction is not its falsity or some ratio of false to true claims. Neither is everything that is said in a novel untrue, nor does every text containing false claims qualify as fiction. False news reports are just that, they are not fictions. The defining feature of a fiction is that readers are supposed to imagine the events and characters described, not that they are false. Gary, 1988, advocated a view that non-physical models are abstract entities. However, there's little agreement on the nature of abstract objects, and Hale lists no less than 12 different possible characterizations. In recent publications, Thomason, 2020, and Thomas Jones developed what they call an artifactualist view of models, which is based on Thomason's 1999 theory of abstract artifacts. This view agrees with the pretense theory that the content of text that introduces a fictional character or a model should be understood as occurring in pretense, but at the same time insists that in producing such descriptions, authors create abstract cultural artifacts that then exist independently of either the author or the readers. Artifactualism agrees with Platonism that abstract objects exist, but insists contra Platonism that abstract objects are brought into existence through the creative act and are not eternal. This allows the artifactualist to preserve the advantage of pretense theory, while at the same time holding the realist view that fictional characters and models actually exist. Set theoretic structures. An influential point of view takes models to be set theoretical structures. This position can be traced back to Supp's 1960 and is now with slight variance held by most proponents of the so-called semantic view of theories. There are differences between the versions of the semantic view, but with the exception of Gary 1988, all versions agree that models are structures of one sort or another. This view of models has been criticized on various grounds. One pervasive criticism is that many types of models that play an important role in science are not structures and cannot be accommodated within the structuralist view of models, which can neither account for how these models are constructed nor for how they work in the context of investigation. Examples for such models are the interpretive models and mediating models discussed later. Another charge held against the set theoretical approach is that set theoretical structures by themselves cannot be representational models, at least if that requires them to share some structures with the target, because the ascription of a structure to a target system which forms part of the physical world relies on a substantive non-structural description of the target, which goes beyond what the structuralist approach can afford. Descriptions and equations. Time-honored position has it that a model is a stylized description of a target system. It has been argued that this is what scientists display in papers and textbooks when they present a model. This view has not been subject to explicit criticism. However, some of the criticisms that have been marshaled against the so-called syntactic view of theories equally threaten a linguistic understanding of models. First, a standard criticism of the syntactic view is that by associating a theory with a particular formulation, the view misconstrues theory identity because any change in the formulation results in a new theory. A view that associates models with descriptions would seem to be open to the same criticism. Second, models have different properties than descriptions. The Newtonian model of the solar system consists of orbiting spheres, but it makes no sense to say this is about its description. Conversely, descriptions have properties that models do not have. One way around these difficulties is to associate the model with the content of a description rather than with the description itself for discussion of the position on models that builds on the content of a description. The contemporary version of the description in Levy and Toon's 2012 so-called direct representation view. This view shares with the fiction view of models the reliance on Walton's pretense theory, but uses it in a different way. The main difference is that the views discussed earlier see modeling as introducing vehicle of representation, the model that is distinct from the target, and they see the problem of elucidating what kind of thing the model is. On the direct representation view, there are no models distinct from the target. There are only model descriptions and targets with no models in between them. Modeling on this view consists in providing an imaginative description of real things. A model description prescribes imaginings about a real system. This approach avoids the above problems because the identity conditions for models are given by the conditions for games of make-believe and not by the syntax of a description, and property ascriptions take place in pretense. There are, however, questions about how this account deals with models that have no target and about how models, thus understood, deal with real idealizations. A closely related point approach sees models as equations. This is a version of the view that models are descriptions because equations are syntactic items that describe a mathematical structure. The issue that this view faces are similar to the ones that have already been encountered. First, one can describe the same situation using different kinds of coordinates and as a result obtain different equations, but without thereby also obtaining a different model. Second, the model and the equation have different properties. It is open to question whether these issues can be avoided by appeal to pretense account. Epistemology, the cognitive function of models. One of the main reasons why models play such an important role in science is that they perform a number of cognitive functions. Significant parts of scientific investigation are carried out on models rather than on reality itself, because by studying a model, we can discover features of and certain facts about the system the model stands for. Models allow for surrogative reasoning. The cognitive function of models has been widely acknowledged in the literature, and some even suggest that models give rise to a new style of reasoning, model-based reasoning, according to which inferences are made by means of creating models and manipulating, adapting, and evaluating them. Learning about models. Learning about models happens in two places: in the construction of the model and in its manipulation. There are no fixed rules or recipes for model building, and so the very activity of figuring out what fits together and how affords an opportunity to learn about the model. Once the model is built, we do not learn about its properties by looking at it. We have to use and manipulate the model in order to elicit its secrets. Depending on what kind of model we are dealing with, building and manipulating a model amount to different activities demanding different methodologies. Material models seem to be straightforward because they are used in common experimental contexts. Hence, as far as learning about the model is concerned, material models do not give rise to questions that go beyond questions concerning experimentation more generally. Not so with fictional abstract models. What constraints are there to the construction of fictional abstract models, and how do we manipulate them? A natural response seems to be that if we do this by performing a thought experiment, different authors have explored this line of argument, but they have reached very different and often conflicting conclusions about how thought experiments are performed and what the status of their outcomes is. An important class of models is computational in nature. For some models, it is possible to derive results or solve equations of a mathematical model analytically, but quite often this is not the case. It is at this point that computers have a great impact because they allow us to solve problems that are otherwise intractable. Hence, computational methods provide us with knowledge about the consequences of a model where analytic methods remain silent. Many parts of current research in both the natural and social sciences rely on a computer simulation, which helps scientists to explore the consequences of a model that cannot be investigated otherwise. The formation and development of stars and galaxies, the dynamics of high-energy, heavy ion reactions, the evolution of life, outbreaks of wars, the progression of an economy, moral behavior, and the consequence of decision procedures in an organization are explored with computer simulations, to mention only a few examples. Tinkle, God bless. Computer simulations are also heuristically important. They can suggest new theories, models, and hypotheses, for example, based on a systematic exploration of a model's parameter space. But computer simulations also bear methodological perils. For example, they may provide misleading results because, due to the discrete nature of the calculations carried out on a digital computer, they only allow for the exploration of a part of the full parameter space, and this subspace need not reflect every important feature of the model. The severity of the problem is somewhat mitigated by the increasing power of modern computers, but the availability of more computational power can also have adverse effects. It may encourage scientists to swiftly come up with increasingly complex but conceptually premature models involving poorly understood assumptions or mechanisms and too many additional adjustable parameters. This can lead to an increase in empirical adequacy, which may be welcome for certain forecasting tasks, but not necessarily to a better understanding of the underlying mechanisms. As a result, the use of computer simulations can change the weight we assign to various goals of science. Finally, the availability of computer power may seduce scientists into making calculations that do not have the degree of trustworthiness one would expect them to have. This happens, for instance, when computers are used to propagate probability distributions forward in time, which can turn out to be misleading. So it is important not to be carried away by the means of the new powerful computers offer and lose sight of the actual goals of research. Learning about target systems. Once we have knowledge about the model, this knowledge has to be translated into knowledge about the target system. It is at this point that the representational function of models becomes important again. If a model represents, then it can instruct us about reality because at least some of the model's parts or aspects have corresponding parts or aspects in the world. But if learning is connected to representation and there are different kinds of representations, like analogies, idealizations, then there are also different kinds of learning. If, for instance, we have a model we take to be a realistic depiction, the transfer of knowledge from the model to the target is accomplished in a different manner than when we deal with the analog or model that involves idealizing assumptions. Explaining with models. Some models explain, but how can we fulfill this function given that they typically involve idealization? Do these models explain despite or because of the idealizations they involve? Does an explanatory use of models presuppose that they represent, or can non-representational models also explain? And what kind of explanation do models provide? There's a long tradition requesting that the explanums of a scientific explanation must be true. We find this requirement in the deductive nomological model, as well as in the more recent literature. For instance, Strevens claims that no causal account of explanation allows veridical models to explain. Authors working on the tradition deny that idealizations make a positive contribution to explanation and explore how models can explain despite them being idealized. McMullen argues that a causal explanation based on an idealized model leaves out only features which are irrelevant for the respective explanatory task. Friedman, 1974, argues that a more realistic and hence less idealized model explains better on the unification account. The idea is that idealizations can, at least in principle, be de-idealized. Strevens, 2008, argues that explanatory causal model has to provide an accurate representation of the relevant causal relations or processes which the model shares with the target system. The idealized assumption of a model do not make the difference for the phenomenon under consideration and are therefore explanatorily irrelevant. In contrast, both Potocnik, 2017, and Rice, 2015, argue that models that explain can directly distort many difference-making causes. According to Woodward's 2003 theory, models are tools to find out about the causal relations that hold between certain facts or processes, and it is these relations that do the explanatory work. More specifically, explanations provide information about patterns of counterfactual dependence between the explanums and the explendum, which enable us to see what sort of difference it would have made for the explendum if the factors cited in the explanums had been different in various possible ways. Accounts of causal explanation have also led to various claims about how idealized models can provide explanations, exploring to what extent idealizations can allow for the misrepresentation of irrelevant causal factors by the explanatory model. However, having the causally relevant features in common with real systems continues to play the essential role in showing how idealized models can be explanatory. But is it really the truth of explanums that makes the model explanatory? Other authors pursue a more radical line and argue that false models explain not only despite their falsity, but in fact because of their falsity. Cartwright maintains that the truth doesn't explain much in her so-called simulacrum account of explanation. She suggests that we explain a phenomenon by constructing a model that fits the phenomenon into the basic framework of a grand theory. On this account, the model itself is the explanation we seek. This squares well with basic scientific intuitions, but it leaves us with the question of what notion of explanation is at work, and of what explanatory function idealizations play in model explanations. Wimsatt stresses the role of false models as a means to arrive at true theories. Batterman and Rice, 2014, argue that models explain because the details that characterize specific systems do not matter for the explanation. Bakulich pursues a similar line of reason and sees the explanatory power of models as being closely related to their fictional nature. Bakulich and Kennedy present non-representational accounts of model explanation, and Reese and Woody provide general discussions on the relationship between representations and explanation. Understanding with models. Many authors have pointed out that understanding is one of the central goals of science. In some cases, we want to understand certain phenomenon. In other cases, we want to understand a specific scientific theory that accounts for the phenomenon in question. Sometimes we gain understanding of a phenomenon by understanding the corresponding theory or model. It is, however, controversial whether understanding a phenomenon always presupposes an understanding of the corresponding theory. Although there are many different ways of gaining an understanding, models and the activity of scientific modeling are of particular importance here. This insight can be traced back to at least Lord Kelvin, who, in his famous 1884 Baltimore lectures on molecular dynamics and the wave theory of light, maintained that the test of do we or do we not understand a particular subject in physics is can we make a mechanical model for it? But why do models play such a crucial role in the understanding of a subject matter? Elgin, 2017, argues that this is not despite, but because of models being literally false. She views false models as the felicitous falsehoods that occupy central stage in the epistemology of science and mentions the ideal gas model in statistical mechanics and the Hardy-Weinberg model in genetics as examples for literally false models that are central to the respective disciplines. Understanding it is holistic and it concerns a topic, a discipline, or a subject matter rather than isolated claims or facts. Gaining understanding of a context means to have an epistemic commitment to the comprehensive, systematically linked body of information that is grounded in fact, is duly responsive to reasons or evidence, and enables non-trivial inference, argument, and perhaps action regarding the topic of information pertains to. And models can play a crucial role in the pursuit of these epistemic commitments. Elgin, Lipton, and Rice all argue that models can be used to understand independently of their ability to provide an explanation. Other authors, among them Strevens, argue that understanding presupposes a scientific explanation and that an individual has scientific understanding of a phenomenon just in case they grasp a correct scientific exploration of that phenomenon. On this account, understanding consists in particular form of epistemic access an individual scientist has to an explanation. For Strevens, this aspect is grasping, while for Deregget, it is intelligibility. It is important to note that both Strevens and Deregget hold that the subjective aspects are a worthy topic for investigation in the philosophy of science. This contrasts with the traditional view that delegates them to the realm of psychology. Other cognitive functions. Besides the functions already mentioned, it had been emphasized variously that models perform a number of other cognitive functions. Knutila argues that the epistemic value of models is not limited to their representational function and develops an account that views models as epistemic artifacts which allow us to gather knowledge in diverse ways. Narcissian stresses the role of analog models in concept formation and other cognitive processes. Hartman and Leplin discuss models as tools for theory construction and emphasize their heuristic and pedagogical value. Epstein lists a number of specific functions of models in the social science. Peschard investigates the way in which models may be used to construct other models and generate new target systems. And Isaac discusses new explanatory uses of models which do not rely on their representational capacities. Models and theories. An important question concerns the relationship between models and theories. There is a full spectrum of positions ranging from models being subordinate to theories to models being independent of theories. Models as subsidiaries to theory. To discuss the relationship between models and theories in science, it is helpful to briefly recapitulate the notion of a model and of a theory in logic. A theory is taken to be a usually deductively closed set of sentences in formal language. A model is a structure that makes all sentences in a theory true when its symbols are interpreted as referring to objects, relations, or functions of a structure. The structure is a model of the theory in the sense that it is correctly described by the theory. Logical models are sometimes also referred to as models of theory to indicate that they are interpretations of an abstract formal system. Models in science sometimes carry over from logic in the idea of being the interpretation of an abstract calculus. This is salient in physics, where general laws such as Newton's equation of motion lie at the heart of a theory. These laws are applied to a particular system. The resulting model then is an interpretation or realization of the general law. It is important to keep the notions of a logical and representational model separate. These are distinct concepts. Something can be a logical model without being a representational model, and vice versa. This, however, does not mean that something cannot be a model in both senses at once. In fact, Hess, 1967, points out many models in science are both logical and representational models. There are two main conceptions of scientific theories, the so-called syntactic view of theories and the semantic view of theories. On both conceptions, models play a subsidiary role to theories, albeit in very different ways. The syntactic view of theories retain the logical notions of a model and a theory. It construes a theory as a set of sentences, an axiomatized logical system, and a model is an alternative interpretation of a certain calculus. The model is meant to be something that we are familiar with, and it serves the purpose of making an abstract formal calculus more palpable. A given theory can have different models, and which model we choose depends on our aims and our background knowledge. Proponents of the syntactic view disagree about the importance of models. Carnap and Hempel thought that models only serve a pedagogical or aesthetic purpose and are ultimately dispensable because all relevant information is contained in the theory. Nagel, 1961, and Braithwaite, 1953, on the other hand, emphasize the heuristic role of models, and Schaffner, 1969, submits that theoretical terms get at least part of their meaning from models. The semantic view of theories dispenses with the sentences and axiomatized logical system and construes the theories as a family of models. On this view, a theory literally is a class, cluster, or family of models. Models are the building blocks of which scientific theories are made. Different versions of the semantic view work with different notions of model, but in the semantic view, models are mostly constructed of set theoretic structures. Models is independent from theories. In both the syntactic and the semantic view of theories, models are seen as subordinate to theory and as playing no role outside the context of a theory. This vision of models has been challenged in a number of ways, with authors pointing out that models enjoy various degrees of freedom from theory and function autonomously in many contexts. Independence can take many forms, and large parts of the literature on models are concerned with investigating various forms of independence. Models is completely independent of theories. The most radical departure from a theory-centered analysis of models is the realization that there are models that are completely independent from any theory. If a model is constructed in a domain where no theory is available, then the model is sometimes referred to as a substitute model because the model substitutes a theory. Models is a mean to explore theory. Models can also be used to explore theories. An obvious way in which this can happen is when a model is a logical model of a theory. A logical model is a set of objects and properties that make a formal sentence true, and so one can see in a model how the axioms of the theory play out in a particular setting and what kinds of behaviors they dictate. But not all models that are used to explore theories are logical models, and models can represent features of theories in other ways. Models as complements of theories. A theory may be incompletely specified in the sense that it only imposes certain general constraints but remains silent about the details of a concrete situation. Situations which are provided by a model. Special case of the situation is when a qualitative theory is known and the model introduces quantitative measures. Redhead's example of a theory that is undetermined in this way is axiomatic quantum field theory, which only imposes certain general constraints on quantum fields but does not provide an account of particular fields. Hari, 2004, notes that models can complement theories by providing mechanisms for processes that are left unspecified in the theory, even though they are responsible for bringing about the observed phenomenon. Theories may be too complicated to handle. In such cases, a model can complement a theory by providing a simplified version of the theoretical scenario that allows for a solution. Quantum chromodynamics, for instance, cannot easily be used to investigate the physics of an atomic nucleus, even though it is relevant the relevant fundamental theory. To get around this difficulty, physicists construct tractable phenomenological models which effectively describe the relevant degrees of freedom of the system under consideration. The advantage of these models is that they yield results where theories remain silent. Their drawback is that that is often not clear how to understand the relationship between the model and the theory, as the two are strictly speaking contradictory. Models as preliminary theories. The notion of a model as a substitute for a theory is closely related to the notion of a developmental model. This term was coined by Leplin in 1980, who pointed out how useful models were in the development of early quantum theory, and it is now used as an umbrella notion covering cases in which models are some sort of preliminary exercise to theory. Also closely related is the notion of a probing model or study model. Models of this kind do not perform a representational function and are not expected to instruct us about anything beyond the model itself. The purpose of these models is to test new theoretical tools that are used later on to rebuild representational models. This is not only true for physics, as Wimsatt points out, a false model in genetics can perform many useful functions. Among them, the following: the false model can help answering questions about more realistic models, provide an arena for answering questions about properties of more complex models, factor out phenomena that would not otherwise be seen, serve as a limiting case of a more general model, or two false models may define the extremes of a continuum of cases on which the real case is supposed to lie, or lead to the identification of relevant variables and the estimation of their values. Interpretive models. Cartwright argues that models do not only aid the application of theories that are somewhat incomplete, she claims that models are also involved whenever a theory with an overarching mathematical structure is applied. The main theories in physics, classical mechanics, electrodynamics, quantum mechanics, and so on fall into the category. There's this kind of formulated in terms of abstract concepts that need to be concretized for the theory to provide a description of the target system, and concretizing the relevant concepts, idealized objects and processes are introduced. For instance, when applying classical mechanics, the abstract concept of force has to be replaced with a concrete force such as gravity. To obtain tractable equations, this procedure has to be applied to a simplified scenario, for instance, that of two perfectly spherical or homogeneous planets in an otherwise empty space, rather than to reality in its full complexity. The result is an interpretative model which grounds the application of the mathematical theories to real-world targets. Such models are independent from theory in that the theory does not determine their form, and yet they are necessary for the application of the theory to a concrete problem. Models as mediators. The relationship between models and theories can be complicated and disorderly. The contributions to a programmatic collection of essays edited by Morgan and Morrison in 1999 rally around the idea that models are instruments that mediate between theories and the world. Models are autonomous agents in that they are independent from both theories and their target systems, and it is this independence that allows them to mediate between the two. Theories do not provide us with algorithms for the construction of a model. They are not vending machines into which one can assert a problem and a model pops out. The construction of a model often requires detailed knowledge about materials, approximation schemes, and the setup, and these are not provided by the corresponding theory. Furthermore, the inner workings of a model are often driven by a number of different theories working cooperatively. In contemporary climate modeling, for instance, elements of different theories, including among them fluid dynamics, thermodynamics, electromagnetism, are put to work cooperatively. What delivers the result is not the stringent application of one theory, but the voices of different theories when put to use in chorus with each other in one model. In complex cases like the study of a laser system or global climate, models and theories get so entangled that it becomes unclear where a line between the two should be drawn. Where does the model end and the theory begin? This is not only a problem for philosophical analysis, it also arises in scientific practice. Baylor Jones, 2002, interviewed a group of scientists about their understanding of models and their relationship to theories, and reported widely diverging views. There's no substantive difference between models and theory. Models become theories when their degree of confirmation increases. Models contain simplifications and omissions, while theories are accurate and complete. Theories are more general than models, and modeling is about applying general theories to specific cases. The first suggestion seems to be too radical to do justice to many aspects of practice, where a distinction between models and theories is clearly made. The second view is in line with common parlance, where the term model and theory are sometimes used to express someone's attitude towards a particular hypothesis. The phrase "it's just a model" indicates that the hypothesis at stake is asserted only tentatively or is even known to be false, while something is awkwardly awarded the label theory if it has acquired some degree of general acceptance. However, the use of the term model is different from the uses we have seen and is therefore of no use if we aim to understand the relationship between scientific models and theories. And incidentally, one can equally dismiss speculative claims as just being a theory. The third proposal is correct in associating models with idealizations and simplifications, but it overshoots the restricting by restricting this to models. In fact, also theories can contain idealizations and simplifications. The fourth view seems closely aligned with the interpretive models and the idea that models are mediators, but being more general is a gradual notion, hence does not provide a clear-cut criterion to distinguish between theories and models. A room, God bless. Thanks for tuning in. You tinkle. Psychiatrist is the modern day priest. I mean, maybe to some extent, but different people have different understandings. And as we've talked about previously, in terms of the cognitive revolution, to some extent, neuroscience has displaced psychiatrists anyways. So psychiatrists just describe medicine. People don't really care for theory. They want more, the science, and the science is the neuroscience. But a little bit off topic from this, and we could consider, what's the difference between a psychiatric, a psychological, sociological model, and a neurological model that we discussed last time on the philosophy of neuroscience. Models and other debates in the philosophy of science. The debate over scientific models has important repercussions for other issues in the philosophy of science. Traditionally, the debates over, say, scientific realism, reductionism, the laws of nature were couched in terms of theories, because theories were often seen as the main carriers of scientific knowledge. Once models are acknowledged as occupying an important place in the edifice of science, these issues have to be reconsidered with a focus on models. The question is whether, and if so, how discussion on these issues change when we shift focus from theories to models. Up to now, no comprehensive model-based account of any of these issues has emerged, but models have left important traces in the discussions of these topics. Models, realism, and the laws of nature. Models typically provide a distorted representation of their targets. If one sees science as primarily model-based, this could be taken to suggest an anti-realist interpretation of science. Realists, however, deny that the presence of idealizations in models render a realist approach to science impossible, and point out that a good model, while not literally true, is usually at least approximately true, and or that it can be approved in de-idealization. Apart from the usual worries about the elusiveness of the notion of approximate truth, anti-realists have taken issue with this reply for two related reasons. First, as Cartwright 1989 pointed out, there is no reason to assume that one can always improve a model by adding de-idealizing corrections. Second, it seems that de-idealization is not in accordance with scientific practice, because it is usual that scientists invest work in repeated de-idealizing an existing model, rather they shift to a different modeling framework once the adjustments to be made get too involved. A further difficulty with de-idealization is that most idealizations are not controlled. Further anti-realist argument is the incompatible models argument. Takes as its starting point that observation that scientists often successfully use several incompatible models of one and the same target system for predictive purposes. These models seemingly contradict each other as they ascribe different properties to the same target system. These practices appear to cause a problem for scientific realism. Realists typically hold that there is a close connection between the predictive success of a theory and it being at least approximately true. But if several models of the same system are predictively successful, and if these models are mutually inconsistent, then it is difficult to maintain that they are all approximately true. Realists can react to this argument in various ways. First, they can challenge the claim that the models in question are indeed predictively successful. If the models are not good predictors, then the argument is blocked. Second, they can defend a version of perspectival realism. Proponents of this position, which is sometimes also called perspectivism, situate it somewhat between standard scientific realism and anti-realism, and where exactly the right middle position lies is the subject matter of active debate. Third, realists can deny that there is a problem in the first place because scientific models, which are always idealized and therefore strictly speaking false, are just the wrong vehicle to make a point about realism, which should be discussed in terms of theories. A particular focal point of realism debates are the laws of nature, where the questions arise what laws are and whether they are truthfully reflected in our scientific representations. According to the two currently dominant accounts, the best systems approach and the necessitarian approach, laws of nature are understood to be universal in scope, meaning that they apply to everything that there is in the world. This take on laws does not seem to sit well with the view that places models at the center of the scientific research. What role do general laws play in science if it is models that represent what's happening in the world, and how are models and laws related? One possible response to these questions is to argue that laws of nature govern entities and processes in a model rather than in the world. Fundamental laws in this approach do not state facts about the world, but hold true of entities and processes in the model. This view has been advocated in different variants. Cartwright, 1983, argues that all laws are Ceteris Paribus laws, and Cartwright, 1909, makes use of the capacities which he considers to be prior to laws and introduces the notion of nomological machine. This is a fixed enough arrangement of components or factors with stable enough capacities that in the right sort of stable enough environment will, with repeated operation, give rise to the kind of regular behavior that we represent in our scientific laws. Gary, 1999, argues that the laws of a theory are better thought of not as encoding general truths about the world, but rather as open-ended statements that can be filled in various ways in the process of building more specific scientific models. Models in reductionism. The multiple models problem also raises the question of how different models are related. Evidently, multiple models with the same target system do not generally stand in a deductive relationship, as they often contradict each other. Some have suggested a picture of science according to which there are no systematic relations that hold between different models. Some models are tied together because they represent the same target system, but this does not imply that they enter into any further relationship, deductive or otherwise. We're confronted with a patchwork of models, all of which hold Ceteris Paribus in their specific domains of applicability. Some argue that this picture is at least partially incorrect because there are various interesting relations that hold between different models or theories. These relationships range from thoroughgoing reductive relations and controlled approximations over singular limit relations. These suggestions have been made on the basis of case studies, and it remains to be seen whether a more general account of these relations can be given and whether a deeper justification for them can be provided, for instance, within a Bayesian framework. Models also figure in the debate about reduction and emergence. In physics, here some authors argue that the modern approach to renormalization challenges Nagel's 1961 model of reduction or the broader doctrine of reductions. Dizagi Bahmani provided defense of the Nagel-Schaffner model of reduction, and Butterfield argues that renormalization is consistent with Nagelian reduction. Palacios 2019 shows that the phase transitions are compatible with reductionism, and Hartman argues the effective field theories research program is consistent with reductionism. Rosseller 2015 argues for a local form of reduction, which sees the fundamental relation of reduction holding between models, not theories, which is, however, compatible with the Nagel-Schaffner model of reduction. In the social sciences, agent-based models are increasingly used. These models show how surprisingly complex behavioral patterns at the macro scale can emerge from a small number of simple behavioral rules for the individual agents and their interactions. This raises questions similar to the questions mentioned above about reduction and emergence in physics, but so far one finds only scattered remarks about reduction in the literature. Okay, so there you have a broad overview of models. What's the difference between models and theory, the different types of models, a lot of stuff, a lot of information. And so let's go on to the next one. realism and theory change in science. And Tinkle, like, well, who defines the model? People make models, and models are only as useful as they work, as they have explanatory power. I mean, you might have some sort of aristocracy that says this is the model and claim that it works even though it doesn't, and claim they have a correct theory even though it doesn't. But long term, the model is only as good as it works. Or it defines, like we talked about, as truth value in terms of the correspondence theory of truth, or the coherence theory of truth, or some form of pragmatism. Okay, so this is going to have some historical overview, tie a few things together, and hopefully should be interesting. And at the end, it's going to get into some more technical, logical formulations of things like Ramsey sentences and more complex things. Realism and theory change in science. Scientific theories seem to have an expiry date. If we look at the history of science, a number of theories that once were dominant and widely accepted and are currently taught in the history of science courses. Will this be the fate of current scientific theories? Is there a pattern of radical theory change as science grows? Are theories abandoned and black, or are these patterns of retention in theory change? That is, are some parts of theories more likely to survive than other parts? And what are the implications of all of this for the scientific image of the world? These kinds of questions have played a major role in the scientific realism debate. The challenge to scientific realism is supposed to come directly from the history of science. The history of science, it is claimed, is at odds with scientific realism's epistemic optimism. It is full of theories which were shown to be false and abandoned, despite the empirical successes. Hence, it is claimed realists cannot be warrantedly optimistic about their approximate truth of currently empirically successful theories. If we take the historical evidence seriously, it is claimed current theories too will sooner or later be abandoned and take their place in the future history of science courses. The anti-realist line of argument has become known as the pessimistic induction. Without denying that theories change over time, scientific realism have tried to block this line of argument by showing either that it's fallacious or that there is substantive continuity in theory change which warrants the realist optimism that current science is on the right track. This entry discusses the origin and current state of the historical challenge to realism and the various realist reactions to it. The first part focuses on the first enactment of arguments based on the historical pessimism as these appeared in the so-called bankruptcy of sciences controversy in the end of the 19th century. The second part deals with the historical challenge to scientific realism as this is currently formulated in the various lines of defense of the claim that scientific knowledge grows despite theory change. The history of the historical challenge. The bankruptcy of science debate. The issue of theory change in science was debated in the context of the bankruptcy of science controversy that was raging in Paris in the last decade of the 19th century and the first decade of the 20th. A claim of growing popular reputation among various public intellectuals, spearheaded by Ferdinand Brunetière and Leo Tolstoy, was the scientific theories are ephemeral, and this was supposed to prove that science has, at best, no more than predictive value with no legitimate claim to showing what the world is like, especially in its unobservable aspects. In light of the growing interest in the history of science among scientists and philosophers, it was pointed out that science has had a poor track record. It has gone through many radical theory changes in the past, hence there's no reason to believe that what is currently accepted will not be overturned in the future. In his essay, The Non-Acting, published in French in August 1893, the Russian novelist Leo Tolstoy noted, lastly, does not each year produce its new scientific discoveries, which after astonishing the boobies of the whole world and bringing fame and fortune to the inventors, are eventually admitted to be ridiculous mistakes, even by those who promulgated them. Unless then our century forms an exception, which is a supposition we ought have no right to make, it needs no great boldness to conclude by analogy that among the kinds of knowledge occupying the attention of our learned men and called science, there must necessarily be some which will be regarded by our descendants much as we now regard the rhetoric of the ancients and the scholasticism of the Middle Ages. A few years earlier, in 1889, Ferdinand Brunetière, professor at the École Normale Supérieure and the editor of the prestigious journal Revue des Deux Mondes, noted in his review of Paul Bourget's play The Disciple, we differ from animals in recognizing that humans have to be first. They have value, the notion of nature, the struggle for life, for natural selection, do not show what we have in common. Are these the only laws? Do we know whether perhaps tomorrow they will not join in the depths of oblivion the Cartesian vortices of the quiddities of scholasticism? This history-fed pessimism about science, which seemed to capture the public mood, led to a spirited reaction by the scientific community in an anonymous article that appeared in the Scientific Review, a prestigious semi-popular scientific journal, in August 17th, 1889. The following question was raised in the history of science. The history of science the history of human error? What will theories affirmed today be affirmed in a century or two? The reply was, we will say to savants, philosophers, and physicists, physicians, chemists, astronomers, or geologists, go forward boldly, without looking behind you, without caring for the consequences, reasonable or absurd, that can be drawn from your work. Seek the truth without the worry of its applications. A few years later, in 1895, Brunetière strikes back with an article titled Presse una visite au Vatican, published in the Revue des Deux Mondes, by claiming that science is bankrupt. Science has failed to deliver on its promise to change the face of the world. Even if this is not a total bankruptcy, it is certainly a partial bankruptcy, enough to shake off the credit from science. The eminent scientist Charles Richet, professor of physiology at the College of France, editor of the Scientific Review, and Nobel laureate for medicine in 1913, replied with an article, Le Science a-t-elle fait bankrupt, which appeared in the section of the history of science. In this, he did three things. Firstly, he noted that science can never understand the why of things, especially when it comes to infinitely small and infinitely large. Science attends only to the phenomenon. The intimate nature of things escapes us. Secondly, he stressed that science has not promised anything, let alone the discovery of the essence of things. Thirdly, he added that despite the fact that science has made no promises, it has changed the world, citing various scientific, industrial, and technological successes. Turning Brunetière's argument on its head, Richet formulated what he might be called an optimistic induction based on the then recent history of scientific successes. To those who claim that science has failed in the past, his reply is that history shows that it is unreasonable to claim for any scientific question that we will always fail to answer it. Far from warranting epistemic pessimism, the history of science is a source of cognitive optimism. Richet referred to a few remarkable cases, the most striking which was the case of Jean-Louis Prévost and Jean-Baptiste Dumas, who had written in 1823, the pointlessness of our attempts to isolate the coloring matter of the blood gives us almost the certainty that no one will ever be able to find it. 40 years after their bold statement, Richet explained the colored matter, hemoglobin, has been isolated, analyzed, and studied. Richet's reply to the historical challenge suggested lowering the epistemic bar for science. Science describes the phenomenon and does not go beyond them to their unobservable causes. This attitude was echoed in the reply to the bankruptcy change issued by the eminent chemist and politician of the French Third Republic, Marcellin Berthelot, in his pamphlet Science and Moral in 1897. He was firm in his claim that an alleged bankruptcy of science is an illusion of the non-scientific mind. Like Richet, he also argued that science has not pretended to have penetrated into the essence of things. Under the words essence, the nature of things, we hide the idols of our own imagination. Science, he noted, has its starting point in the study of facts and aims to establish general relations, that is, scientific laws, on their basis. If science does not aim for more, we cannot claim that it is bankrupt. We cannot accuse it of affirmations it did not make or hopes it is not aroused. Berthelot, who objected to atomism, captured a broad positivistic trend in French science at the end of the 19th century. according to which science cannot offer knowledge of anything other than the phenomena. In light of this view, the history-fed pessimism is misguided precisely because there has been substantial continuity at the level of the description of the phenomenon, even if the explanatory theses have come and gone. Duhem on continuity. This kind of aptitude was captured by Pierre Duhem, 1906, distinction between two parts of a scientific theory, the representative part, which classifies a set of experimental laws, and the explanatory part, which takes hold of the reality underlying the phenomenon. Duhem understood the representative part of a theory as comprising the empirical laws and the mathematical formalisms, which is used to represent, systematize, and correlate these laws, while he thought that the explanatory part relates to the construction of physical and in particular mechanical models and explanatory hypotheses about the nature of physical processes which purport to reveal underlying unobservable causes of the phenomenon. For him, the explanatory part is parasitic on the representative. To support this view, he turned to the history of science, especially the history of the optical theories and of mechanics. He argued that when a theory is abandoned because it fails to cover new experimental facts and laws, its representative part is retained partially or fully in the successor theory, while the attempted explanation offered by the theory gets abandoned. He spoke of the constant breaking out of explanations which arises to be quelled. Though Duhem embedded this claim for continuity and theory change in an instrumentalist account of scientific theories, he also took it that science aims at the natural classification of the phenomenon, where a classification that is a representation of the phenomenon within a mathematical system is natural if the relationships it establishes among the phenomenon gathered by experiments correspond to a real relation among things. Hence, scientific knowledge does not go beyond the phenomenon, but in doing so, that is intending to be a natural classification, it can extend only up to relations among hidden realities whose essence cannot be grasped. The clear mark of the naturalness of a classification is when it issues in novel predictions. Hence, successful novel predictions issued by a theory are a mark for the theory getting some aspects of reality right, real relations among unobservable entities. Poincaré's relationalism. This kind of relationalism became a popular middle way between positivism and what may be called full-blown realism. Duhem himself justly traced it back to his contemporary Henri Poincaré. He noted with approval that Poincaré felt a sort of revolt against the proposition that theoretical physics is a mere collection of recipes, and he loudly proclaimed that a physical theory gives us something else than the mere knowledge of the facts that makes us discover the real relations among things. In his address to the 1900 International Congress of Physics in Paris, Poincaré made a definitive intervention in the bankruptcy of science debate and its history-fed pessimism. He described this challenge thus: the people of the world are stuck to see how ephemeral scientific theories are. After some years of prosperity, they see them successfully abandoned. They see them ruins accumulated on ruins. They predict that the theories in fashion today will quickly succumb in their turn, and they conclude that they are absolutely futile. This is what's called the bankruptcy of science. The view of the people of the world is not right. Their skepticism is superficial. They understand none of the aim and the role of scientific theories. Otherwise, they would understand that ruins can still be good for something. But unlike the positivist trend around him, Poincaré took it that scientific theories offer knowledge of the relational structure of the world behind the phenomenon. In the introduction to The Science and Hypothesis in 1902, he made clear what he took to be the right answer to the historical challenge. Without doubt, at first the theories seem to us fragile, and the history of science proves to us how ephemeral they are, yet they do not entirely perish, and each of them something remains. It is thus something we must seek to unravel, since there and there alone is the true reality. Poincaré argues what survives in theory change are relations among physical magnitudes expressed by mathematical equations within theories. His prime example was the reproduction of Fresnel's laws concerning the relation of amplitudes of reflected rays vis-a-vis the amplitude of incident rays, and the interface of two media within Maxwell's theory of electromagnetism. Although in this transition, the interpretation of these laws changed dramatically from an ether-based account to an electromagnetic field-based account for Poincare, the question express relations, and if the equations remain true, it is because these relations preserve their reality. They teach us before and after that there is such and such a relationship between something and some other thing. Only this something we used to call motion, we now call it electric current. But these names were only images substituted for the real objects which nature will internally hide from us. The true relations between these real objects are the only reality we can attain to, and the only condition is that the same relations exist between these objects as between the images by which we are forced to replace them. If these relations are known, what does it matter if we deem it as convenient to replace one image by another? In recent literature, Poincare's line of thought has come to be known as structural realism, though it may be best if we describe it as relationalism. In his introduction to the science and hypothesis, he noted that the things themselves are not what science can reach, as the naive dogmatist thinks, but only the relations between things. Apart from these relations, there is no knowable reality. It should be stressed that Poincare does not deny that there is reality outside relations, but he does deny that this reality is knowable. Note also that Poincare does not use the expression things in themselves, but the expression things themselves. Elsewhere, he talks about the nature of things or real objects. It is quite clear that he wanted to draw a distinction between how things are, what their nature is, and how they are related to each other. A plausible way to draw this distinction is to differentiate between the intrinsic and perhaps fully qualitative property of things, what he plausibly calls nature of things, and their relations. The former are unknowable, whereas the latter are knowable. So Poincare and Duhem initiated a strategy for dealing with theory change in science, which pointed to a substantial continuities among successive theories. For them, the continuity is by and large relational, in this sense mathematical. Hence, mathematically convergent scientific theories reveal the relational structure of the world. Boltzmann against historical pessimism. The relationship among answer to the historical pessimism was motivated at least part by the widespread skepticism towards the atomic theory of matter. Atomism posited the existence of unobservable entities, the atoms, to account for a host of observable phenomena, a trend among scientists opposed to the explanation of the visible in terms of the invisible was what Ludwig Boltzmann called phenomenologists, which include the early Max Planck, according to whom the aim of science was to write down for every group of phenomena the equations by means of which their behavior could be quantitatively calculated. The theoretical hypothesis for which these equations might have been deduced were taken to be the scaffolding that was discarded after the equations were arrived at. For a phenomenologist, then hypotheses are not unnecessary or useless, rather they have only a heuristic value. They lead to a stable differential equation, and that's it. According to Boltzmann, a motivation for this phenomenological attitude was the historical principle that hypotheses are essentially insecure because they tend to be abandoned and replaced by others, totally different ones. As he put it, frequently opinions which are held in the highest esteem have been supplanted within a very short space of time, but totally different theories, and nay, even as Remigius, the heathens, so now they, the phenomenologists, exhorted the theoretical physicists to co-sign to the flames the idols that but a moment previously they had worshipped. Like Poincare, Boltzmann's answer to the historical pessimism was that despite the presence of revolutions in science, there is enough continuity in theory change to warrant the claim that some achievements may possibly remain the possessions of science for all time. But unlike Poincare, Boltzmann did not restrict the criterion of invariance in theory change to relations only. The answer to the historical challenge is to look for the patterns and continuity in theory change. In fact, as Boltzmann noted, if the historical principle is correct at all, it cuts also against the equations of the phenomenologist. For unless these very equations remain invariant through theory change, there should be no warrant for taking them to be accurate descriptions of worldly relations. Besides, Boltzmann noted the very construction of the differential equations of the phenomenologist requires commitment to substantive atomistic assumptions. Hence, the phenomenologists are not merely disingenuous when they jettison the atomistic assumptions after the relevant differential equations have been arrived at. Their move is self-undermining. In light of the historical principle, the success of the mathematical equations would lead to their defeat, since the very theory that led to the success would fall foul of the historical principle, it would have to be abandoned. The history-based pessimism and the relevant debate came to an end by the triumph of the atomism in the first decade of the 20th century due to the work of Albert Einstein and the French physicist Jean Perrin on the atomic explanation of Brownian motion, one after the other of major scientists who were initially skeptical about the atomic conception of matter came to accept atomism. The French philosopher André Lalande captured this point. Perrin, professor of physics of the Sorbonne, has described in The Atoms, with his usual lucidity and vigor, the recent experiments in which he has taken so considerable a part, which prove conclusively that the atoms are physical realities and not symbolic conceptions, as people have for a long time been fond of calling them. By giving them precise and concordant measures for their weights and dimensions, it is proved that bodies actually exist, with which, though invisible, are analogous to all points of those which we see and touch. An old philosophical question thus receives a positive solution. Be that as it may be, what this brief account of the history of the historical challenge to realism reveals are that two major lines of defense of realism at play. Both lines of defense are based on the presence of a substantial continuity and theory change in the history of science. This continuity suggests that the disruption of the scientific image of the world as theories change is less radical than is assumed by the historical challenge to realism. But the two lines of defense, the Poincare-Duhem and the Boltzmann one, disagree over what is retained when theories change. The Poincare-Duhem line of defense focuses on mathematical equations which express relations and claims that only relations among unobservable things are knowable, whereas the Boltzmann line of defense focuses on whatever theoretical elements, including entities like atoms, are retained when theories change. Hence, it does not limit scientific knowledge to the knowledge of relations only. Both lines have resurfaced in the current debate. Scientific realism and the pessimistic induction. The disastrous meta-induction. Capitalizing on the line of work of Richard Boyd and the early Hilary Putnam, took scientific realism to involve three theses. 1. Theoretical terms refer to unobservable entities. 2. Theories are approximately true. And 3. There is a referential continuity in theory change. Putnam argued that the failure of the third thesis would lead to a disastrous meta-induction. Just as no term used in the science of more than 50 or whatever years ago referred, so it will turn out that no term used now, except maybe observational terms, if there is such, refers. In answer to this disastrous history-fed argument was the development of a causal theory of reference, which allows for referential continuity in theory change. This theory was first suggested by Saul Kripke in 1972 as an alternative to the dominant descriptive theories of reference of proper names, and was extended by Putnam to cover natural kind terms and theoretical terms. According to the causal theory, the reference of theoretical terms is fixed during an introducing event in which an entity or physical magnitude is posited as the cause of various observable phenomena. The term then refers to the posited entity, though some kind of description of the positive entity will be associated with the term. They do not play a role in the reference fixing. The referent has been fixed existentially. It is the entity causally responsible for certain effects. The causal theory of reference makes it possible that the same term featuring in different theories refers to the same worldly entity. If, for instance, the referent of the term electricity is fixed existentially, all different theories of electricity refer to and dispute over the same existentially given magnitude, electricity. Better, the causal agent and salient electrical effects. Hence, the causal theory makes available a way to compare past and present theories and to claim that the successor theory is more truth-like than its predecessor, since it is truer things of the same entities. It turns out, however, that the causal theory faces a number of conceptual problems, most notable of which is that it makes referential success inevitable insofar as the phenomenon which led to the introduction of a new theoretical term do have a cause. Philosophers of science have tried to put forward a causal descriptive theory of reference, which makes referential continuity possible, whilst allowing room for causal descriptions in fixing the reference of theoretical term. The principle of no privilege. An analogous history-fed pessimism argument can be based on the so-called principle of no privilege, which was advanced by Mary Hess in her 1976. According to this principle, our own scientific theories are held to be much subjected to radical conceptual change as past theories are seen to be. This principle can be used for the derivation of the strong conclusion that all theories are false. As Hess put it, every scientific system implies a conceptual classification of the world into an ontology of fundamental entities and properties. It is an attempt to answer the question, what is the world really made of? But it is exactly these ontologies that are most subject to radical change throughout the history of science. Therefore, in the spirit of the principle of no privilege, it seems that we must say that either that all of these ontologies are true, we must give a realistic interpretation of all of them, or we must say that they are all false, but they cannot all be true in the same world because they contain conflicting answers. And to the question, what is the world made of? Therefore, they must all be false. This argument engages the history of theory change in science in a substantial way. As Hess admitted, the principle of no privilege arises from accepting the induction from the history of science. Hess' argument starts with the historical premise that as science grows over time, there has been a recognizable pattern of change in the ontology of fundamental entities and properties posited by scientific theories. Assuming then the principle of no privilege, it is argued that current theories too will be subjected to a radical change in the ontology of the entities and properties they posit. Hence, current theories are as false as the past ones. The problem with this kind of argument is that historical premise should be borne out by the actual history of theory change in science. It's not enough to say that scientific theories change over time. These changes should be such that newer theories are incompatible with the past ones, or to use Hess' idiom, it should be shown that the past and current scientific ontologies are incompatible with each other. Showing incompatibility between the claims made by current theory and the past theory requires a theory of reference of theoretical terms, which does not allow the terms featuring in different theories can nonetheless refer to the same entity in the world. Hence, it is question begging to adopt a theory reference, which makes it inevitable that there is a radical reference variance in theory change. Referential stability, as noted already, makes possible the claim that past and present ontologies are compatible, even if there have been changes in what current theories say of the posited entities. The revolutionary induction from the history of science about theory change can be blocked by pointing to a pattern of substantial continuity in theory change. Getting nearer to the truth. Can a history-fed argument be used in defense of realism? William Newton Smith, 1981, was perhaps the first in the recent debate to answer positively this question. Scientific realism is committed to the two following theses. Theories are true or false in virtue of how the world is, and the point of the scientific enterprise is to discover explanatory truths about the world. According to Newton Smith, the second point is under threat if we reflect on the fact that all physical theories in the past have had their heyday and have eventually been rejected as false. And he added, indeed, there is inductive support for pessimistic induction, and any theory will be discovered to be false within, say, 200 years of being propounded. We may think of some of our current theories as being true, but modesty requires us to assume that they are not so. For what is so special about the present, we have good inductive grounds for concluding that the current theories, even our most favorite ones, will come to be seen as false. Indeed, the evidence might even be held to support the conclusion that no theory that will ever be discovered by the human race is strictly speaking true. So how can it be rational to pursue that which we have evidence for thinking can never be reached? The key answer to this question is that even if truth cannot be reached, it is enough for the defense of realism to posit an interim goal for the scientific enterprise, the goal of getting nearer to the truth. If this is the goal, the sting of the preceding induction is removed. Accepting pessimistic induction is compatible with maintaining that current theories, while strictly speaking false, are getting nearer to the truth. But aren't all false theories equally false? The standard realist answer is based on what Newton Smith calls the animal farm move. The key point then is that the defense of realism against the historical induction requires showing that there is indeed a privilege that current theories enjoy over past one. which is strong enough to block transferring or inductive grounds, features of past theories to current ones. For most realists, the privilege current theories enjoy over the past ones is not that they are true, while the past theories are false. Rather, the privilege is that they are more truth-like than past theories because they have more predictive power than the past theories. The privilege is underpinned by an explanatory argument. The increasing truth-likeness of current theories best explains their increasing predictive and empirical success. But there is a way to see the historical challenge to realism, which makes it have as its target precisely to undercut the explanatory link between empirical success and truth-likeness. This was brought under sharp relief in the subsequent debates. The plethora of false theories. Last Australian, God bless. The plethora of false theories. The most famous history-based argument against realism, issued by Larry London in 1981, was meant to show how the explanatory link between success and truth-likeness is undermined by the taking seriously of the history of science. It should be noted that Loudon's argument has been subjected to several diverging interpretations, a particularly popular one according to which Loudon argues inductively for the falsity of past theories to the falsity of the current ones. This argument may be put forward. The history of science is full of false theories which have been empirically successful for long periods of time, and yet were shown to be false about the deep structure claims they had made about the world. It is similarly full of theoretical terms featuring in successful theories which do not refer. Therefore, by simple meta-induction on scientific theories, our current successful theories are likely to be false. Loudon substantiated the claim by means of what he called the historical gambit. The following list, which could be extended ad nauseam, gives theories which were once empirically successful and fruitful, yet just false. Loudon boldly noted the famous 6-to-1 ratio. I dare say, for every highly successful theory in the past of science which we now believe to be a generally referring theory, one could find half a dozen once successful theories which we now regard as substantially non-referring. If we're to take seriously the plethora of theories that were both successful and false, it appears that Loudon argument is meant to be a generally inductive argument. There's been a plethora of theories, ratio 6-to-1, which were successful and yet not truth-like. Therefore, it's highly probable that current theories will not be truth-like despite their success. An argument such as this has obvious flaws. Two are the most important. The first is that the basis of induction is hard to assess. This does not just concern the 6-to-1 ratio, of which one may ask, where does it come from? It also concerns the issue of how we individuate and count theories, as well as how we judge success and referential failure. Unless we are clear-cut on all the issues in advance of the inductive argument, we cannot even start putting together the inductive evidence for its conclusion. The second flaw is that the conclusion is too strong. It is supposed to be that there is a rational warrant for the judgments that current theories are not truth-like. The flaw with this kind of sweeping generalization is precisely that it totally disregards the fresh, strong evidence there is for current theories. It renders current evidence totally irrelevant to the issue of their probability of being true. Surely this is unwarranted, not only because it disregards potentially important differences in the quality and quantity of evidence there is for current theories, differences that would justify treating current theories as more supported by available evidence than past theories, whereby the then available evidence, but also because it makes a mockery of looking for evidence for scientific theories. If I know that X is more likely than Y, and that this relationship cannot change by doing Z, then there's no point in doing Z. The second flaw becomes even more apparent when one takes a closer look at the successful yet false theories in Loudon's list. Would anyone be willing to insist that, say, the humoral theory of medicine, the vital force theory of physiology, and the theory of crystalline spheres are on par with our current scientific theories with the same domain of application? The difference between their respective evidence is undoubtedly enormous. Nevertheless, it would rather be mistaken to restrict our attention to those theories comprising Loudon's own list. Indeed, subsequent scholars have provided new lists of cases where admittedly false theories had been used in the derivation of impressive empirical predictions. Most notably, Timothy Lyons and Peter Vickers suggested the following partial overlapping lists. These This summarized much of the work done by the historians of science and historically informed philosophers of science. They are meant to present cases of empirical success that were supposedly brought about by false theoretical hypotheses, hence offering a fresh source of historical challenges to realism. At first sight, the cases provided look substantially different from the majority of Loudon's examples. The success, at least in some of them, are more impressive, yet it remains to be seen whether there are more troublesome for scientific realism. The divide at empirical strategy. If we think of the pessimistic argument not as inductive but as a warrant remover argument, and if we also think of the fate of past theories should have a bearing on what we are warranted in accepting now, we should think of it structure differently. It has been argued by Ceteris that we should think of the pessimistic argument as a kind of reductio. The argument of Loudon above aimed to discredit the claim that there is an explanatory connection between empirical success and truth likeness, which would warrant the realist view that current successful theories are truth-like. And if we view the historical challenge in this way, as a potential warrant remover argument, the past record of science does play a role in it, since it is meant to offer this warrant remover. Ceteris 1996 reconstruction of Loudon's argument as follows. The argument: currently successful theories are truth-like. If currently successful theories are truth-like, then past theories are not. These characteristically false past theories were nonetheless empirically unsuccessful, the historical gambit. Hence, empirical success is not connected with truth-likeness, and truth-likeness cannot explain success. The realist potential warrant for A is defeated. Premise B of the argument is critical. It is meant to capture radical discontinuity in theory change, which was put thus stated in the material mode. Past theories are deemed not to have truth-like because the entities they posited are no longer believed to exist, and or because the laws and mechanisms they postulated are not part of our current theoretical description of the world. In this setting, the historical gambit makes perfect sense unless there are past successful theories which warrantedly deemed not to be truth-like. The second premise cannot be sustained, and the warrant-removing reductio of the first fails. If the third can be substantiated, success cannot be used to warrant the claim that current theories are true. The realist explanatory link between truth-likeness and empirical success is undercut. The third claim can be substantiated only by examining past successful theories and their fate. History of science is therefore thereby essentially engaged. The realist response has come to be known as the divide at empirical strategy to refute the pessimistic argument. The focus of the strategy was on rebutting the claim that the truth of current theories implies that past theories cannot be deemed truth-like. To defend realism, realists needed to be selective in their commitments. This selectivity was developed by Kitcher and independently by Ceteris. One way to be selective is to draw a distinction between working points of the theory, those theoretical posits that occur substantially in the explanatory schemata of the theory, and presuppositional posits, putative entities that appear to exist if the instances of the explanatory schemata of the theory are to be true. Another way is to draw a distinction between the theoretical claims that essentially or ineliminately contribute to the generation of success of a theory and those claims that are idle components that have had no contribution to a theory's success. The underlying thought is that the empirical success of a theory does not indiscriminately support all the theoretical claims of a theory, but rather the empirical support is differentially distributed among the various claims of the theory according to the contributions that they make to the generation of this success. Generally, Kitcher and Ceteris have argued that there are ways to distinguish between the good and the bad parts of the past abandoned theories and to show that the good parts, those that enjoyed evidential support, were not idle components and the like, were retained in the subsequent theories. It is worth noting that methodologically the divided empirical strategy recommended that the historical challenge to realism can only be met by looking at the actual success of past successful theories and by showing that those parts of past theories that were fueling theory successes were retained in subsequent theories, and that those theoretical terms which were central in the relevant past theories were referential. In fact, Vickers has recently made the methodological suggestion that if one's sole aim is to cope with a historical challenge, then it's sufficient that one shows that the abandoned hypotheses were not essential for the relevant theory's empirical success without at the same time taking side of which are the essential theoretical hypotheses. As Vickers claims, in order to respond to a pessimistic induction style challenge, all the realist needs to do is show that the specific assumptions identified by the anti-realist do not merit realist commitment. And she can do this without saying anything about how to identify the posits which do merit realist commitment. Besides, according to Vickers' conception of the dialectic of the pessimistic induction debate, the onus of proof lies with the anti-realist. The anti-realist has to reconstruct the derivation of the prediction, identify the assumptions that merit realist commitments, and then show that at least one of them is not truth-like by our current lights. And then all the realist needs to show is that the specific assumptions were essential. In some, Vickers argues that the project of responding to the historical challenge and the project of explaining what realists should commit to have to be kept distinct. At any rate, either employed in the definition of the trustworthy theoretical parts or in the mere handling of historical challenge, the divide at Empira move suggests that there has been enough theoretical continuity and theory change to warrant the realist claim that science is on the right track. Criticisms of the divide at Empira. The realist move from substantive continuity and theory change to truth-likeness has been challenged on grounds that there is no entitlement to move from whatever preservation and theoretical constituents there is in theory change to these constituents being truth-like. Against this point, it has been argued that the realist strategy proceeds in two steps. The first is to make the claim of continuity or convergence, plausibility, to show that there is continuity in theory change. Substantive theoretical claims that feature in past theories are played a key role in their successors, especially novel predictions, have been incorporated into subsequent theories and continue to play an important role in making them empirically successful. But this first step does not establish that the convergence is to the truth. For this claim to be made plausible, a second argument is needed that the emergence of this evolving but convergent network of theoretical assertions is best explained by the assumption that it is by and large truth-like. So there's, after all, entitlement to move from convergence to truth-likeness, insofar as truth-likeness is the best explanation of this convergence. Another critical point was that the divide at Empira strategy cannot offer independent support to realism since it is a tailor-made to suit realism. It is the fact that the very same present theory is used both to identify which parts of the past theories were empirically successful and which parts were approximately true that accounts for the realist wrong impression that these partly coincide. With this strategy of analysis, an impressive retrospective convergence between our judgments of the sources of the past theory's success and the things that it got right about the world is virtually guaranteed. It is the very fact that some features of a past theory survive in a present account of nature that leads the realist both to regard them as true and to believe that they were the sources of the rejected theory's success or effectiveness. So the apparent convergence of truth and the sources of success in past theories is easily explained by the simple fact that both kinds of retrospective judgments have in common source in our present beliefs about nature. It has been claimed by Psilos, 2009, that the foregoing objection is misguided. The problem is this: there are theories scientists currently endorse, and there are theories that had been endorsed in the past. Some, but not all of them, were empirically successful, perhaps for long periods of time. They were empirically successful, irrespective of the fact that subsequently they came to be replaced by others. This replacement was contingent matter that had to do with the fact that the world did not fully cooperate with the then extant theories. Some of their predictions failed, or the theories became overly ad hoc or complicated in their attempt to accommodate anomalies or what have you. The replacement of theories by others does not cancel out the fact that the replacement theories were empirically successful. Even if scientists had somehow failed to come up with new theories, the old theories would not have ceased to be successful. So success is one thing, replacement is another. Hence, it is one thing to inquire into what features of some past theories accounted for their success, and quite another to ask whether these features were such that they were retained in subsequent theories of the same domain. These are two independent issues, and they can be dealt with both conceptually and historically independently. One should start with some past theories and, bracketing the question of their replacement, try to identify on independent grounds the sources of their empirical success, that is, to identify those theoretical constituents of the theories that fueled their success. When a past theory has been, as it were, anatomized, we can then ask the independent question of whatever there is in a sense in which the sources of success of a past theory that the anatomy has identified are present in our current theories. It's not then the case that the current theory is the common source for the identification of the successful parts of the past theory and of its truth-like parts. Apart from Stanford's case against the divide and impure move, the latter has become the target of criticisms, among the others by Timothy Lyons. Lyons, 2006, focuses critique on Silo's criterion for the conditions under which hypothesis indispensability contributes to the derivation of a novel prediction. Thus construes, Lyons criticizes Silo's criterion for essentially as being superfluous, unmotivated, and therefore inappropriate. In reply, Lyons, Peter Vickers, and ally have defended the divide and impure move against pessimistic induction. According to Vickers, when realists are presented with an instance of seemingly success-inducing yet false hypothesis, all they need to do is show that the specific hypothesis does not satisfy the above condition. It should be noted, however, that this, in essence, is the strategy recommended by Psilos in his 1994 paper, where he aimed to show using specific cases that various assumptions do not merit realist commitment because they're weaker assumptions that fuel the derivation of successful predictions. Ally stressed it is motivated by a plausible epistemic principle associated with the Occam's razor. In abductions, we can assume only what is essential, the weakest hypothesis sufficient to explain a given effect, but if the hypothesis, although deployed, was not essential in deriving the novel prediction in hand, it is not essential in explaining its derivation either. Therefore, deployment realist need not and must not be committed to its truth. The Vickers-Ally refinement of the divide and impure move has not been uncontested. It has been criticized on principal grounds as well as for not being sufficient in dealing with the pessimistic induction style challenges. For instance, Dean Peters, 2014, argues inter alia that Victor's criterion for essentiality cannot account for the unificatory aspect of the scientific theorizing, whereas Florian Boget, 2021, and Dana Tuladzicki have provided new historical counterexamples within the field of nuclear physics and phycometry and the 19th century miasma theory of disease, respectively, that cannot be handled, or so it is argued by the Vickers-Ally criterion. It should also be noted, according to Vickers himself, the employment of his condition in dealing with pessimistic induction seems to bring scientific realism dangerously close to structural realism. Structural realism. An instance of the divide and impure strategy is structural realism. This view has been associated with John Worrell, 1989, who revived the relationist account of theory change that emerged at the beginning of the 20th century in opposition to scientific realism. Structural realism restricts the cognitive content of scientific theories to their mathematical structure, together with the empirical consequences. But in opposition to instrumentalism, structural realism suggests that the mathematical structure of a theory represents the structure of the world, real relations between things. Against pessimistic induction, structural realism contends that there is continuity in theory change, but this continuity is again at the level of mathematical structure. Hence, the carryover mathematical structure of the theory correctly represents the structure of the world, and this best explains the predictive success of the theory. Structural realism was independently developed in the 1970s by Grover Maxwell in an attempt to show that the Ramsey sentence approach to theories need not lead to instrumentalism. Ramsey sentences go back to the seminal work of Frank Ramsey, 1929. To get the Ramsey sentence of a finitely axiomatizable theory, we conjoin the axioms of the theory in a single sentence, replace all the theoretical predicates with a single with distinct variables, and bind these variables by placing an equal number of existential qualifiers in front of the resulting formula. The Ramsey sentence that replaces theory has exactly the same observational consequences as the theory. It can play the same role as the theory in reasoning. It is truth evaluable if there are entities that satisfy it, but since it dispenses altogether with theoretical vocabulary, it refers to whatever entities satisfy it only by means of quantifiers. It was taken to remove the issue of the reference of theoretical terms predicates. Structural realism was suggested to be the view that scientific theories issue in existential commitments to unobservable entities, and all observational knowledge of unobservables is structural knowledge, knowledge not of the first order or intrinsic properties, but rather of their higher order or structural properties. The key idea here is that a Ramsey sentence satisfies both conditions. So we might say that if true, a Ramsey sentence gives us knowledge of the structure of the world. There is a certain structure that satisfies the Ramsey sentence, and the structure of the world or of the relevant worldly domain is isomorphic in this structure. Though initially Worrell's version of structural realism was different from Maxwell's, being focused on and motivated by Poincaré's argument for structural continuity and theory change, in later work, Worrell came to adopt the Ramsey sentence version of structural realism. More recently, David Papineau, 2010, has argued that if we identify the theory with its Ramsey sentence, it can be argued that past theories are approximately true if there are entities which satisfy or nearly satisfy their Ramsey sentences. The advantage of this move, according to Papineau, is that the issue of referential failure is bypassed when assessing theories for approximate truth, since the Ramsey sentence replaces the theoretical terms with existential bound variables. But as Papineau admits, the force of the historical challenge to realism is not thereby thwarted, for it may well be the case that the Ramsey sentence of most past theories are not satisfied, not even nearly so. Induction or deduction. In the more recent literature, there has been considerable debate as to how exactly we should understand pessimistic induction. There are those like Anjan Chakravarti who take it as the pessimistic induction is an induction. He says pessimistic induction can be described as a two-step worry. First, there's an assertion to the fact that the history of science contains an impressive graveyard of theories that were previously believed to be true, but subsequently judged to be false. Secondly, there's induction on the basis of this assertion, whose conclusion is that the current theories are likely future occupants of the same graveyard. Yet it's plausible to think that qua an inductive argument, history-based pessimism is bound to fail. The key point here is that the sampling of theories which constitute the inductive evidence is neither random nor otherwise representative of theories in general. It has been argued that seen as an inductive argument, pessimistic induction is fallacious. It commits the base rate fallacy. If in the past there have been many more false theories than true ones, if in other words, truth has been rare, it cannot be concluded that there is no connection between success and truth. The answer is indeterminate if we don't take into account the base rate of truth, the incidence rate of truth in the population of theories. Seen in this light, pessimistic induction does not discredit the reliability of success as a test for a truth of a theory. It merely points to the fact that truth is scarce among past theories. Challenging this inductive credentials of pessimistic induction has acquired a life of its own. The standard objection is that theories are not uniform enough to allow an inductive generalization of the form seen one, seen them all. That is, theories are diverse enough over time, structure, and content not to allow us to take a few of them, not pick randomly as representative of all the projected and characteristics shared by those picked to all theories in general. In particular, the list that London produced is not a random sample of theories. They are all between the 20th century and have all been chosen solely on the basis they had some success, irrespective of how robust these successes were. An argument of the form, a certain percent of past theories are false, therefore the percent of all successful theories are false, would be a weak inductive argument because it fails to provide grounds for projecting the property of the observed members of the reference class to unobserved members of the reference class. Things would be different if we had a random sampling of theories. Mizrahi collected 124 instances of theories from various sources and picked at random 40 of them. The 40 were then divided into three groups: accepted theories, abandoned theories, and debated theories. Of the 40 theories, 15% were abandoned and 12% debated. Mizrahi then notes that these randomly selected data cannot justify an inductively drawn conclusion that most successful theories are false. On the contrary, an optimistic induction would be more warranted. 72% of the sample theories are accepted theories considered true. Therefore, 72% of all theories are accepted theories considered true. Mizrahi has come back to the issue of random sampling and has attempted to show that the empirical evidence is against pessimistic induction. In the history of science, if the history of science were a graveyard of dead theories and abandoned posits, then random samples of scientific theories and theoretical posits would contain significantly more dead theories and abandoned posits than live theories and accepted posits. It is not the case that random samples of scientific theories and theoretical posits contain significantly more dead theories and abandoned posits than live theories and accepted posits. Therefore, it is not the case the history of science is a graveyard of dead theories and abandoned posits. A similar argument has been defended by Park in 2011. We may call it the explosion argument. Most key theoretical terms of successful theories of the 20th century refer in the light of current theories, but then most central terms to successful past theories refer the reason being that there are more 20th century theories than theories in total. This is because the body of scientific knowledge exploded in the 20th century with far more human and technological resources. Let's call this broad way to challenge the inductive credentials of the pessimistic argument, the privilege for current theory strategy. This has been adopted by Michael Devitt, 2007. 2. Though restricted to entities, Devitt, who takes realism to be a position concerning the existence of unobservables, noted that the right question to ask is, what is the success ratio of past theories, where the success ratio is the ratio of the determinately existence to the determinately non-existence plus indeterminates. Asserting a privilege for current science, he claims that we are now much better at finding out about unobservables. According to him, then, it is fairly indubitable that the historical record shows improvement over time in our success ratio for unobservables. In a similar fashion, but focusing on current theories, Doppelt in 2007 claims that realists should confine their commitment to the approximate truth of current best theories. What the best theories are those that are both the most successful and well established. The asymmetry between current best theories and past ones is such that the success of current theories is of a different kind than the success of past theories. The difference Doppelt assumes is so big that the success of current theories can only be explained by assuming that they are approximately true, whereas the explanation of the success of past theories does not require this commitment. If this is right, there is sufficient qualitative distance between past theories and current best ones to block any pessimistic induction from the successful but false superseded theories to the likelihood that our most successful and well-established current theories are also probably false. The key difference, Doppelt argues, is that our best current theories enjoy a singular degree of empirical confirmation impossible for their predecessors, given their ignorance of so many kinds of phenomenon and dimensions of nature discovered by our best current theories. This singular degree of empirical confirmation amounts to raising the standard of empirical success to a level unreachable by past theories. The advocate of pessimistic induction can argue that past best theories also raised and met the standards of empirical success, which inductively supported the conclusion that current best theories will be superseded by other theories that will meet even higher standards of success. Doppelt's replies that this new version of pessimistic induction should not be given a free pass as though it were on par with the original pessimistic induction, the reasoning being that in the history of the sciences, there is greater continuity in the standards of empirical success than in the theories taken to realize them. Hence, the standards of empirical success changes slower than theories. Hence, it is not very likely that current standards of empirical success will change anytime soon. It has been argued, however, that Doppelt cannot explain the novel predictive success of past theories without arguing that they had truth-like constituents. Besides, as Ely puts it, current best theories explain the empirical success of discarded ones only to the extent that they show that the latter were partly true. The privilege for current theory strategies has been supported by Ludwig Farbach, 2011. The key point is that the strategy is that the history of science does not offer a representative sample of the totality of theories that should be used to feed the historical pessimism of pessimistic induction. In order to substantiate this, Farbach suggested, based on extensive bibliometric data, that over the last 3 centuries, the number of papers published by scientists, as well as the number of scientists themselves, has grown exponentially, with a doubling rate of 15 to 20 years. Hence, he claims the past theories that fed the historical premise of pessimistic induction were produced during the time that the first 5% of all scientific works ever done by scientists. As such, the sample is totally unrepresentative of theories in total, and hence the pessimistic conclusion the current theories are most likely to be false and abandoned in due course is inductively unwarranted. Moreover, Farbach argued the vast majority of theories enunciated in the last 50 to 80 years, which constitute the vast majority of scientific work ever published, are still with us. Hence, as he puts it, the anti-realist will have a hard time finding even one or two convincing examples of similarly successful theories that were accepted in the last 50 to 80 years for some time but later abandoned. Since there have been practically no changes among our best, most successful theories, Farbach suggests an optimistic meta-induction to the effect that they will remain stable in the future. All the empirical consequences which scientists will ever have occasion to compare with results of observation at any time of the future are true. The conclusion is that pessimistic induction is unsound. Its conclusion that many of our best scientific theories will fail empirically in the future cannot be drawn. The key assumption of the foregoing argument is that there is a strong connection between the amount of scientific work as measured by the number of journal articles and the degree of success of the best scientific theories. But this can be contested on the grounds that it is a lot easier to publish currently than it was in the 17th century, and that the current research is more tightly connected to the defense of a single theoretical paradigm than before. This might well be a sign of maturity of current science, but as it stands, it does not show that the present theoretical paradigm is not subject to radical change. Florian Muller, 2015, put the point in terms of decreasing marginal revenues. The correlation between increased scientific work and scientific progress, which is assumed by Farbach, may not be strong enough. It seems more plausible to expect decreasing marginal revenues of scientific work, since it usually takes much less time to establish very basic results than to make progress in a very advanced state of science. The privilege for current theory strategy can be further challenged on the ground that requires some fundamental difference between the theories we currently accept and the one successful theories we have since rejected. As Brad Ray in 2013 has argued, Farbach's strategy is doomed to fail because the argument from exponential growth could be repeated at former periods too, thereby undermining itself. Imagine that we go back to 1950 and we look at the period between 1890 and 1950. We could then argue along Farbach's lines that if the pre-1890 theories, which were false and abandoned, were an unrepresentative sample of all theories, and that the recent theories 1890 to 1950 are by far the most theories until 1950, and that since most of them have not been abandoned by 1950, that they are likely to remain impervious to theory change. Or imagine that we are further back in 1890 and look at the theories of the period of 1830 to 1890. We could run the same argument about those theories, that they're likely to survive theory change. But if we look at the historical pattern, they did not survive, nor did the theories between 1890 and 1950. But the same token, we should not expect current theories to survive theory change. Is there room for first defending an epistemic privilege for current science? 2 points are worth making. The first is that it's hard to defend some kind of epistemic privilege of current science if the realist argument against pessimistic induction stays only at a level of statistics, even assuming that there can be statistics over theories. If there is an epistemic privilege of current science in relation to past science, it is not a matter of quantity but of quality. The issue is not specifying how likely it is that an arbitrary current theory is true given the evidence of the past record of science. The issue instead is how specific scientific theory or real theory that describes and explains certain well-founded worldly phenomenon is supported by evidence there is for it. If we look at the matter from this perspective, we should look at case histories and not at the history of science at large. The evidence there is for a specific theory need not be affected by past failures in the theoretical understanding of the world in general. The reason is that there is local epistemic privilege, that is, privilege over past relevant theories concerning first-order evidence and specific methods. The second point is that Ray's argument against Farbach is, in effect, that there can be a temporal meta-induction, which undermines at each time or period the privilege that scientific theories at the time or period are supposed to have. So Ray's point is this. At each time, scientists claim that their theories are not subject to radical change in subsequent times, but if we look at the pattern of theory change over time, the history of science shows that there have been subsequent times such that the theories accepted were considered false and abandoned. Hence, he takes it that at no time are scientists justified in accepting their theories as not being subject to radical change in the future, but this kind of argument is open to criticism. It assumes, as it were, homogeneity, that science at all times is the same when it comes to how far it is from the truth. Only on this assumption can it be argued that at no time can scientists claim that their theories are not subject to radical change, for if there are senses in which the subsequent theories are closer to the truth than in their predecessors, it is not equally likely that they will be overturned and their predecessors were. The point then is that though at each time or period scientists might well claim that their theories are not subject to radical change at subsequent times, they are not equally justified in making this claim. There might well be times or periods in which scientists are more justified in making the claims that their theories are not subject to radical change at subsequent times simply because they have no reason to believe that their theories are truer than their predecessors. An analogous point was made by Park in 2016. He defined what he called proportional pessimism as the view that as theories are discarded, the inductive rationale for concluding the next theories will be discarded grows stronger. This view entails that the more theories that have been discarded before the theory is discarded, the more justified we are in thinking that the theory is likely to be discarded. However, it is also the case that based on their greater success, we are more justified to take newer theories to be more likely to be truth-like than older ones. We then reach a paradoxical situation. We are justified to take newer theories to be both more probable than older ones and more likely to be abandoned than older ones. If an inductive rendering of historical pessimism fails, would a deductive rendering fare better? Could pessimistic induction be considered at least as a valid deductive argument? Ray interprets the original argument by Loudon as being deductive, and he notes, as far as Loudon is concerned, a single successful theory that is false would falsify the realist claim that all successful theories are true, and a single successful theory that refers to a non-existent type of entity would falsify the realist claim that all successful theories have generally referring theoretical terms. But if this is the intent of the argument, history plays no role in it. All that is needed is a single counterexample, past or present. This should be noted, is an endemic problem with all attempts to render pessimistic induction as a deductive argument. Mueller, for instance, notes that fundamental problems raised from pessimistic induction is simply that successful theories can be false. He adds, even just one counterexample, as long as it's not explained away, undermines the claim that truth is the best explanation for the success of theories, as it calls into question the explanatory connection in general. Thus put, the history of the past failures plays no role in pessimistic induction. Any counterexample, even one concerning a current theory, will do. How is it best to understand the realist thesis that the history of science is supposed to undermine? Mizrachi notes that the realist claim is not meant to be a universal statement. As he puts it, success may be a reliable indicator of an approximate truth, but this is compatible with some instances of successful theories that turn out to be approximately true. In other words, that a theory is successful if is a reason to believe that it is approximately true, but it is not a conclusive proof that the theory is approximately true. The relationship between success and approximate truth in this sense is more like the relation between flying and a bird. Flying characterizes birds, even if kiwis do not fly. If this is so, then there is need for more than one counterexample for the realist thesis to be undermined. A recent attempt to render pessimistic induction as a deductive argument is by Timothy Lyons. He takes realism to issue the following meta-hypothesis: our successful scientific theories are approximately true. He then reconstructs pessimistic induction thus: if the realist meta-hypothesis were true, then we would have no successful theories that cannot be approximately true. If we did, each would be a miracle, which no one of us accepts. However, we do have successful theories that cannot be approximately true. The list of miracles, therefore, not the realist meta-hypothesis is false, and the no miracles argument put forward to justify the meta-hypothesis is unacceptable. This is supposed to be a deductive argument against the meta-hypothesis, but in his argument, the history of science plays no role. All that is needed for the argument above is to sound a single instance of a successful theory that is not true. A single non-white swan is enough to falsify the hypothesis all swans are white. There is no point in arguing here. The more the merrier. In a similar fashion, it does not add much to argument to claim the quest to empirically increase the quantity of instances is rather to secure the soundness of the modus tollens, to secure the truth of the pivotal second premise, the claim that there are counter instances to the realist meta-hypothesis. In any case, a critical question is, can some false but rigorously empirically successful theories justifiably be deemed truth-like from the point of view of successor theories? This question is hard to answer without looking at actual cases in the history of science. The general point made by Vickers is that it is not enough for the challenger of realism to identify some component of past theories which were contributing to their successes, such that they were not retained in subsequent theories. The challenger of realism should show that false components merit realist commitment. If they do not, that is enough to answer the historical challenge. More generally, the search for a general form of the pessimistic induction or deduction has yielded the following problem. If the argument is inductive, it is at best weak. If the argument is deductive, even if taken to be sound, it makes the role of the history of science irrelevant. New induction. Stafford has aimed to replace pessimistic induction with what he calls a new induction in the history of science, according to which past historical evidence of transient underdetermination of theories by evidence makes it likely that current theories will be supplanted by hitherto unknown conceived ones, which nonetheless are such that when they are formulated, they will be at least as well confirmed by the evidence as the current ones. But the new induction is effective, if at all, only in tandem with pessimistic induction. For if there is continuity in our scientific image of the world, the hitherto unconceived theories will replace the current ones and won't be radical rivals they are portrayed to be. When it comes to the realist commitment to theories, the proper philosophical task is to ignore neither the first order scientific evidence that there is for a given theory nor the lessons that can be learned for the history of science. Rather, the task is to balance the first order and the second order of evidence. The first order evidence is typically associated with whatever scientists take into account when they form an epistemic attitude towards a theory. It can be broadly understood to include some of the theoretical virtues of the theory at hand, of the kind that typically go into plausibility judgments associated with assignment of prior probabilities to theories. The second order evidence comes from the past record of scientific theories and or from meta-theoretical philosophical considerations that have to do with the reliability of scientific methodology. It concerns not particularly scientific theories, but science as a whole. The second order evidence feeds claims such as those that motivate pessimistic induction or the new induction. Actually, the second order evidence is multifaceted. It is negative, showing limitations and shortcomings, as well as positive, showing how learning from experience can be improved. Okay, yeah, God bless. That was really long. A lot of information there. So let me keep it going. I have more stuff to review. Let me just take a break. I'm going to say Kriya Shema and pour myself another drink. A lot of stuff to cover. I didn't realize how long these were. I'd hoped to do 5 today. I might just end up doing 4 because these are so long. So you just got to get these done. A lot of due diligence, a lot of stuff. So sorry about the dead time here. Just got to catch my breath and a lot of stuff to cover. And anybody finding this useful, God bless. Hope that glad to provide a service. Okay, yeah, sorry about the dead time. Just my throat's a little dry. Okay, just say Kriya Shema, then we'll get right back to work. Okay, so let's next look at theoretical terms in science. Theoretical terms in science. A simple explanation of theoreticity says that a term is theoretical if and only if it refers to a non-observational entities. Paradigmatic examples of such entities are electrons, neutrinos, gravitational forces, and genes, etc. There is yet another explanation of theoreticity. A theoretical term is one whose meaning becomes determined through the axioms of a scientific theory. The meaning of the term force, for example, is seen to be determined by Newton's laws of motion and further laws about special forces such as the law of gravitation. Theoreticity is a property that is commonly applied to both expressions in the language of science and the reference and concepts of such expressions, objects, relations, and functions, as well as concepts thereof may thus qualify as theoretical in a derived sense. Several semantics have been devised that aim to explain how a scientific theory contributes to the interpretation of the theoretical terms and, as such, determines what they mean and how they are understood. All these semantics assume the respective theory to be given in an axiomatic fashion, yet theoretical terms are also recognizable in scientific theories which have as yet resisted a satisfying axiomization. Theoretical terms pertain to a number of topics in the philosophy of science. A fully fledged semantics of such terms commonly involves a statement about scientific realism and its alternatives. Such a semantics, moreover, may involve an account of how observation is related to theory in science. All formal accounts of theoretical terms deny the analytical synthetic distinction to be applicable to the axioms of a scientific theory. The recognition of theoretical terms in the language of science by Carnap thus amounts to a rejection of an essential tenet of earlier logical empiricism and positivism, the demonstration that all empirically significant sentences are translatable into observational language. The present article explains the principal distinction between observational and theoretical terms, discusses important criticisms and refinements of this distinction, and investigates two problems concerning the semantics of theoretical terms. Finally, the major formal accounts of the semantics are expounded. Two criteria of theoreticity: reference to non-observable entities and properties. As just explained, a theoretical term may simply be understood as an expression that refers to non-observable entities or properties. Theoreticity in this understanding is the negation of observability. This explanation of theoreticity thus rests on an antecedent understanding of observability. What makes an entity or property observable? As Carnap has pointed out, a philosopher understands the notion of observability in a narrower sense than a physicist. For a philosopher, a property is observable if it can be directly perceived by the senses. Hence, such properties as blue, hard, or colder than are paradigmatic examples of observable properties in the philosopher's understanding of observability. The physicist, by contrast, would also count quantitative magnitudes that can be measured in a relatively simple, direct way as observable. Hence, the physicist views such quantities as temperature, pressure, and intensity of electrical current as observable. The notion of direct perception is spelled out by Carnap by two conditions. Direct perception means, first, perception unaided by technical instruments, and second, that the perception is unaided by inference. These two conditions are obviously not satisfied for the measurement of quantities like temperature and pressure. For the philosopher, only spatial positions of liquids and pointers are observed when these quantities are measured. To an even higher degree, we are unable to observe electrons, molecules, gravitational forces, and genes on this narrow understanding of observability. Hence, expressions referring to such entities qualify as theoretical. In sum, a property or object is observable in the philosopher's sense if it can be perceived directly, where directness of observation excludes the use of technical artifacts and inferences. Notably, Carnap admits that this explanation of the distinction is not sufficiently precise to determine a sharp line between observational and theoretical terms. He rather views the theory observation distinction as being introduced into a continuum of degrees of observability by choice. Semantic dependence upon a scientific theory. Oh, sorry, I forgot to redo the screen share. Sorry about that. Just see here the table of contents. The above explanation of theoreticity may be felt unsatisfactory as it determines the property of being theoretically only via negation of the property of being observable. This explanation does not indicate any specific connection between the semantics of theoretical terms and corresponding scientific theories. There is, however, also a direct characterization of theoreticity that complements the criterion of non-observability as expressions in theoretical if and only if its meaning is determined through the axioms of a scientific theory. This explanation rests on what has become to be referred to as the contextual theory of meaning, which says that the meaning of a scientific term depends in some way or other on how this term is incorporated into a scientific theory. Why adopt the contextual theory of meaning for scientific terms? Suppose the notion of meaning is understood along the lines of a Fregean notion of sense. The sense of a term be understood as that what determines its reference. It is furthermore a reasonable requirement that a semantic theory must account for our understanding of the sense and hence our methods for determining the extension of scientific terms. For a large amount of scientific terms, these methods rest upon axioms of one or more scientific theories. There's no way of determining the force function in classical mechanics without using some axiom of this theory. Familiar methods make use of Newton's second law of motion, Hooke's law, the law of gravitation. Likewise, virtually all methods of measuring temperature rest upon laws of thermodynamics. Take measurements by a gas thermometer, which is based on the ideal gas law. The laws of scientific theories are thus essential to our understanding of determining the extension of scientific terms. The contextual theory of meaning, therefore, makes intelligible how students in scientific discipline and scientists grasp the meaning or sense of scientific terms. On this account, understanding the sense of a term means knowing how to determine its reference or extension, at least in part. The contextual theory of meaning can be traced back at least to the work of Duhem. His demonstration that a scientific hypothesis in physics cannot be tested in isolation from its theoretical context is joined with and motivated by semantic considerations, according to which it is physical theories that give meaning to the specific concepts of physics. Poincare literally claims that certain scientific propositions acquire meaning only by virtue of the adoption of certain conventions. Perhaps the most prominent and explicit formulation of the contextual theory of meaning is to be found in Feyerabend's landmark explanation, reduction, and empiricism. For just as the meaning of a term is not an intrinsic property but is dependent upon the way in which the term has been incorporated into a theory, in the very same manner, the content of a whole theory, and thereby again the meaning of the descriptive terms which it contains, depends upon the way in which it is incorporated into both the set of its empirical consequences and the set of all alternatives which are being discussed at a given time. Once the contextual theory of meaning has been adopted, there is no reason to confine its application to a single theory, especially as the boundaries of such language or of such a theory are almost never well defined. The accounts of contextual theory of meaning in the works of Duhem, Poincare, and Feyerabend are informal insofar as they do not crystallize into a corresponding formal semantics for scientific terms. The view that meaning is bestowed upon a theoretical term through the axioms of scientific theory implies that only axiomatized or axiomatizable scientific theories contain theoretical terms. In fact, all formal accounts of the semantics of theoretical terms are devised to apply to axiomated scientific theories. This is due in part to the fact that physics has dominated the philosophy of science for a long time. The majority of general propositions in scientific theories other than those of physics, however, have instances that fail to be true. Criticism and refinements of the theory observation distinction. Criticisms. The very idea that clear-cut theory observation distinction has received much criticism. First, with the help of sophisticated instruments such as telescopes and electron microscopes, we're able to observe more and more entities which had to be considered unobservable at a previous stage of scientific and technical evolution. Second, assume observability is understood as excluding the use of instruments. On this understanding, which are reduced to criticizing the theory observation distinction, can be dealt with. However, we would then have to conclude that things being perceived with glasses are not observed either, which is counterintuitive. Third, there are concepts applying to or being thought to apply to both macroscopic and submicroscopic particles. Hence, there are clear-cut instances of observation concepts that apply to unobservable entities, which does not seem acceptable. These objections to the theory observation distinction can be answered in a relatively straightforward manner from a Carnapian perspective. Carnap was quite explicit that the philosopher's sense of observation excludes the use of instrument. In fact, Carnap's most explicit explanation of observability defines this notion in such a way that it is relativized to an organism. Recall, moreover, that Carnap's theory observation distinction was not intended to do justice to our overall understanding of these notions, hence certain quotidian and scientific uses of observation, such as observation using glasses, may well be disregarded when this distinction is drawn, as long as the distinction promises to be fruitful in the logical analysis of scientific theories. Closed look reveals that Carnap agrees with critics of the logical empiricist agenda, such as Maxwell and Achenstein in 1965, on there being no clear-cut theory observation distinction. There's no question here of who is using the term observable in the right or proper way. There's a continuum which starts with direct sensory observation and proceeds to enormously complex indirect methods of observation. Obviously, no sharp line can be drawn across this continuum. It is a matter of degree. A bit more serious is Putnam's 1962 objection, drawing upon the application of apparently clear-cut instances and observation concepts to submicroscopic particles. Here, Carnap would have to distinguish between color concepts applying to observable entities and related color concepts applying to unobservable ones. So the formal language in which the logical analysis proceeds would have to contain a predicate red applying to a macroscopic object and another one red applying to a submicroscopic one. Again, such a move would be in line with the artificial or ideal language philosophy that Carnap advocated. There's another group of criticism coming from the careful study of the history of science. Hansen, 1958, Feyerabend, 1962, and Kuhn aim to show that the observation concepts are theory-laden in a manner that makes their meaning theory dependent. Feyerabend, for example, held that all terms are theoretical. Hansen thinks that Tycho and Kepler were literally seeing different things when perceiving the sun rising because their astronomical background theories were different. Kuhn was more tentative when expounding his theory of theory-ladenness of observation. In a discussion of the Sneed formalism of the structure of the school, he favored a theory observation distinction that is revitalized, relativized, first to a theory and second to the application of the theory. Virtually all formal accounts of theoretical terms, in fact, assume that those phenomena which a theory is meant to account for can be described in terms of expressions whose meaning does not depend on the theory. The counterthesis to this meaning of putative observation terms depends on a quotidian or scientific theory, therefore attacks on a core doctrine of the logical empiricists and subsequent work on theoretical terms. Refinements. There is a simple, intuitive, and influential proposal on how to relativize the theory observation distinction in a sensible way. The term T is theoretical with respect to a theory, or for sure a T term if and only if it is introduced by a theory T at a certain stage in the history of science. O terms, by contrast, are those that were antecedently available and understood before T was set forth. This proposal draws on the theory observation distinction in an apparently sharp way by means of relativizing the distinction to a particular theory. Needless to say, the proposal is in line with the contextual theory of meaning. The distinction between T terms and antecedently available O terms has two particular merits. First, it circumvents the view that any sharp line between theoretical and observational terms is conventional and arbitrary. Second, it connects the theory observation distinction with what seemed to have motivated that distinction in the first place, an investigation of how we came to understand the meaning of terms that appear to be meaningful in virtue of certain scientific theories. A similar proposal of a relativized theory observation distinction was made by Sneed in his seminal The Logical Structure of Mathematical Physics. The original exposition of the theoreticity criterion by Sneed in 1979 is a bit more involved as it makes use of a set theoretical predicates and intended applications, rather technical notions of the structuralist approach to scientific theories. There has been a lively discussion, mainly but not exclusively within the structuralist school, how to express the relativized notion of theoreticity most properly. As noted above, Kuhn proposed a twofold revitalization of theoreticity. First, to a scientific theory, and second, to applications of such theory. Notably, Steed's criterion of theoreticity suggests a strategy that allows us to regain a global, non-relativized theory observation distinction. Simply take a term T to be the theoretical if and only if it holds for all methods of determining an extension. That method rests upon some axiom of some theory. A term is not theoretical or observational if and only if there are means for determining its extension, at least in part, that do not rest upon any axiom of any theory. The criterion is still relative to our present stage of explicit theories, but comes closer to the original intentionally Carnap's theory observation distinction, according to which observation is understood in the narrow sense of unaided perception. Two problems of theoretical terms. The problem of theoretical terms is a recurrent theme of the philosophy of science literature. Different shades of meaning have been associated with this problem. It is in a most comprehensive formulation. The problem of theoretical terms is to given a proper account of the meaning of reference to theoretical terms. There are at least two kinds of expressions that pose a distinct problem with theoretical terms, respectively. First, unitary predicates referring to theoretical entities such as electron, neutrino, or nucleotide. Second, non-unitary theoretical predicates such as homology in evolutionary biology and theoretical function expressions such as force, temperature, and intensity of the electromagnetic field in physics. Sneed's problem of theoretical terms concerns only the latter kind of expression. We shall now start surveying problems concerning the semantics of expressions for theoretical entities and then move on to expressions for theoretical relations and functions. Theoretical entities. A proper semantics for theoretical terms involves an account of reference and one of meaning and understanding. Reference fixing needs to be related to meaning as we want to answer the following question: how do we come to refer successfully to theoretical terms? This question calls for different answers depending on what particular conception of theoretical entity is adopted. The issue of realism and its alternatives, therefore, comes into play at this point. For the realist, theoretical entities exist independently of our theories about the world. Also, natural kinds that classify these entities exist independently of our theories. The instrumentalist picture is commonly reported to account for theoretical entities in terms of mere fictions. The formalist variant of instrumentalism denies that theoretical terms have reference in the first place because these two extreme cases there is a number of intermediate positions. Carnap attempted to attain a metaphysically neutral position as to avoid any commitment to or denial of scientific realism. In his account of the theoretical language of science, theoretical entities were conceived as mathematical entities that are related to unobservable events in certain determinate ways. An electron, for example, figures as a certain distribution of charge and mass in four-dimensional manifold of real numbers, where charge and mass are real valued functions. These functions are the four-dimensional manifold itself, are to be related to observable events by means of universal axioms. Notably, Carnap would not have accepted the characterization of his view as anti-realist or non-realist, since he thought that metaphysical doctrine of realism to be void of content. There are thus different metaphysical views of theoretical entities in science, each with its consistent with the understanding that a theoretical entity is inaccessible by means of unaided perception. First, theoretical entities are mind and language independent. Second, theoretical entities are mind and language dependent in some way or another. Third, they are conceived of as mathematical entities that are related to the observable world in certain determinate ways. We may distinguish between the first, the realist view, second, a collection of non-realist views, and three, a Pythagorean view of theoretical entities. Now, there are three major accounts of reference and meaning that have been used implicitly or explicitly for the semantics of theoretical terms: the descriptive picture, causal and causal historical theories, and hybrid ones that combine descriptivist ideals with causal elements. Accounts of reference and meaning other than these played no significant role in the philosophy of science. Hence, we need to survey the last 9 combinations, consisting first of an abstract characterization of the nature of theoretical entities, realist, non-realist, and Pythagorean, and second, particular count of the reference descriptivist, causal, and hybrid. Some of these combinations are plainly inconsistent and hence can be dealt with very briefly. Let us start with the realist view of theoretical entities. The realist view. The descriptivist picture is highly intuitive with regard to our understanding of expressions referring to theoretical entities on the realist view. The descriptivist explanation of meaning and reference makes use of theoretical terms, functions. The semantics of theoretical entities, therefore, is connected with the semantics of theoretical relations and functions. It seems to hold in general that the theoretical entities in the sciences are to be characterized in terms of theoretical functions and relations. The descriptivist account, however, faces two particular problems with regards to the historic evolution of scientific theories. First, it's if descriptions of theoretical entities are constitutive of the meaning of corresponding unary predicates, one must wonder what the common core of understanding is that adherents of successive theories share and whether there is such a core at all. Issues of incommensurability arise when the descriptivist picture with the descriptivist picture. A second problem arises with when elements of the description of an entity in a given theory are judged wrong from the viewpoint of the successor theory. Then, on a strict reading of a descriptivist account, the corresponding theoretical terms fail to refer in the given theory. For if there is nothing that satisfies the description, the corresponding expression has no referent. This is a simple consequence of the theory of description by Russell in his famous On Denoting in 1905. Hence, an account of the weighting descriptions is needed in order to circumvent such failures of reference. As is well known, Kripke in 1980 set forth a causal historical account of reference as an alternative to the descriptivist picture. This account begins with an initial baptism that introduces a name and goes on with causal chains transmitting the reference of the name from speaker to speaker. In this picture, Aristotle is the man once baptized, so he might not have been the student of Plato or done any other things commonly attributed to him. Kripke thought this picture to apply both to proper names and general terms. It is hardly indicated, however, how this picture works for expressions referring to theoretical entities. Kripke's story is particularly counterintuitive in the view of the ahistorical manner of teaching in the natural sciences. Their up-to-date textbooks and recent journal articles are more important than the original historical introductions of a theoretical term. The Kripkean causal story may also be read as an account of reference fixing without being read as the story of grasping the meaning of theoretical terms. Reference, however, needs to be related to meaning so as to ensure that scientists know what they're talking about and are able to identify the entities under investigation. Notably, even for expressions of everyday language, the charge of not explaining meaning has been leveled against Kripke's causal historical account. The same charge applies to Putnam's 1975 causal account of reference and meaning, which Putnam himself abandoned in 1980. A purely causal or causal historical account of reference does not seem a viable option for theoretical terms. More promising are hybrid accounts that combine descriptivist intuitions with causal elements, such as accounts has been given by Psilos. A term T refers to an entity X if and only if X satisfies the core causal descriptions associated with T. The two terms T prime and T denote the same entity if and only if their putative reference play the same causal role with respect to a network of phenomenon, and the core causal description of T prime takes up the kind constitutive properties of the core causal description associated with T. The account has two particular merits. First, it is much closer to the way scientists understand and use theoretical terms than purely causal accounts. Because of this, it is not only an account of reference, but also one of meaning for theoretical terms. In purely causal accounts, by contrast, there is a tendency to abandon the notion of meaning altogether. Second, it promises to ensure a more stable notion of reference that is purely descriptivist account of reference and meaning. Notably, the kind of causation that Psilo's hybrid account refers to is different than the causal historical chains that Kripke thought responsible for the transmission of reference among speakers. No further explanation, however, is given of what kind of constitutive property is and how we are to recognize such a property. Psilos merely infers the existence of such properties from the assumption of there being natural kinds. Non-realist views. Non-realist and anti-realist semantics for theoretical terms are motivated by the presumption that the problem of theoretical terms has no satisfying realist solution. What does the non-realist semantics of theoretical terms look like? The view that theoretical entities are mere fictions often figures in realist portraits of anti-realism. This view is hardly seriously maintained by any philosopher of science in the 20th century. If one were to devise a formal or informal semantics for the view that theoretical entities are mere fictions, a purely descriptive account seems most promising. Such an account could, in particular, make heavy use of the Fregean notion of sense. Formalist variants of instrumentalism are a more serious alternative to realist semantics than the fiction view of theoretical entities. Formalist views in the philosophy of mathematics aim to account for mathematical concepts and objects in terms of syntactic entities and operations thereupon within a calculus. Such views have been carried out over to theoretical concepts and objects in the natural science, with the qualification that the observational part of the calculus is interpreted in such a way that the symbols refer to physical and phenomenal objects. Cognitive access to theoretical entities is thus explained in terms of our cognitive access to the symbols and rules of the calculus in the context of the antecedent understanding of the observational terms. Formalist ideas were sympathetically entertained by Hermann Weyl. 1949, he was driven towards such ideals by the adherence of Hilbert's distinction between real and ideal elements and the corresponding distinction between real and ideal propositions. Propositions of observational language were construed as real in the sense of the Hilbertian distinction, while the theoretical propositions are construed as ideal. The content of the ideal proposition is understood in terms of the syntactic consistency of the whole system, consisting of the ideal and real propositions being asserted. The Pythagorean view. There remains to discuss the view that theoretical entities are mathematical entities which are related to observable entities in certain determinate ways. The theory is clearly of the descriptivist type, as we shall see more clearly when dealing with the formal account by Carnap. No causal elements are needed in Carnap's Pythagorean empiricism. The Pythagorean view shifts the problem of theoretical terms to the theory of meaning and reference for mathematical expressions. The question of how we're able to refer successfully to electrons is answered by the Pythagorean by pointing out that we are able to refer successfully to mathematical entities. Moreover, the Pythagorean explains it is part of the notion of an electron that corresponding mathematical entities are connected to observable phenomena by means of axioms and inference rules. The empirical surplus of theoretical entities in comparison to pure mathematical entities is thus captured by axioms and inference rules that establish connections to empirical phenomena. Since mathematical entities do not by themselves have connections to observable phenomenon, the questions of truth and falsehood may not be put in truth conditional manner for those axioms that connect mathematical entities with phenomenal events. Carnap therefore came to speak of postulates when referring to axioms of a scientific theory. How do we come to refer successfully to mathematical entities? This, of course, is a problem in the philosophy of mathematics. Carnap has not much to say about the meaning of reference of mathematical expression in seminal The Methodological Character of Theoretical Concepts in 1956, but discusses these issues in the Empiricism, Semantics, and Ontology in 1950. There he aims at establishing a metaphysically neutral position that avoids a commitment to Platonism, nominalism, or formalist conceptions of mathematical objects. A proponent of a Pythagorean view other than Carnap is Hermann Weyl, 1949. As for the cognition of mathematical entities, Weyl largely follows Hilbert's formalism in his later work. Hence, there is a non-empty intersection between the Pythagorean view and the formalist view of theoretical entities. Unlike Carnap, Weyl did not characterize the interpretation of theoretical terms by means of model theoretical notions. Theoretical functions and relations. For theoretical functions and relations, a particular problem arises from the idea that a theoretical term is by definition semantically dependent upon a scientific theory. Let us recall the above explanation of theoreticity. A term T is T theoretical if and only if any method of determining the extension of T or some part of that extension rests upon some axiom of T. Let phi be an axiom and m be a corresponding method of determination. The present explanation of T theoreticity then means that m is valid only on condition that phi being true. The latter dependency holds because phi is used either explicitly in calculations to determine t or in the calibration of the measurement devices. Such devices then perform the calculation implicitly. Suppose now that t is a theoretical with respect to a theory t, then it holds that in order to measure t, we need to assume the truth of some axiom of t. Suppose further that t has occurrences in the axiom as is standard in examples of t theoreticity. From this, it follows that in standard truth conditional semantics, the truth value of the axiom is dependent on the semantic value of the term. This leads to the following epistemological problem. On the one hand, we need to know the extension of the term in order to find out whether the axiom is true. On the other hand, it is simply impossible to determine the extension of the term without using the axiom or some other axiom of the theory. This mutual dependency between the semantic values of the axiom and the terms makes it difficult, if not impossible, to have evidence for the axiom being true in any of its applications. We could, of course, use an alternative measurement, a method of the term, say, resting upon another axiom of the theory to gain evidence of the axiom being true in some selected term. This move, however, only shifts the problem of application of another axiom of the theory. For these applications, the same applies of same type of difficulty arises, mutual dependency on the semantic values of the axioms and terms. We are thus caught either in a vicious circle of or an infinite regress when attempting to gain evidence for the property of a single measurement of a theoretical term. Sneed was the first to describe that particular difficulty in the present manner and termed it the problem of theoretical terms. Measurement of the force, function, in classical mechanics exemplifies the problem well. There's no method of measuring force that does not rest upon some law of classical mechanics. Likewise, it is possible to measure temperature without using some law that depends upon either phenomenological or statistical thermodynamics. Although this formulation is primarily epistemological, Sneed's problem with theoretical terms has a semantic reading. Let the meaning of a term be identified with the methods of determining its extension. Then we can say that our understanding of T theoretical relations and functions originates from the axioms of a scientific theory. In standard truth conditional semantics, by contrast, one assumes that the truth value of an axiom is determined by the semantic values of those descriptive symbols which have occurrences in the axiom. Among these symbols, there are the theoretical terms of the theory. Hence, it appears that standard truth conditional semantics does not accord with the order of our grasping of the meaning of theoretical terms. In the next section, we will deal with the indirect means of interpreting theoretical terms. These prove to be ways out of the present problem of theoretical terms. Formal accounts. A few notational conventions and preliminary considerations are necessary to explain the formal accounts of theoretical terms. Essential to all these accounts is the division of a set of descriptive symbols into a set of observational and another set of theoretical terms. The descriptive symbols of a formal language are simply the non-logical ones. A scientific theory thus can be formulated to be a language including the observation and theoretical terms. The division of the descriptive vocabulary gives rise to a related distinction between T and C axioms among the axioms of a scientific theory. The T axioms contain only the theoretical term symbols as descriptive ones, while the C axioms contain both the observational and theoretical symbols. The latter axioms establish a connection between the theoretical and observational terms. Ramsey assumes that there is but one domain of interpretation for all descriptive symbols. Carnap, by contrast, distinguishes between a domain of interpretation in observational terms and another for theoretical terms. Notably, the latter domain contains exclusively mathematical entities. Ketland, 2004, has emphasized the importance of distinguishing between an observational and theoretical domain of interpretation. TC is a first-order sentence in Ramsey's seminal article Theories, 1921. Carnap, in 1956, however, works with higher-order logic to allow for the formulation of mathematical propositions and concepts. The Ramsey sentence. The Ramsey sentence of a theory TC in the language of VOVT is obtained by the following two transformations of the conjunction of T and C axioms. First, replace all the theoretical symbols in the conjunction by higher order variables of appropriate type. Second, bind these variables by higher order existential qualifiers. This sentence says that there is an existential interpretation of the theoretical terms that verifies together with an antecedently given interpretation of the observational language, the axioms TC. The Ramsey sentence expresses an apparently weaker proposition than TC, at least in standard truth conditional semantics. If one thinks that the Ramsey sentence expression expresses the production of a scientific theory more properly than TC, one holds that Ramsey's view of scientific theories. Why should one prefer the Ramsey view to the standard one? Ramsey himself seemed to have a contextual theory of meaning in mind when proposing the replacement of theoretical terms with appropriate higher order variables. Any addition to the theory, whether in the form of new axioms or particular assertions, are to be made within the scope of the original axioms. They are not therefore strictly propositional by themselves, just as the different sentences in story beginning once upon a time have not complete meanings, and so are not propositions by themselves. Axioms figure in this explanation as theoretical terms to be replaced by higher order variables. One difficult, however, remains with the Ramsey view. It concerns the representation of deductive reason. For many logicians, the primary objective of logic. Now Ramsey thinks that the incompleteness of theoretical assertions does not affect our reasoning. No formal account, however, is given that relates our deductive practices in which abundant use of theoretical terms is made to the existential quantified variables in the Ramsey sentence. We lack a translation of theoretical sentences other than axioms. Such a translation would not obey the laws of classical logic. These laws, however, are supposed to govern deductive reasoning in science. A proper semantics of theoretical terms should take the semantic peculiarities of these two terms into account without revising the rules of deductive reasoning in classical logic. There thus remains the challenge of relating the apparent use of theoretical terms in deductive scientific reasoning to the Ramsey formulations of scientific theories. Carnap was well aware of this challenge and addressed it using a sentence that became labeled later on the Carnap sentence of a scientific theory. The sentence is part of a proposal that draws analytic synthetic distinction at the global level of a scientific theory, as this distinction proved not to be applicable to single axioms. From the viewpoint of standard truth conditional semantics, however, this instruction to interpret the Carnap sentence appears arbitrary, if not even misguided. Indirect interpretation. The notion of indirect interpretation was introduced by Carnap in his Foundations of Logic and Mathematics, 1939, with the intention of accounting for the semantics of theoretical terms in physics. It goes without saying that this notion is understood against the background of the notion of direct interpretation. Carnap had the following distinction in mind. The interpretation of descriptive symbol is direct if and only if it is given by an assignment of an extension or an intention, and this assignment is made by expressions of the meta-language. The interpretation of a descriptive symbol is indirect by contrast if and only if it is specified by one of the several sentences of the object language, which then figure as axioms in the respective calculus. Here are two simple examples of a direct interpretation. R designates the property of being rational. A designates the property of being an animal. The predicate H, by contrast, is interpreted by an indirect manner by a definition in the object language. Interpretation of a symbol, by definition, counts as one type of indirect interpretation. Another type of interpretation of theoretical terms by axioms of a scientific theory. Carnap remains content with a merely syntactic explanation of indirect interpretation. The calculus is first constructed floating in the air, so to speak. The construction begins at the top and then adds lower and lower levels. Finally, by the semantic rules, the lowest level is anchored at the solid ground of the observable facts. The laws, whether general or specific, are not directly interpreted, but only the singular sentences. This account amounts to the formalist understanding of the theoretical language in science. It has two particular merits. First, it circumvents Snead's problem of theoretical terms, since the axioms are not required to be true in the interpretation of the respective language that represents the facts of the theory-independent world. The need for assuming such interpretation is simply denied. Second, the account is in line with the contextual theory meaning for theoretical terms, as our understanding of such terms is explained in terms of the axioms of the respective scientific theories. There are less formalist accounts of indirect interpretation in terms of the explicit model theoretical notions by Przylecki and Andreas in 2010. The latter account is based on the ideas about theoretical terms in Carnap 1958. It emerged from an investigation into the similarities and dissimilarities between Carnapian postulates and definitions. Recall that Carnap viewed the axioms of a scientific theory and postulates since they contribute to the interpretation of theoretical terms. When explaining the Carnap sentence, Carnap says that if the Ramsey sentence is true, the theoretical terms are to be understood in accordance with some interpretation that satisfies TC. This is the sense in which we can say that the Carnapian postulates contribute to the interpretation of theoretical terms in a manner akin to the interpretation of a defined term by the corresponding definition. Postulates and definitions alike impose a constraint on the admissible or intended interpretation of the complete language, where it contains basic and indirectly interpreted terms. Yet the interpretation of theoretical terms by axioms of a scientific theory differs in several ways from that of a defined term by a definition. First, the introduction of theoretical terms may be joined by the introduction of another theoretical domain of interpretation, in addition to the basic domain of interpretation in which observational terms are interpreted. Second, it must be assumed that the interpretation of theoretical terms results in a unique determination of the extension of those terms. This is an implication of Carnap's doctrine of partial interpretations, as will become obvious by the end of the section. Third, axioms of a scientific theory are not conservative extensions of the observational language since they enable us to make predictions. Definitions, by contrast, must be conservative. Consequently, Andreas, 2018, generalized that the present semantics, so as to capture scientific reasoning, is a paraconsistent setting. The proposal is based on a preferred model semantic satisfaction of a theory, and agreement with the empirical data comes in degrees. Some interpretations score better than others. The idea leads to a strict partial order of interpretations, and we understand the theoretical terms in such a manner that the set of instances of all the axioms is satisfied to a maximal extent in the context of a given interpretation of the observational terms. This proposal parallels certain adaptive logics developed by Betens and Mahus. Notably, it allows us to capture scientific reasoning with the Ceteris Paribus laws that hold true most of the time but have exceptions. This could be helpful for the analysis of theoretical terms in scientific disciplines other than physics. Relatively little research has been done on the semantics of theoretical terms and theories from scientific disciplines other than physics. It has remained an open question whether or not formal semantics that were primarily developed to capture theories in physics are applicable to theories in biology, chemistry, psychology, and economics. For a structuralist framework by Balzar, it could be shown that such applications are feasible. Rockefeller and McClellan studied theoretical terms in psychology, albeit without explicit considerations of their formal semantics. Direct interpretation. Both the Ramsey view and the indirect interpretation semantics deviate from the standard truth conditional semantics at the level of theoretical terms and theoretical sentences. Such a deviation, however, was not felt to be necessary by all philosophers that have worked on theoretical concepts. Tumiela defends a position he calls semantic realism, and that retains standard truth conditional semantics. Hence, direct interpretation is assumed for theoretical terms by Tuomela. Yet semantic realism for theoretical terms acknowledges there to be an epistemological distinction between observational and theoretical terms. Tuomela's criterion of theory observation distinction largely coincides with Steed's above expounded criterion defining theoretical terms. And while Carnap and Feyerabend and a number of other writings, we find different formulations of the idea that axioms of a scientific theory determine the meaning of theoretical terms without these axioms qualifying as a proper definition of theoretical terms. Lewis, however, wrote a paper with the title How to Define Theoretical Terms, 1970. A closer look at the literature reveals that the very idea of explicitly defining theoretical terms goes back to Carnap's 1961 use of Hilbert's epsilon operator in scientific theories. This operator is an indefinite description operator that was introduced by Hilbert to designate some object X that satisfies an open formula epsilon. Lewis in 1970 introduced a number of modifications concerning both the language of Carnap sentences and its interpretation in order to attain proper definitions of theoretical terms. First, theoretical terms are considered to refer to individuals as opposed to the relations and functions. This move is made coherent by allowing the basic language to contain relations like X has a property Y. The basic non-theoretical language is thus no observational language in this account, yet it serves as a basis for introducing theoretical terms. The set of V of O terms is best described as our antecedently understood vocabulary. Second, denotationalist terms are dealt with along the lines of free logic by Dana Scott, 1967. An improper description, for example, denotes nothing in the domain of discourse. Atomic sentences containing denotationalist terms are either true or false. An identity statement that contains a denotationalist term on both sides is always true. If just one side of an identity formula has an occurrence of a denotationalist term, the identity statement is false. Third, Lewis insists on a unique interpretation of theoretical terms, thus rejecting Carnap's doctrine of partial interpretation. Carnap is most explicit about the indeterminacy that this doctrine implies. This indeterminacy of theoretical terms drives Carnap to use Hilbert's epsilon operator there, as just explained. For Lewis, by contrast, a theoretical term is denotationalist if its interpretation is not uniquely determined by the Ramsey sentence. For a scientific theory to be true, it must have a unique interpretation. Using these modifications, Lewis transformed the Carnap sentence into three Carnap-Lewis postulates. A few further properties of Lewis's definition of theoretical terms are noteworthy. First, they specify the interpretation of theoretical terms uniquely. This property is obvious for the case of unique realizations of TC, but holds as well for other cases since the assignment of no denotation counts as an interpretation of a descriptive symbol in free logic. Second, it can be shown that these definitions do not allow for the derivation of any language sentences except logical truths, just as the original Carnap sentences did. Lewis, therefore, in fact succeeds at defining theoretical terms. He does so without attempting to divide the axioms into definitions and synthetic claims about the spatio-temporal world. The replacement of theoretical relations and function symbols with individual terms was judged counterintuitive by Papineau, 1996. The reformulations, however, of Lewis's definitions using second higher order variables is not difficult to accomplish, as Schurz in 2005 has shown. In this reformulation, the problem arises that theoretical terms are usually not uniquely interpreted, since our observational evidence is most of the time insufficient to determine the extension of theoretical relations and function symbols completely. Theoretical functions such as temperature, pressure, electromagnetic force, etc., are determined only for objects that have been subjected to appropriate measurements. However, indirect in view of this problem, Schurz suggests that the higher order quantifiers range only over those extensions that correspond to natural kind properties. This restriction renders the requirement of unique interpretation of theoretical terms plausible once again. Such a reading was also suggested by Psilos with references to Lewis' 1984 discussion of Putnam's 1980 model theoretic argument. In this paper, Lewis himself suggests that the restriction of the interpretation of descriptive symbols to extensions corresponding to natural kind properties. One final note on indirect interpretation is in order. Both Carnap and Lewis interpret theoretical terms indirectly simply because any definition is an instance of indirect interpretation. For this reason, Snead's problem of theoretical terms does not arise. Yet the problem of Carnap's and Lewis's proposals conforms to a pattern of definition in the narrow sense and not to the peculiar pattern of indirect interpretation that Carnap in 1939 envisioned for the interpretation of theoretical terms. This is why the indirect interpretation semantics has been separated from the present discussion of defining theoretical terms. Conclusion. The idea that there are scientific terms whose meaning is determined by scientific theory goes back to Duhem and Poincare. Such terms came to be referred to as theoretical terms in the 20th century philosophy of science. Properties and entities that are observable in the sense of direct unaided perception did not seem to depend on scientific theories as forces, electrons, and nucleotides did. Hence, philosophers of science and logicians set out to investigate the semantics of theoretical terms. Various formal accounts resulted from these investigations, among which the Ramsey sentence by Ramsey, Carnap's notation notion of indirect interpretation and Lewis's proposal of defining theoretical terms are the most prominent ones. Though not all philosophers of science understand the notion of theoretical terms in such a way that semantic dependence upon a scientific theory is essential, this view prevails in the literature. The theory-observation distinction has been attacked heavily and is presumably discredited by a large number of philosophers of science. Still, the distinction continues to permeate a number of important strands in the philosophy of science, such as scientific realism and its alternatives in the logical analysis of scientific theories. A case in point was the recent interest in the Ramsey account of scientific theories, which emerged in the wake of Worrell's structural realism. We have seen, moreover, that formal accounts of theoretical terms works well with theory-observation distinction that is relativized to a particular theory. Critics of the distinction, by contrast, have commonly attacked a global and static division into theoretical and observational terms. Note finally that Carnap assigned no ontological significance to the theory-observation distinction in the sense that entities of one type would be existent in a more genuine way than ones of the other. Okay, yeah, a lot of material there. Tinkle, yeah, God bless. So, yeah, let's keep at it and think about this a little bit more. A lot of important information. So I have two more to go over, and these are pretty technical. So I think I'm going to skip a lot more of it than I planned. So I had intended to read, way more of this than I think I'm actually going to. So let's do the Ceteris Paribus laws. And there's a lot of logic. Like, say, when it really gets down to understanding this, it's symbolic in nature. It's like, what is logic? What is metaphysics? What is science? And it's not narrative, although you have pragmatic theories or there is a narrative part. It's basically going to be reduced to a logical structure in symbolic form. So to some extent, that's beyond the scope of what I'm capable of doing here. So I'm just going to read more of the narrative part, and I'm going to have to skip the technical part because it's just too much. Ceteris Paribus laws. Laws of nature take a center stage in philosophy of science and metaphysics. Laws are usually believed to stand in tight relations to many philosophical key concepts as causation, explanation, confirmation, determinism, and counterfactuals. Traditionally, philosophers have focused on physical laws, which were taken to be at least true universal statements that support counterfactual claims. But although this claim about laws might be true with respect to physical laws, laws in the special sciences appear to have, maybe not surprisingly, different features than the laws of physics. Special science laws are usually taken to have exceptions, to be non-universal, or to be ceteris paribus laws. How and whether the laws of physics and the laws of the special sciences differ is one of the crucial questions motivating the debate on the ceteris paribus laws. Another major controversial question concerns the determination of the precise meaning of ceteris paribus. Philosophers have attempted to explicate the meaning of ceteris paribus clauses in different ways. The question of meaning is connected to the problem of empirical content. The question whether ceteris paribus laws have non-trivial and empirical testable content. Since many philosophers have argued that ceteris paribus laws lack empirically testable content, this problem constitutes a major challenge to a theory of ceteris paribus laws. So I went over this in depth multiple times. A lot of this is extremely complicated, a lot of logical, heavy notation, symbolic form, and I'm probably going to skip over most of that. People could read over that on their own. I highly recommend it. The multiple truth theory in some formulation will contain some of this symbolic logical format. Although, as we see, there's many, they get the Ramsey sentence, the Carnap sentence, Lewis, the Phrygian piano. There's many conventions of logical notation. and they all have problems and inconsistencies. And so it's a lot of work. That's why the multiple truth hypothesis is taking so long to put out. But hopefully the due diligence of reading through this will prove worthwhile. Introduction. Systematic introduction. In the philosophy of science and metaphysics, laws of nature take center stage. Many explanations of philosophical key components in philosophy of science essentially rely on laws of nature. For instance, the majority of theories of causation, explanation, confirmation, determinism, and counterfactuals presuppose laws of nature. Until the second half of the 20th century, certain characteristics of laws of nature were taken for granted by philosophers of science. Laws of nature were taken to be true, logically contingent, universal statements that support counterfactual claims. Laws were taken to play a major role in explanation, induction, confirmation, causation, and in counterfactual reasoning. The paradigm case for such laws were taken from fundamental physics. Newton's second law, or the Schrödinger equation, fit the bill of the traditional concept of the law of nature. Philosophers of science were aware of the fact that there are hardly any universal laws of this kind. Biology, psychology, economics, or other special sciences. This posed no problem as long as there was a consensus that this might be conceived as a shortcoming of the special sciences. However, with the success, especially of the biological sciences, it became clear that there is a genuine scientific knowledge that does not conform to the paradigm of physics. As a consequence, scientific practice in the special sciences was no longer taken to be deficient, but was analyzed as a legitimate practice different from physics. The generalizations of the special sciences, including biology, psychology, and economics, seem to differ in important ways from the generalizations of fundamental physics. All of the generalizations are non-universal, that is, they are actual and merely possible situations in which the above generalizations do not hold, although all the conditions obtained that are explicitly stated in the antecedents of these generalizations. However, even though the generalizations are not universal, they do play a role in explanations and predictions. They may be used for purposes of manipulation, and they support counterfactuals. The question arises how to deal with this situation. Are these generalizations to be classified as laws, laws that pertain only to special conditions, Ceteris Paribus laws, or are they something entirely different? Given the fact that the laws play a major role in most accounts of explanation, causation, there seems to be basically three options. These generalizations do not qualify as laws because they are not universal. Therefore, there are no genuine explanations in those areas of science that rely on these generalizations, most notably the special sciences. These generalizations do not qualify as laws because they're not universal. However, explanation, causation do not presuppose the existence of universal laws. These generalizations do not qualify as laws, despite the fact that they are not universal, because they have important features in common with universal laws, most importantly, the support of counterfactuals. The difference between the second and third may be to some extent merely terminological. Woodward and Hitchcock, for example, replaced laws with invariant generalizations, but admit that their account may be read as reconceptualization of lawhood. The motivation of those who take the third option and stick to the concept of laws is that the generalizations cited above have high enough in common with Newton's first law or the Schrödinger equation to classify them as laws. For instance, they play the same kind of role in explanation, prediction, and they support counterfactuals. There are two beneficial consequences of this particular approach. First, against the first option, it need not be denied that there are genuine explanations in the special science. Second, against the second option, in analogy to the traditional view, the concept of law, albeit of non-universal or Ceteris Paribus laws, can be used in explanations of notions such as explanation and causation. The main problem for those who choose the third option is that they have to spell out what is meant by non-universal law statement and how it can perform similarly explanatory and predictive tasks as a universal law. A convenient way to reconstruct the debate about the third option is to understand non-universal laws as statements that are qualified by a Ceteris Paribus henceforth clause. Yet, how to understand the meaning of the Ceteris Paribus CP clause is not an open question that is to be answered differently by various philosophers. Before we discuss the various accounts of CP laws, several issues surrounding the notion of Ceteris Paribus should be distinguished in order to structure the debate. How can different kinds of CP laws be distinguished and classified? Are there criteria to distinguish genuine CP laws from the strict laws? How and whether the laws of fundamental physics and the laws of the special sciences differ is one of the crucial questions driving the debate about Ceteris Paribus laws. Are there any genuine CP laws at all? Some authors deny that there are any genuine CP laws, while most of these authors agree that there are sentences that may be reconstructed as containing implicit CP clauses. They claim that these sentences lack clear meaning, cannot be tested, and therefore do not qualify as laws. However, if there are CP laws, further questions arises. In what disciplines do we find CP laws? Are the CP laws confined to the special sciences, or are the CP laws also in fundamental physics? What kind of CP laws are used in the sciences? It seems that in the literature, there are two very different kinds of situations are envisaged. On the one hand, several authors stress that CP laws describe the behavior of systems under ideal or abstract conditions. Such conditions are, if at all, only rarely realized. On the other hand, there are authors who claim that, at least in certain disciplines, CP conditions are nothing but normal conditions, or CP laws are laws expressing normality hypothesis. What are the truth conditions of CP law statements? Philosophers have attempted to determine the meaning of CP clauses in different ways. The question of meaning is connected to the problem of empirical content. The question whether CP laws have non-trivial and empirically testable content. Since many philosophers have argued that CP laws lack empirically testable content, this problem constitutes a major challenge to a theory of CP laws. Formally independent but methodologically related is the question under what conditions it is epistemologically legitimate to accept CP laws. Having distinguished these issues, it should be clear that the debate about CP clauses and CP laws does not exist. Instead, theories of CP engage in different and often separable enterprises. Overview. Section 2 gives, on the one hand, an account of the explicit use of CP clauses, mainly in the literature on economic issues from scholasticism to modern economics. On the other hand, we sketch two problems in the philosophy of science and philosophy of mind that explain why the CP laws have become an intensely discussed issue since the 1980s. Section 3 distinguishes between readings of the CP clause and a fortiori different kinds of CP laws. In Section 3.1, exclusive CP laws, factors not mentioned in the antecedent of the laws are assumed to be absent, are distinguished from comparative CP laws, factors not mentioned in the antecedent of the laws are assumed to be constant. In line with the bulk of the relevant literature, we focus on the exclusive CP laws. In Section 3.2, a distinction between definite and indefinite CP laws are presented. Section 4 presents the main challenge to the CP laws. It appears that many laws, like of the special sciences, if taken as strict laws, turn out to be false. However, if they are hedged by a CP clause, they appear to lack a clear meaning and appear to be empirically untestable. All of the major accounts of CP laws discussed in Section 5 to 8 are reactions to this challenge. Section 5 deals with the most influential early accounts of CP laws. They take the CP laws to be incomplete laws that can be completed, whereas Fodor, 1987, and others focus on special science CP laws that can be completed by adding factors to the antecedent of the law that are dealt with in more fundamental sciences. Petrosky and Ray, 1995, take CP laws to contain implicit promises. That is, when asserting a CP law, one promises to be able to cite factors that complete the law on a case-by-case basis if the consequent of the CP law does not obtain, although the antecedent does. In Section 5.2, we present several objections against such completer accounts. Section 6 presents two versions of stability theories of laws in the special sciences, namely Lang's stability theory in Section 6.1 and Woodward and Hitchcock's invariance theory in Section 6.2. The common general idea of invariance or stability theories of laws is that the laws differ from merely accidental non-laws in virtue of their invariance or stability under counterfactual suppositions. According to this view, Ceteris Paribus or non-universal laws differ from universal laws in degree, not in kind. Universal laws hold under all counterfactual suppositions, whereas Ceteris Paribus or non-universal laws merely hold for a limited range of suppositions. Section 7 deals with the dispositional account of CP laws. The unifying idea is that the laws of nature are grounded in dispositional properties. We distinguish two different dispositional accounts of CP laws on Huderman's 2014 version that is based on the pioneering work of Mill and Cartwright. Law statements are statements about dispositions, tendencies, or capabilities rather than about overt behavior, and CP laws have turned into strict laws. Bird's 2007 version of dispensationalism, by contrast, does not turn CP laws into strict laws. Instead, it identifies CP laws with generalizations hedged by a CP clause that are grounded in non-fundamental dispositional properties that admit of interferers. Section 8 deals with the normality theories of law. The guiding idea of normality theories is that CP all A and B's means that normally A are B's. The various normality accounts differ in their explication of the notion of normality, where Skurs interprets normality as a higher conditional objective probability of the consequent of the law statement given the antecedent. Spohn 2012 suggests to explicate the normality conditions in terms of degrees or belief and ranking functions over possible worlds. Section 9 sketches the relevance of CP laws in other areas of philosophy, such as epistemology and ethics. Section 10 is a survey of recent work on CP laws in metaphysics, philosophy of language, and linguistics, as well as other sciences. Section 11 presents a brief conclusion and outlook for future research. And finally, Section 12 provides a concise overview of the relevant literature. History and background. A brief historical survey from scholasticism to modern economics. The Latin phrase ceteris paribus, or ceteris, literally means other things being equal, was used in a non-technical sense by Cicero. However, most of the early uses of ceteris paribus clauses are found in economics. In economic context, the use of the ceteris paribus clause can be traced back to Petrus Olivi in 1295. In the 16th century, Juan de Medina and Luis de Molina used ceteris paribus while discussing economic issues. In 1662, William Petty was probably the first to use the term in English language publication in his Treatise of Taxes and Contributions. Petty qualifies his labor theory of value by a ceteris paribus clause. John Stuart Mill used the explicit phrase ceteris paribus only occasionally, but it had an important impact because he characterized economy by its way of coping with disturbing factors. Political economy considers mankind as solely occupied in acquiring and consuming wealth. Not that any political economist was ever so absurd as to suppose that mankind is really thus constituted. When a concurrence of causes produces an effect, these causes have to be studied one at a time and their laws separately investigated, since the law of effect is compounded by the laws of all the causes which determine it. Since economy is thus concerned with only one cause, its laws describe what would happen provided there are no other causal factors. The view of CP laws promoted by Mill in the absence of disturbing factors view. The historical roots of this view are, for example, found in John Eliot Cairns' description of the methodology of economics and character and logical method of political economy, 1888. The doctrines of political economy are to be understood as asserting not what will take place, but what would or what tends to take place. In this sense only they are true. Cairns uses the expression ceteris paribus in order to refer what would or what tends to take place if normal conditions obtained. The use of ceteris paribus clauses was advocated and popularized by Alfred Marshall in the 19th century. It was Marshall's genuine contribution to economics to advocate partial equilibrium analysis. Marshall's claim that an analysis of this kind holds merely ceteris paribus. In his influential Principles of Economics, Marshall defines the task of economics in terms of the phrase ceteris paribus. Economists answer a complex question, studying one bit at a time, and at last combining his partial solutions into a more or less complete solution of the whole riddle. In breaking it up, he segregates those disturbing causes whose wanderings happen to be inconvenient for a time in a pound called ceteris paribus. In the introduction to the same work, Marshall explains why economics is interested in the isolation of causes by assuming that other things are equal. The forces to be dealt with in economics are, however, so numerous that it is best to take a few at a time and to work out a number of partial solutions as auxiliaries to our main study. Thus, we begin by isolating the primary relations of supply, demand, and price in regard to a particular commodity. We deduced to inaction all of the forces by the phrase other things being equal. We do not suppose that they are inert, but for the time we ignore their activity. This scientific device is a great deal older than science. It is the method by which consciously or unconsciously sensible men have dealt with immemorial with every difficult problem in ordinary life. In a similar vein, Leonel Robbins claims in a classic paper, An Essay on the Nature and Significance of Economic Science, that economic laws and antecedent facts deductively imply economic predictions, but only if other things remain unchanged. The use of Ceteris Paribus in economics and in philosophy of economics is not of merely historiographical interest. In current philosophy of economics and economics, the use and of the debate of Ceteris Paribus is a vital issue. The philosophy of economics and the debate on philosophy of economics, it is widely recognized that generalizations in economics are qualified by Ceteris Paribus clause, yet its interpretation is controversial. Economists themselves use the Ceteris Paribus clause. Expressions such as Ceteris Paribus and other things being equal are commonly used in textbooks. Often they are explicated in a special section. Background to the contemporary debate. Outside the economics literature, the use of the Ceteris Paribus phrase became a central and also controversial issue in some areas of philosophy of science and in the philosophy of mind in the 1980s. The fact that test procedures for scientific theories or hypotheses are reliable only if disturbing factors are excluded or at least controlled for had already been noted by Carnap, Canfield, and Lair in 1961, have pointed out that in order to figure as premises of deductive nomological explanation, the laws of physics have to be furnished with CP clauses. Canfield and Lair also present an argument for why these CP clauses cannot be defined away, namely that any such attempt leads to an infinite regress of further CP clauses. The issue of disturbing factors was taken up in 1970 by Lakatos, who raised it as a problem for the falsification methodology. Some scientific theories forbid an event occurring only on the condition that no other factor has any influence on it. Another way of putting this is to say that some scientific theories are normally interpreted as containing a Ceteris Paribus clause. Popper only briefly commented on this claim in a footnote, while other authors discussed it explicitly as a problem for falsification. Hempel argues in 1988 paper on Provisios that every inferential construer of scientific theory testing is confronted with the problem that a provisio always has to be added. A provisio has to be conceived as a clause which pertains to some particular application of a given theory and which asserts that, in the case at hand, no effective factors are present other than those explicitly taken into account. In fact, Hempel dismisses the phrase Ceteris Paribus as not particularly helpful. Carnap, Lakatos, and Hempel all argue that in theory testing, we usually implicitly assume an additional premise that states that there are no disturbing factors, even though in the latter literature, Hempel's paper has taken to evidence for the existence of CP laws even in fundamental physics. The issue of whether CP clause has to be added as an extra premise in theory testing has to be distinguished from the claim that laws themselves should be read as containing an implicit CP clause. Two further developments lead to the explicit discussion of CP laws. First, in her paper, The Truth Doesn't Explain Much, Nancy Cartwright, 1983, criticizes the DN model of explanation on the grounds that the alleged laws which the explanation relies, according to the DN model, are not true, but rather generalizations that hold under special, typically ideal conditions only. These CP laws, she claims, will not do the work required. Ceteris Paribus generalizations, read literally without the Ceteris Paribus modifier, are false. They're not only false, but held by us to be false, and there is no ground in the covering law picture for false laws to explain anything. On the other hand, with the modifier, the Ceteris Paribus generalizations may be true, but they cover only those very few cases where the conditions are right. According to Cartwright, the problem arises that these laws cover only special or ideal conditions, whereas in scientific practice they are used to explain phenomena in non-ideal situations as well. CP laws seem to play an essential role in explanations, but there's no account available for how CP laws can do this work. Second, the issue of CP laws became important in the philosophy of mind as well. Davidson argued for his anomalous monism on the basis of a stark contrast between homonomic and heteronomic generalizations. Homonomic generalizations are those that can be improved in the same vocabulary in which they are stated. This requires, as Davidson put it, a comprehensive closed system that is only provided by physics. Outside of physics, We have only heteronomic generalizations, generalizations that can be made precise only by drawing on the vocabulary of another science. As a consequence, Davidson assumes that only physics laws, whereas physics has laws, whereas there cannot be psychophysical or psychological laws. Moreover, generally, Davidson's argument implies that there are no special science laws. This claim provoked discussions about whether there are genuine psychological laws. Some authors, such as Schiffer, 1991, and Ehrman, Roberts, and Smith, 2002, have been argued that no special science from biology upwards has genuine laws of its own. By contrast, most authors have supported only the weaker claim that there are no strict special science laws, but have argued that special science laws should be construed as laws that contain implicit CP clauses. Fodor, 1987, observes that we do not use psychological generalizations for predicting and explaining human behavior. These generalizations or laws, says Fodor, are non-strict. They are hedged by a CP clause. Nevertheless, these claims, he insisted, are neither false nor informative. It is, I expect, a long story how the generalizations of the special sciences manage to be both hedged and informative. Telling this story is part of making clear why we have this special sciences at all, why we don't just have basic physics. So by the end of the 1980s, CP laws had become focal in two important debates, one about the structure of scientific explanations in general, and the other about the status of the special sciences as autonomous scientific disciplines. A framework for the discussion distinguishing exclusive comparative and definite indefinite ceteris paribus laws. It has been argued that ceteris paribus is an ambiguous notion. Two distinctions will help to disambiguate the notion, the distinction between comparative and exclusive CP laws, and the distinction between definite and indefinite CP laws. Comparative versus exclusive CP laws. Ceteris suggests distinguishing between two conceptions of CP laws, comparative versus exclusive. Comparative CP laws require that factors not mentioned in the antecedent or the consequent of the law remain unchanged. By contrast, exclusive CP laws assert the connection between the antecedent and consequent only under the condition that certain factors are excluded. The comparative sense of CP clauses derives from the literal meaning of ceteris paribus as the others being equal. A comparative CP law asserts that the increase or decrease of the value of a variable leads to an increase or decrease of the value of another variable, provided that all the other possibly unknown independent variables that describe the state of the considered system, or at least those independent variables that are potentially interfering, remain at same values. Thereby, a variable is so-called independent if and only if it is not causally or nomologically influenced. So to repeat, that a variable is independent means, by the above definition, only that if it is not caused by, though it may well be the cause. The reason why CP laws of this type are called comparative in Ceteris is that the requirement that the other independent variables are equal or remain at the same value only makes sense if the law compares two states of a described kind of system. These two systems differ in the value of the antecedent variable, but agree in their values of the independent variables. If the latter condition holds for all possible values, the comparative CP law is called unrestricted, otherwise it is called restricted. Another possible name of this kind of CP law would be the equality CP law. So this gets pretty intense. I recommend people reading it, but I'm going to skip a lot of this because time is limited and it's pretty technical. Restricted comparative CP laws are nothing but comparative CP laws in the scope of an exclusive CP clause, which assert the comparative CP relation only for a restricted class of circumstances expressed in the terms allowed values of the independent variable. An important distinction concerning definite versus indefinite CP laws. An important distinction concerning only exclusive CP laws is the distinction between definite and indefinite exclusive CP laws. The definite exclusive CP law specifies the disturbing factor which are excluded or the validity conditions which are required. In the antecedent of the law, in other words, a definite exclusive CP law, exclusively CP has a strict completion, whereas the completing condition excludes the presence of the specified disturbing factors in the application. Ehrman, Roberts, and Smith call definite exclusive CP laws lazy CP laws. It's widely agreed in the philosophy that the real signifiers of exclusive CP laws lies in situations where strict completion is impossible. In that case, the exclusive CP law is indefinite, which means that the exclusive CP law consists in a universal second order condition which excludes the kind of disturbing factors to the law, whatever they are. So unfortunately, okay, I will read more parts of this. Like this, it gets pretty intense, and this is pretty important. So, the challenge: exclusive Ceteris Paribus laws between falsity and triviality. Exclusive CP laws in the form exclusively CP A's are B's admit exceptions, instantiations of A's which are not B's. A philosophical reconstruction of exclusive CP laws, which includes restricted comparative CP laws, and thus the majority of all CP laws, faces a severe problem. This problem can be articulated in the form of a dilemma. This dilemma has been formulated by Lang, who attributes it to Hempel. First horn: if exclusive CP laws are reconstructed as some sort of strict law, then they will tend to be false. Typically, it will not be the case that all A's satisfying a completer condition C are B, since the range of potentially disturbing factors is typically indefinable. In other words, special science laws that instantiate perfect regularities are, mildly put, scarce. Yet if one supposes that the laws to be formalized as universally quantified conditional sentence, then one counterinstance due to disturbing factor to the universally quantified sentence means that it is false. Second horn: if we instead suppose that an indefinite exclusive Ceteris Paribus clause is attached to the law, so that means that all A's are B's if nothing interferes, then the CP laws in question is in danger of lacking empirical content. It lacks empirical content because it seems to say nothing more than all A's are B's and not all A's are B's. If this is true, then exclusive CP laws are analytically true sentences and therefore trivially true. This, however, is an unwelcome consequence because laws of the special sciences should be reconstrued as empirical statements, not as sentences being true in a virtual meaning. Both horns are quite unpleasant results for any philosopher looking for a theory of non-strict laws. To deal with this dilemma is a central challenge for every theory of Ceteris Paribus laws. In the following section, several attempts to cope with the dilemma are presented to the tenacious problems discussed. The method of completers, exclusive CP laws, the method of completers, semantics and epistemic completers. The general idea behind completer approaches is that the best way to explicate exclusive CP laws is to add the missing conditions for a strict implication into the antecedent to the first law statement. There are two quite different possibilities to do this. The first possibility is to add these conditions explicitly by appropriate descriptions of the first order individual variables involved in the law. If this were the correct account, all correct CP laws would turn out to be definite exclusive CP laws. The second possibility is to add these conditions by way of a second order quantification over the first order predicate variables, which applies to the first order individual variables of the law. In this account, CP laws are turned into indefinite exclusive CP laws. Fodor's starting point for his account of CP laws is Davidson's distinction between homonomic and heteronomic generalizations. Exceptions to the generalizations of a special science are typically inexplicable from the point of view of, that is, the vocabulary of that science, that one of the things that makes it a special science. But of course, it may nevertheless be perfectly possible to explain the exceptions in the vocabulary of some other science. On the one hand, the special science Ceteris Paribus clauses are ineliminable from the point of view of its propriety conceptual resources, but on the other hand, we have so far at least no reason to doubt that they can be discharged in the vocabulary of some lower level science. So Fodor's idea is that the additional factors whose existence is required by the exclusive CP clause cannot be completely specified within the conceptual resources of the special sciences, although this could be done, at least in principle, within the vocabulary of some more fundamental science, such as neurophysiology or ultimately fundamental physics. Fodor calls the missing factors completers. Although Fodor starts with the hope that the missing conditions of exclusive CP laws could eventually be specified in the fundamental science, his definition of exclusive CP laws involves second-order quantification over variables. unspecified completers of independent exception explainers. Hence, his account of the exclusive CP laws belongs to the family of indefinite exclusive CP laws. Because of this fact, Fodor and related accounts face severe problems. Schiffer, Fodor, and Mott try to explain CP laws by ordinary truth conditions. In contrast, Petrowski and Ray provide stronger conditions for what they call non-vacuous truth in terms of epistemic conditions such as explanations and independent conformability. Petrowski and Ray compare CP clauses to checks. These checks represent a promise to the effect that all counterinstances of the putative law can be explained by citing factors that are independent of that law. If the promise cannot be kept, the check was no good to begin with. Completion is conceived here as an explanatory completion, and is required only post factum. If there is a counter instance of the law in question, we are committed to explain why the law was not instantiated. A CP law holds in a closed system, a system considered in abstraction from other independently existing factors, such as systemization in non-vacuous, only to the extent that deviations from the regularities that are constitutive, or it can be explained by those factors. For the CP laws to be acceptable, in spite of the counter instances, we need independent evidence for the existence of the disturbing factor. It would not be acceptable if the only evidence for the existence of the disturbing factor were the counter instance we started with. Petrowski and Ray account involved a second order quantification over specified exception explainers. Thus, as in the case of semantic completer accounts, their account explicates indefinite exclusive CP laws and faces severe problems to be explained. So it's like invariance and stability theories. The common guiding idea of invariance and stability theories is that the laws differ from non-laws in virtue of their invariance or stability under counterfactual suppositions. Stability and invariance are often taken to be synonymous. For the sake of clarity, we will use stability to refer to Lang's stability theory of laws, and we will use invariance to refer to Woodward and Hitchcock's invariance theory of laws. In stability invariance accounts, laws qualified by CP clause are considered to be non-strict in the sense that they hold true only under a limited range of counterfactual suppositions. Different versions of invariance or stability theories differ in how they determine this limited range of counterfactual suppositions. In this sense, invariance or stability theories can be understood as an alternative to exclusive interpretations of non-strict laws and as an attempt to deal with the dilemma of triviality and falsity. Counterfactual, stable laws, and pragmatic knowledge of disturbing factors. According to Lang, the universal fundamental laws in physics and the CP laws in the inexact special sciences differ only in degree. The lawhood of universal laws and the CP laws is due to the same property of these statements, their stability. Lang's approach consists of two steps. First, the role of laws in scientific reasoning is determined. They figure in explanations and predictions. They support counterfactuals, and they're indictively confirmed. And second, it is claimed that the laws can play this role because of their characteristic stability. So in order to understand Lang's account of CP laws, we must first clarify the crucial notion of stability. Lang's basic idea is that laws are law-like because they are true in a wide range of possible conditions. Most importantly, that laws do not only hold true in any non-nomic actual condition, but also remain true in all non-nomic counterfactual suppositions. Along these lines, Lang proposes a preliminary definition of laws in terms of nomic preservation. Some proposition L is a law if and only if its truth is preserved under all those counterfactual suppositions that are consistent with every physical necessity under all physically possible counterfactual suppositions. This definition, however, raises an obvious question. What does it mean to be physically possible? Roughly, a proposition is a physical possibility if and only if there is some possible world where the same laws of nature hold as the actual world and obtains at will. But if this is true, Lang's definition of lawhood seems to be circular, since being consistent with the laws of the actual world is ultimately part of the definers of being a law of the actual world. We can now turn to the question of how CP laws differ from universal laws. According to Lang, CP laws are stable sets of propositions whose application is pragmatically restricted to the purposes of scientific discipline. He elaborates this idea with respect to the laws in special sciences or inexact sciences, as he calls them. A set is stable for the purpose of an inexact science if and only if it is invariant under every counterfactual supposition of interest to the science and consistent with the set. Lang tries to avoid the horns of the falsity or triviality dilemma by treating Ceteris Paribus as a name for a set of interfering factors. Notice the interfering factors does not list all the possible interferences which prevent the occurrence of the CP all A's or B's, but only those factors that are relevant for a discipline. One can understand Lang in a way that he provides two strategies to determine the members of the interference set, the strategy of non-negligibility and the strategy of intended interest of a science. Both strategies try to explicate a methodology that is implicitly used by the scientist in a particular discipline. The strategy of non-negligibility, instead of providing a complete list of all interfering factors, the scientists merely refer to those interfering factors that arise sufficiently often and can cause sufficient great deviations. The strategy of intended interest of a science, a law may still count as stable if it fails to hold under those counterfactual suppositions that do not fall into the range of law's intended purpose and application. It is illuminating to contrast Lang's strategy of determining a set of disturbing influences, interferences in the light of intended application of the law with the use of CP clauses that does not indeed render a statement trivial. According to Lang, excuse clauses of this kind differ from CP clauses as used in scientists because the latter refers to strategies for determining disturbing factors, although the relevant set of disturbing factors is not listed explicitly. It is implicit in the scientific practice and the education and studies in a particular field of inquiry. Based on his stability theory of laws, Lang also proposed an argument for the autonomy and irreducibility of special science laws. Recall that arguing for the autonomy and irreducibility of the special sciences with respect to physics was one of the crucial motivations to the start of the debate on CP laws. Suppose that the laws of a certain special science are stable with respect to the purposes, the pragmatic restrictions unique to the special science. In other words, the special science laws are stable for counterfactual suppositions that violate other disciplines' laws, for example, the laws of fundamental physics. Thus, the special sciences laws are stable under some counterfactual suppositions for which fundamental physics is stable. This unique range of stability makes the special sciences epistemically autonomous as a scientific discipline because the special sciences laws configure, for instance, an explanation answering some why questions that no other disciplines can answer as adequately as the special science itself. Invariance under the interventions of explanatory generalizations. Similar to Lang's stability theory, the invariance approach also identifies the stability of invariance of a generalization as its key feature for performing the role of a law and figuring in explanations and predictions. As in Lang's theory, to be invariant means for Woodward and Hitchcock's to be true under several, not necessarily all, counterfactual suppositions. Despite this basic agreement, there are important respects in which the invariance theory differs from Lang's stability theory. In what follows, we will focus on the distinguishing features of the invariance approach. The quantitative language of law statements. Although the idea might be implicit in Lang's theory, invariance theories conceive candidates for law statements explicitly and straightforwardly as quantitative statements. Thus, the predicates occurring in the statement about variables which maintain certain variables. Counterfactual suppositions viewed differently. Interventions. Invariance theories characterize the counterfactual supposed antecedent conditions under which a generalization remains stable differently than Lang's stability theory. In different kinds of variables, invariance theories distinguish two kinds of variables: explicit variables that figure explicitly in a generalization and background variables that describe background conditions which are not mentioned in the generalizations and questions. Consequently, interventions can be carried out with respect to both kinds of variables. Similar to Lang's theory, Woodward and Hitchcock used the intended purpose of inquiry of a certain discipline to distinguish between interventions into explicit variables and background variables. According to their invariance theory, only the former are of importance to laws in a specific scientific discipline. Obviously, the reason to ignore rare but possible changes in the background variables is very similar to Lang's strategy of non-negligibility. Woodward contrasts these negligible changes of background variables with important changes of explicit variables. Conditions of invariance. Invariance theories differ drastically from Lang's approach in defining the key notion, stability or invariance. According to Woodward and Hitchcock, a statement in the form is invariant if and only if the following so-called testing invariance condition holds, that there are at least two different possible values of an explicit variable for which realizes a value in the way that the function describes, and the fact that takes or alternatively is the result of an intervention. The most intuitive case of testing an intervention might be describing an actual state of affairs, describes a possible counterfactual of affairs. The degrees of invariance, one can still distinguish more or less stable generalizations, so invariance is not all or nothing matter. Instead, it admits of degree. Roughly put, the degree of invariance of a generalization G is measured by the range of possible values of variables contained in G for which G remains invariant. This applies two extremes of invariance. A generalization that holds for all possible values of its variables is maximally invariant. A generalization G that holds merely for two of the possible values of the dependent variables of G is minimally invariant. Between these extremes of invariance lie generalizations which hold only for a certain range of values. Woodward and Hitchcock illustrate this latter kind of generalizations by the example of an equation that describes the growth of a plant depending on the amount of water and fertilizer. According to Woodward and Hitchcock, laws or generalizations of special sciences do not hold under all interventions. They merely hold for a certain range of possible values of those variable figuring in the law statement. By being non-strict, the generalizations in the special sciences do not satisfy a condition that is traditionally associated with laws of nature, namely the condition of universality. Nevertheless, being invariant for a limited range of values is enough for a proposition to play a law-like role in the sciences. Woodward and Hitchcock developed further criteria and examples of determining the degree of invariance of a generalization. Let us compare Lang's stability theory and Woodward and Hitchcock's invariance theory with respect to a range of counterfactual suppositions, or alternately interventions to which the law is applicable. One could say that Lang's stability theory and Woodward and Hitchcock's invariance theory start from the opposed extremes of the spectrum of stability. Lang starts at the maximum of stability. He starts with the claim that the law proposition remains true for all counterfactual suppositions that are consistent with the law, where by definition a counterfactual supposition is admissible if it is consistent with the laws of nature. In the second step, Lang reduces the set of all counterfactual suppositions consistent with the law because certain pragmatic goals of the discipline which uses the propositional law. Woodward and Hitchcock start with minimal stability, the satisfaction of the testing intervention condition for some propositional. In the second step, Woodward and Hitchcock add to a minimum stability that the law's degree of invariance increases with a number of possible interventions for which the law holds among other criteria. Different strategies to distinguish laws from accidentally true generalizations. Traditionally, philosophers of science believe that genuine laws differ from accidentally true generalizations in kind. In various theories such as Woodward and Hitchcock agree that such a distinction can be drawn. Accidentally true generalizations are not minimally invariant in the sense of satisfying the testing intervention condition. Therefore, laws and accidental generalizations differ in kind. However, Woodward and Hitchcock acknowledge the fact that minimally invariant generalizations may fail to be stable because these generalizations may be true only if very specific background conditions obtain. Analogously, Lang argues for a principal distinction between laws and accidents within the framework of his stability theory. However, Lang's strategy to distinguish laws from accidents seems to be partly motivated by the intuition that minimal invariance in Woodward and Hitchcock's sense is too weak to account for real-life stability displayed by scientific generalizations. Correspondingly, Lang argues that Woodward and Hitchcock's account fails to distinguish laws from mere accidents and therefore also fails to account for laws' characteristic explanatory power. John Stuart, dispositional accounts. John Stuart Mill objected to the claim that laws might have exceptions. The problem of exceptions disappears if laws are taken to refer to tendencies. With regard to exceptions, in any tolerable advanced science, there is properly no such thing as an exception. What is thought is Mill in 1836. What is thought to be an exception to a principle is always some other and distinct principle cutting into the former, some other force which impinges against the first force and deflects it from direction. There are not a law and exception to that law, the law acting in the 99 cases and the exception in the one. There are two laws, each possibly acting in the whole 100 cases and bringing about a common effect by their conjunct operation. Thus, if it were stated to be a law of nature that all heavy bodies fall to the ground, it would probably be said that the resistance of the atmosphere, which prevents a balloon from falling, constitutes the balloon as an exception to the pretended law of nature, but the real law is that all heavy bodies tend to fall. The idea was taken up by Cartwright and others. Cartwright's discussion of CP laws focused on the question why CP laws are of interest in non-ideal situations. In what CP law says is confined to special, namely ideal circumstances, it seems prima facie that these laws are irrelevant for all other non-ideal situations. That, however, is not the case in scientific practice. CP laws are used to explain phenomenon outside of the ideal circumstance. Cartwright argues that this practice requires the postulation of capacities or tendencies. The logic that uses what happens in ideal circumstances to explain what happens in real ones is the logic of tendencies or capacities. What is ideal situation for studying a particular factor? It is a situation in which all other disturbing factors are missing. And what is special about that? When all other factors are absent, that factor manifests its power explicitly in its behavior. This tells you something about what will happen in the very different mixed circumstances, but only if you assume that the factor has a fixed capacity that carries it with it from situation to situation. Subsequently, her suggestion has been taken up by several authors that attempt to provide semantics for CP laws or even of laws in general in terms of dispositions. The prima facie advantage of dispensational accounts of laws vis-a-vis the CP law problem is the following. The dispensational account provides semantics for CP laws. According to one version of the dispensationalist account of CP laws, a law statement is true provided the type of system in question has the disposition that the law statement attributes to the system. Reconstructing law statements as statements about disposition, tendencies, or capacities rather than about overt behavior turns CP laws into strict laws. The claim is, as in Mill, that certain kinds of systems have certain kinds of tendencies or dispositions. In stating the law is no longer necessary to appeal to CP clauses. One advantage of the so-called problem of instantiation. The problem is that many CP laws appear not to have any instances can be solved. The law is no longer considered to be a description of the system's current behavior that is only manifested under very special conditions, if at all. The law concerns the underlying stable tendencies or dispositions. Furthermore, the dispositionalist account is able to provide a rationale for why scientists are interested in CP laws. CP laws describe how systems behave in the absence of disturbing factors. If the disposition tendency can manifest itself completely, this knowledge can be used to account for more complex situations in which various systems and their dispositions are intertwined, provided laws of superposition are available. There's a different version of a dispositionalist about CP laws according to which they are not turned into strict laws. In a nutshell, Bird's general idea is that the laws of those regularities whose truth is guaranteed by the essential disposition nature of one or more of their constituent properties. According to Bird, fundamental essentially dispositional properties or potencies give rise to strict laws since they are no or only very few finks or antidotes that would prevent the manifestation of the potency from occurring if the stimulus had occurred. However, the manifestation process of non-fundamental dispositional properties can be inferred with, and so the manifestation only occurs ceteris paribus in conditions where the trigger occurs and the finks and antidotes are absent. Therefore, these non-fundamental properties give rise to ceteris paribus laws only. We want to focus on two kinds of concerns that have been raised with respect to dispositionalist accounts. Dispositions, power, potency, or tendencies may be present without being manifest. Thus, if one wants to if one wants to explain is the actual pattern, how does citing a tendency which for all we know may or may not be dominant and thus by itself or may not produce something like the actually observed pattern serve to explain this pattern. As a rejoinder, dispositions can point to laws of composition. As a consequence, it is not the disposition on its own that can explain the actual pattern in such laws, but rather the dispositions plus the law of composition. To the extent that such laws are available, the contribution of the various tendencies or dispositions can be determined even if they fail to be completely manifest. It can, however, be disputed whether such laws of supposition composition are available in general, especially if one holds like Bird that every law needs to be grounded in potencies. But even if the composition laws are taken to be underpinned by dispositions, a further law seems to be needed that tells us what happens if the disposition for the law of composition fails to be manifest. We need a meta law that tells what the law of composition contributes to the actual behavior, so the assumption that laws of composition are grounded in dispositions attributed to physical systems threatens to lead an infinite regress. The second problem concerns the question whether a dispositional account can indeed avoid the dilemma for exclusive CP laws, even though it is true, at least on one version, that the laws no longer appeal explicitly to CP clauses. The triviality or falsity dilemma turns up at a different place. The dispositionist still has to specify the stimulus or triggering conditions for the disposition in order to give the disposition's ascription a determinate content. The condition under which the disposition will manifest itself are exactly those that are required to explicate the CP clause. So explicating the triggering condition of a disposition requires that something informative is said about the CP clauses, and more generally leads us back to the problems discussed in the previous sections. Normality theories. The reconstruction of exclusive CP laws in terms of strict completions does not imply anything about the probability with which undisturbed antecedent events will produce the consequent. According to the proponents of normality theories, this seems to be counterintuitive because CP laws should be asserted only if the situation without non-negligible disturbing factors is a normal or at least a rather probable situation. Examples of correct exclusive CP laws which violate this normativity condition are, for example, exclusively CP, no tires blow out, exclusively CP, there are no clouds in the sky. Several authors have therefore developed so-called normality accounts of CP laws, including Silverberg, Ehrman and Roberts, and Ceteris, who argue that the normality interpretation is the preferred interpretation of the exclusive CP laws in the life sciences from biology upwards to the social sciences. Normality theories can be understood as an alternative to the definite and or indefinite exclusive interpretations of non-strict laws. The general idea of normality theories is that CP all A's are B means that normally A's are B's. They can also be combined with comparative interpretation into normal comparative law statements such as normally an increase of X leads to an increase of Y when other X independent variables are held constant. However, the normality account differs in their explication of the notion of normally. One possibility is to explicate the normality condition in terms of the high probability of the consequent predicate given the antecedent predicate where the underlying condition probabilities are objective statistical probabilities based on the description of evolutionary systems. Another possibility is to explicate the normality conditions in terms of the degrees of belief in ranking functions over the possible worlds. Largely independent of Ceteris and Spum's specific approaches, but in agreement with the general idea of normality approaches, Hutterman and Rutlinger and Kolanenko, Rutlinger, Roberts, and Struvens have recently explored statistical approaches to CP laws according to which CP law statements are statistical claims. According to the statistical consequence thesis, normic laws imply numerically unspecified statistical generalizations of the form most A's are B by which they can be empirically tested. The statistical consequence thesis has been challenged by cognitive scientists and by the philosophers of biology. Ceteris defends the statistical consequence thesis by the following argument, which is based on the generalized theory of evolution that does not only apply to biological evolution, but also to cultural evolution. The common domain of the life sciences, which according to Ceteris include biology, psychology, as well as the social sciences and the humanities, are evolutionary systems or their products. Evolutionary systems are systems whose self-regulatory properties have been gradually selected according to their contribution to reproductive success. The temporal persistence of self-regulatory systems is governed by a certain range of prototypical norm states in which these systems constantly have to be in order to stay alive. They manage this with the help of regulatory mechanisms which compensate for disturbing influence of the environment. Although the self-regulatory capacities of evolutionary systems are the product of a long adaptation history, they're not perfect. Dysfunctions may occur, whence their normal behavior may have various exceptions. Yet it must be the case that these systems are in their prototypical norm states in the high statistical majority of the cases in time, since otherwise they would not have survived the evolution. In this way, evolutionary theoretic foundation of normic laws do not only explain why normic laws are the typical form of the laws of the life sciences. It also explains why normic laws are not strict, but nevertheless are associated with high conditional statistical probabilities, at least for most cases and times in evolution. According to Ceteris 2002, the difference between idealization conditions in physics and normality conditions in evolutionary science can be explained in follows. In physics, one traditionally thinks of complexity as a source of disorder. Regularities are obtained by abstracting away from complexities. In evolutionary systems, by contrast, complexity is usually a source of order, complexity which has been selected by evolution to stabilize normic behavior. As Wackbroit puts it, ideal planets are theoretical abstractions. Mass points under the influence of a centripetal force are nothing else. They do not literally exist. In contrast, normal birds really do exist because they are what has been selected through evolution. When speaking of normal bird, we do not extract from its admirable complexity, but we rely on it as the cause of its normal behavior. This does not mean that the abstract laws of physics play no role in the explanation of function and behavior of evolutionary systems. Normal conditions approach. Another way to understand Ceteris Paribus as referring to normal conditions is introduced by Wolfram Sporn. Sporn takes the connection between Ceteris Paribus qualifications and normality to be straightforward. Ceteris Paribus means other things being normal. Let us call this the normal condition approach. The basic idea of the normal condition approach is that CP laws hold when normal conditions obtain. Sporn characterizes normal conditions as exactly those conditions that normally, usually, mostly obtain in the small space-time region inhabited by us. Translated in probabilistic terms, the expression conditions that normally, usually, mostly obtain means the occurrence of some conditions is highly probable. For Spohn, a condition is normal if it is expected, or at least not ruled out to obtained by a rational epistemic agent. Sporn's normal condition approach differs from Schertz's normal condition approach in at least two respects. According to Sporn, and contrary to Schertz's theory, which refers to the objective probabilities, the fact that normal conditions obtain is conceived epistemically and more specifically stochastically. An epistemic agent forms beliefs about the normality of conditions. Someone strongly believes that that condition obtains. Sporn describes the epistemic functioning of belief stochastic states about normality by modeling degrees of belief in terms of ranking functions. Normality in Sporn's theory is explicated in terms of background conditions, not in terms of probabilistic relations between the antecedent predicate and the consequent predicate. If someone believes that the law holds, then he believes that this functioning relation holds under normal conditions, which means in terms of Sporn's ranking function that the law is believed with rank 0. It is true in all normal worlds of a ranked world model. Such a ranked world model consists of a set of possible worlds together with a ranking function which attaches to each world a natural number specifying its rank. Worlds with rank 0 are the most normal worlds. Worlds with rank 1 contain exceptions from normal conditions, first degree exceptions. Worlds with rank 2 exceptions from those exceptions, second degree exceptions, etc. Sporn 2014 is the most recent in-depth elaboration of his normal conditions based on epistemic accounts of his Ceteris Paribus laws and conditions. Since the normal condition N expresses the proposition that a given situation the world is normal, it would seem that the ranking of worlds account entails the possibility of a strict completion by adding a normality condition to the antecedent. Indeed, it follows from the truth condition of the assertion normality in a ranked world model that there exists a propositional N, namely the set of all worlds with rank 0, such that normality is true in the given ranked model if and only if the material implication is true in all worlds of the model. This does neither imply, however, that the completing proposition can be linguistically expressed, nor that it can be expressed in a non-trivial way, in the sense that it does not imply on logical reasons alone, since one can only speak of a strict completion of normality if both conditions hold. It follows that the ranking of worlds account does not in fact entail the possibility of a strict completion. The result is adequate because we have argued above in most cases, especially in all non-deterministic situations, a strict completion is impossible. Thus, to have to keep in mind that speaking of a normality condition does not imply that these normality conditions can be expressed by any non-trivial proposition. Also note that the rank world accounts and the conditional probability accounts are equivalent as a semantics for logical axiomizations of conditional reasoning. Ceteris paribus laws of non-monotonic reasoning. Reasoning from exclusive or normic CP laws has an important logical feature. The inferences are in contrast to deductively valid arguments non-monotonic. An inference is monotonic if and only if adding arbitrary new premises to a valid argument preserves its validity. Two prominent semantic criteria for the truth of non-strict conditional and the correctness of inference from non-strict conditionals have been suggested in the literature. The high probability semantics understands normic laws in the sense of high conditional probability assertions. The semantics considers a non-strict conditional A implies B as true in a probability model if the uncertainty of the conditional, which is defined as 1 minus the conditional probability, is sufficiently low. An inference of a conclusion conditional from a set of premise conditionals regarded as valid in the semantics if and only if the uncertainty of the conclusion conditional is not greater than the sum of uncertainties of the premise. High probabilistic semantics goes back to Adams, 1975, and is extended to Schur's. The second semantics, the normality semantics, corresponds to the normal condition account. The semantics considers a conditional A implies B to be true in a ranked world model if and only if all lowest rank A worlds and B worlds. An inference is considered as valid in this semantics if and only if all ranked world models which verify all premises conditionals verify the conclusion conditional. Remarkably, both semantics lead to the same conditional logics. Both semantics possess the system of preferential entailment as correct and complete axiomatization of inferences among pure conditionals of the system of rational entailment for inferences among true function combinations of conditionals. Prima facie reasons and ceteris paribus conditions in ethics and epistemology. The use of CP is not restricted to the philosophy of science. It has been used in other areas of theoretical and practical philosophy as well. For instance, prima facie reasons are reasons under the constraint of exclusive CP conditions. They play an important role in the ethics and epistemology. In ethics, a prima facie norm is an obligation. Petrowski has promoted the ceteris paribus understanding of moral obligations as a solution to paradoxes of moral obligations, especially for the solution of moral dilemmas. The CP reading of moral obligations have proven to be helpful because although two conflicting CP obligations may block each other, they do not produce a strict consistency in the same sense of deductive logic. In epistemology, a prima facie reason for a belief is the reason which justifies this belief in the absence of defeaters of exceptional information to the contrary. Prima facie reasons have been suggested in epistemology as means of providing weak and defensible a priori justifications for epistemologically fundamental beliefs, such as the belief in the existence of an external reality, for which a strict and non-circular a priori justification seems to be impossible. Nevertheless, the inference from visual appearances to reality counts as defensively justified as long as there does not exist serious defeaters, reasons for serious doubts. One may object that a similar kind of possible exception to the inference from visual appearances to reality is constituted by the possibility of a Cartesian demon who infuses humans with illusory perceptions, which is one of the major skeptical counter-arguments to the inference from appearances to reality. In response to this objection, several epistemologists have argued that these kinds of exceptions are not seriously exceptional, and therefore the inference from appearances to reality is defeasibly valid. Finally, applications CP clauses are also found in the form of presuppositions in the philosophy of language. Here to assume that understanding linguistic expressions requires defeasible assumptions or presumptions, for example, presumptions concerning the rationality of the speaker. Ceteris paribus laws, metaphysics, language, and science. In the current literature, a number of novel trends and innovative approaches to CP laws have emerged that cannot easily be subsumed under the already existing accounts. For this reason, they deserve special mention. We believe there are at least 4 clearly discernible novel tendencies in the current work of CP laws. A reconnection to metaphysics. One of the most salient trends in the current literature is the discussion of CP laws reconnects philosophy to the science of analytical metaphysics in at least 3 respects. Current accounts of CP laws makes use of David Lewis's 1973 best system account of laws. Moreover, the interpretation of objective probabilities and the metaphysics of decomposition are brought into play for making and understanding CP law statements. The most vivid sign of this reconnection consists of the fact that several authors have recently defended friendly amendment of David Lewis's best system account of laws of nature. While Lewis's original version primarily focuses on fundamental laws, the amended versions are intended to capture all non-fundamental laws of the special sciences. Schrenk, Callender, and Cohn and Frisch defend a so-called best system account for special science laws. Unterhuber develops a version of the better best system account utilizing generics. Jog and Lowell argue for a pragmatic version of the best systems account that captures also central insights of the better best systems theory on their view. The universality of laws is not an end of itself, and generalizations invariance is limited to our cosmic epoch only. This time invariance arguably would be enough to make it useful for us, and thus a law according to the account. Rutlinger and Bachman provided a critical discussion of the better best system account. Brandon Mitchell and Wheeler presented versions of the best system account deploying the idea of algorithmic compression from data science. Albert and Lower advocated a statistical mechanical version of the best system approach to special science laws, which is, unlike the better best system account, committed to the particular Boltzmann-inspired interpretation of statistical mechanics, including assumptions about the early history of the universe. Westlake and Frisch provide critical responses, while Fenton and Glynn constructively use examples by Albert and Lower for an analysis of CP laws. Finally, Albert and Lower's account also connects the debate of CP laws with the ongoing discussions of whether causation has a place in the fundamental physics or whether causation is an emergent phenomenon captured by the CP law statement of the special sciences. And other metaphysical issues besides Lewis's account of law had influenced the recent literature on CP laws. The metaphysics of probabilities and the disposition stand out in this respect, taking results from Ehrman and Roberts and Skurs. Several authors, including Huntemann and Rutlinger, Aqualalenko, Roberts, and Strevens, discuss the prospects of a statistical approach to CP laws, or a softness approach, to use Strevens' term, according to which CP laws are statistical claims. A third metaphysical trend concerns the metaphysics of dispositions. Huterman and Pemberton Cartwright argue in favor of dispositionalist accounts of CP laws and provide responses to standard objections to the dispositionalist view. Drawing on linguistics and philosophy of language, several recent approaches to CP laws explicitly draw on research in linguistics and philosophy of language, taking into account linguistic work on genetics. Nickel argues that our understanding of CP law statements is improved if one takes them to be generics and uses the formal semantics for generics to shed light on the meaning of CP laws. Roberts makes contact with philosophy of language and analyzing CP laws as vague and indexical statements about frequencies. Ward, Karzabazadeh, and Nickel explore the link between CP laws and different accounts of natural kind terms. Sensitivity to the science. Several philosophers have made an effort to draw attention to the fact that adequate discussions of laws has to be sensitive to the differences between distinct scientific disciplines. Their motivations is to provide a theory of laws that fits generalizations and models in the life sciences and social sciences, and more generally the sciences of complex systems. In particular, Mitchell, Strevens, Craver, Huterman, Wimsatt, Tobin, Woodward, and Rutlinger distinguish various dimensions of characterizing how generalizations in these scientific disciplines may be non-universal or allow for exceptions. These dimensions include stability, robustness, specificity, and historical contingencies. A similar vein, Skurs introduces a novel distinction between Ceteris Paribus and Ceteris Rectus laws. Fenton and Glynn hold that some higher-level laws about the macro behavior of a complex system are minutus rectus laws that should be distinguished from CP laws because their non-universal character stems from a probability distribution over initial micro conditions. Finally, motivated by examples from population ecology, herb science, and statistical mechanics, Strevens and Weisberg argue for new interpretation of laws and models involving idealized assumptions, the minimalist account of idealizations. Strevens proposes treating CP laws and idealized laws separately. What seems to emerge from this literature is the Ceteris Paribus character of generalizations is multifaceted. There's a number of ways in which generalizations could be non-universal due to idealizations by expressing statistical regularities and probability distributions over initial conditions, by drawing on the notion of normality, by being sensitive to changes in initial and background conditions, and so on, using scientific concepts and methods. Recent philosophical attempts in capturing CP laws increasingly involve importing key concepts from the sciences and using these concepts or developing a general theory of CP laws inspired by classical mechanics. Malton and Huderman analyzed CP conditions in terms of default or inertial behavior. Both authors capture a violation of CP conditions as a deviation from inertial behavior, where deviating from inertial behavior is itself a process governed by laws of deviation or laws of interaction and composition. Other philosophers are influenced by the life science, such as Nicol, Pemberton, Cartwright, and Strevens, who rely on the concept of mechanism in order to explicate the content of CP conditions more generally. Colin Lanko argues that CP laws are best understood by drawing on methods from statistics, such as multivariate regression analysis. Schertz uses causal Bayesian networks as a formal framework for causal reconstruction of Ceteris Paribus and Ceteris Rectus laws. Finally, Jun argues that focusing on the equilibrium methodology used in thermodynamics as well as in economic reason facilitates new understandings of the explanatory role of CP laws in terms of efficient performance. Conclusion. Where the debates about CP laws leading? What are the important challenges to be met in future research? There are at least 4 main areas of productive future research. The debate on CP laws since the 1980s has not particularly focused on the detailed case study of laws in different scientific disciplines, but this seems just to be what a satisfying theory of CP laws requires. A possible result of a detailed case study might well be that generalizations reveal quite different features in different disciplines. In other words, the explication of CP laws in, for instance, physics, biology, and economics might differ significantly. If so, this result also raises interesting methodological questions for philosophers of science, such as what degree of unification with respect to laws in different scientific disciplines do we require in order to approve of a theory? What is the connection between CP laws and theories of causal explanation? Various theories of causations and mechanisms. When applied to special sciences, many theories of causal explanations, causations, and mechanisms seem to presuppose generalizations. Interesting, these generalizations tend to be classified as non-strict. Consequently, these generalizations are in the domain of the debate of CP laws. These theories of explanation, causations, and mechanisms are important to test cases for the adequacy of theories of CP laws. What metaphysical claims do the various theories of CP laws commit us to? Do exclusive CP laws commit us to assume that the fundamental laws of nature are deterministics, or are they compatible with a probabilistic metaphysics? Furthermore, do CP laws commit us to dispositionalist metaphysics, or are they compatible with a Humean ontology? Is structural realism an adequate metaphysics for CP laws in general, and in particular for the laws of the special sciences? What role do CP laws play in formal philosophy? For example, is it important to answer the following questions? How are the logical principles of non-Metonic reasoning connected to CP laws? How do CP laws relate to Bayesian probabilities and to the rules of Bayesian updating and these probabilities? There are areas of research are, of course, not a complete list of future research topics. Nevertheless, it seems to us that these questions are interesting enough to stimulate productive further research on Ceteris Paribus laws. Okay, so that one was really long and intense. So anyone still sticking through this, God bless. Hope you find this a little bit useful. So I hope you could see the likely connection to the multiple truth hypothesis in terms like the Ceteris Paribus laws. You mean that all things being equal, there's always some exceptions. And what does it mean that there's some exceptions and that different rules have different exceptions? Can you systematize the exceptions? And the multiple truth hypothesis would be an attempt to do that. I mean, that would be, basically the general goal of the multiple truth hypothesis is to systematize, here what's referred to as CB laws. So, that was really long, and I'm going to do one more. Let's do it. So I'm enjoying this. I'm, gaining a lot. I feel my, I feel the progress in my understanding. So the goal of this is to advance the due diligence for the multiple truth hypothesis. I really want to get things right and understand it. I read through these multiple times. I highlighted it, but just letting the words leave my mouth, I see the benefit of it. So anyone listening to it, hope you're also, gaining just the book on tape, or, if you're following my work, appreciate it. So let's do the last one. mechanisms in science. Around the turn of the 21st century, what has come to be called new mechanical philosophy, or for brevity, new mechanism, emerged as a framework for thinking about the philosophical assumptions underlying many areas of science, especially in sciences such as biology, neuroscience, and psychology. In this entry, we introduce and summarize the distinctive features of this framework, and we discuss how it addresses a range of classical issues in the philosophy of science, including explanation, metaphysics, the relation between scientific disciplines, and the process of scientific discovery. For each of these issues, we show how the mechanistic framework has reoriented philosophical works, what is the new mechanism has contributed to the discussion, and what remains to be done. And there's a lot to this, so we'll see how much I get through. Hopefully I'll get through all of this. The rise of new mechanism. 20th century philosophy of science was largely dominated by logical empiricism, more a framework for doing a philosophy of science than any coherent set of doctrines. Logical empiricism addressed a range of issues in philosophy of science through the lens of logical and mathematical structures constitutive of scientific thought and practice. Logical empiricism tended by and large to focus on abstract epistemic features of science with little attention to scientific practice. Physics was the dominant exemplar. The new mechanical philosophy emerged around the turn of the 21st century as a new framework for thinking about the philosophy of science. The philosophers who developed this framework were, by comparison with logical empiricists, practitioners as well of the history of science, and tended by and large to focus on biological rather than physical sciences. Many of the new mechanists developed their framework explicitly as a successor to the logical empiricist treatment of causation, levels, explanations, laws of nature, reduction, and discovery. As with logical empiricism, the new mechanical philosophy is less a systematic and coherent set of doctrines than is an orientation to the subject matter of the philosophy of science. The approach emerged as philosophers and historians of science began to break from the once standard practice of reconstructing scientific inference with the tools of logic and deed to embrace detailed investigation of actual episodes from the history of science. The main tenets of logical empiricism has been under intense criticism for a decade, and a new era of historically informed philosophy of science has taken hold through the work of Kuhn, 1962, Landon, 1977, and Lakatos. To many scholars raised in the post-logical empiricist milieu, it appeared that much of the practice of contemporary science, both in laboratory and print, was driven by the search for mechanisms, that many of the grand achievements in the history of science were discoveries of mechanisms, and that more traditional philosophy of science, for whatever reason, has failed to appreciate this central feature of the scientific worldview. Aspects of the new mechanical philosophy began to emerge in the late 1960s. Fodor, 1968, for example, contrasted mechanistic explanations dealing with parts and their law-like interactions with functional explanations in psychology. Wimsatt, building on the work of Simon and Kaufman, argued repeatedly with the abstract and idealized structure of logical empiricism were ill-suited to understanding how scientists discover and explain complex systems at multiple levels of organization. Cummings, 1975, provided an account of functional analysis characterizing a function as a contribution a component part makes to overall capacity of some system that includes the component. Salmon, 1984, argued that empiricist views of scientific explanation are fundamentally flawed because they neglect causal mechanisms. Cartwright, 1989, argued that logical empiricist conception of a law of nature is in fact a philosophical fiction used to describe the search for capacities of non-logical machines. These strands began to coalesce into overarching perspective in the 1990s. The earliest clear statement of the new mechanisms was Bechtel's and Richardson's 2010 Discovering Complexity. The self-consciously put aside logical empiricist concerns with theory reduction and focus instead on the process by which scientists discover mechanisms. Pseudo-Afterglenum argued that mechanisms are the secret connection Hume sought between cause and effect, a thesis related to the partly inspired by Cartwright's focus on the capacities of nomological machines. Likewise, Taggart's How Scientists Explain Disease centered the search for causes and mechanisms in medicine. McNamara, Darden, and Cravers, thinking about mechanisms, referred MDC, drew these standard strands together and became, for many the lightning rod of the new mechanist perspective. MDC suggested that the philosophy of biology and perhaps the philosophy of science more generally should be reconstructed around the fundamental idea that many scientists organize their work around the search for mechanisms. The concept of a mechanism. The term mechanism emerged in the 17th century and is derived from Greek and Latin terms for machine. Descartes understood the mechanistics as the basic building block of the physical world. In Le Monde, he proposed to explain diverse phenomena in the natural world, such as planetary motion, the tides, the motion of the blood, and the properties of light in terms of the conservation of inertial motion through contact action. Subsequently, the idea of mechanism has been transformed many times to reflect the evolving understanding of the basic causal forces in the world: attraction and repulsion, Du Bois-Reymond, conservation of energy, Helmholtz, gravitational attraction, Newton. These concepts of mechanism has had an almost separate evolution in the history of the life sciences, at times eschewing the metaphysical austerity embraced by Descartes and many earlier mechanists. The new mechanists inherit the word mechanism from these antecedents, but in their effort to capture how the term is used in contemporary science, have distanced themselves both from the idea that a mechanism and machines are, and especially from the austere metaphysical world picture in which all real changes involve only one in a limited set of fundamental activities or forces. Mechanists have generally eschewed the effort to spell out necessary and sufficient conditions for something to be a mechanism. Instead, they offer qualitative descriptions designed to capture the way scientists use the term and deploy the concept in their experimental and inferential practices. Three characterizations are most commonly cited. MDC, mechanisms are entities and activities organized such that they are productive of regular changes from start to setup to finish or termination conditions. Glennon, a mechanism for behavior, is a complex system that produces that behavior by the interaction of a number of parts, where the interaction between parts can be characterized by direct invariant change relating generalization. Bechtel and Abramson, a mechanism is a structure performing a function in virtue of its component parts, component operation, and their organizations. The orchestrated functioning of the mechanism is responsible for one or more phenomenon. Each of the characterizations contain four basic features: phenomenon, parts, causings, and organization. We consider each of these in detail below. A useful canonical visual representation of a mechanism underlying a phenomenon is shown. At the top is the phenomenon of some system engaged in a behavior. This is the behavior of the new mechanism as a whole. Beneath it are the parts and their activities organized together. The dotted, roughly vertical lines reflect the fact that the parts and activities are contained within and are components of the mechanism engaged in the behavior. Thus, represented mechanisms are decompositional in the sense that the behavior of the system as a whole can be broken down into organized interactions among the activities of the parts. In the early literature, these different characterizations were often treated as competitors. Taberley, 2004, argued instead that they reflect different and complementary emphases and intellectual orientation. Many mechanists have adopted this economical stance. For example, Ilari and Williamson offer a consensus concept of mechanism. A mechanism for a phenomenon consists of entities and activities organized in such a way that they are responsible for the phenomenon. Likewise, Glenham refers to minimal mechanism. A mechanism for a phenomenon consists of entities or parts whose activities and interaction are organized in such a way that they produce the phenomenon. These economical characterizations each include the four basic elements and are designed to make the characterization more inclusive. MDC's insistence on the regularity of mechanisms is abandoned, for example, to accommodate mechanisms that work only once or that work irregularly. Bechtel and Abramson's emphasis on the functions is abandoned to accommodate mechanisms that serve no end and to distance mechanisms from the loaded term so often opposed to mechanisms. The economical characterizations intentionally downplay the fact that the term mechanism is used differently in different scientific and philosophical contexts. Indeed, much of the progress in the early years involved learning to recognize the many ways that the term mechanism can be used and the many commitments that can be undertaken in its name. Taking these economical views as a starting point, now consider the four basic components: phenomenon, parts, causings, and organization. Phenomenon. The phenomenon is the behavior of the mechanism as a whole. All mechanisms are mechanisms of some phenomenon. The mechanism of protein synthesis synthesizes proteins. The mechanism of action potential generates action potential. The boundaries of a mechanism, what is in the mechanism and what is not, are fixed by the reference to the phenomenon that the mechanism explains. The component in a mechanism are components in virtue of being relevant to the phenomenon. MDC describes mechanisms as working from start or setup conditions to termination conditions. They insist that it is impoverished to describe the phenomenon as input-output relation because there are often many such inputs and outputs from a mechanism, and because central features of a phenomenon might be neither inputs nor outputs, but rather details about how the phenomenon unfolds over time. Darden, appealing to the example of protein synthesis, often associates the phenomenon with the end state, the protein. Craver and Cummings and Cartwright often speak in the phenomenon roughly as a capacity of or behavior of the mechanism as a whole, producing, underlying, and maintaining. New mechanists speak variously of the mechanism as producing, underlying, or maintaining the phenomenon. The language of production is best applied to mechanisms conceived as a causal sequence terminating in some end product. In such cases, the phenomenon might be an object, a state of affairs, or an activity or event. For many physiological mechanisms, in contrast, it is more appropriate to say that the mechanism underlies the phenomenon. Finally, a mechanism might maintain a phenomenon. In such a case, the phenomenon is a state of affairs, or perhaps a range of state of affairs that is held in place by the mechanism. These ways of talking can in many cases be intertranslated. The product is produced, the production has an underlying mechanism, and the state of affairs is maintained by an underlying mechanism. Yet clearly confusion can arise from the mixing these ways of talking. Regularity. Must the relationship between the mechanism and the phenomenon be regular? This is an area of active discussion. MDC stipulate that mechanisms are regular in that they work always or for the most part in the same ways under the same condition. Some have understood this incorrectly in our view as asserting that there are no mechanisms that work only once, or that mechanisms must work significantly more than once in order to count as a mechanism. Some argue that mechanisms have to be regular in the factual sense, repeated on many occasions. This view would seem to require a somewhat arbitrary cutoff point in degree of regularity between things that truly count as mechanisms and those that do not. Some mechanists argue that there is no difficulty applying the term mechanism to one-off causal consequences, as when an historian speaks of the mechanisms that give rise to World War I. Other mechanists argue that the type token distinction is too crude a dichotomy to capture the many levels of abstraction at which mechanisms, types, and tokens might be characterized. It is possible, however, to read the MDC statement as asserting not a factual kind of regularity, but as a counterfactual kind of near determinism, where all the conditions the same, then the mechanism would likely produce the same phenomenon, where likely accommodates mechanisms with stochastic elements. While the MDC account leaves open the possibility that some mechanisms are stochastic, it clearly rules out mechanisms that usually fail to produce their phenomenon. Skipper and Milstein press this point to argue the MDC account cannot accommodate the idea that natural selection is a mechanism. If, as Gould argued, one could not reproduce the history of life by rewinding the tapes and letting things play forward again, the natural selection would not be an MDC mechanism. It's unclear why MDC would allow for the possibility of stochastic mechanisms and rule out, by definition, the possibility that they might fail more often than they work. Whether any biological mechanisms are truly irregular in this sense, all the causally relevant factors are the same, but the product of the mechanism differs, in a separate question from whether they are mechanistic simpliciter. Crickle, 2014, reviews the many different ways of unpacking the relevant notion of regularity. Her favorite solution, reverse regularity, holds that there must be a generalization to the effect that typically when the phenomenon occurs, the mechanism was acting. Parts. Mechanists have struggled to find a concise way to express the idea of parthood required of the components of a mechanism. The project is to develop an account that is both sufficiently permissive to include the paradigmatic mechanisms from diverse areas of science and yet not vacuous. Formal mereologies are difficult to apply to the material parts of biological mechanisms. Axioms of mereology, such as reflexivity, everything is a part of itself, and unrestricted composition, any two things form a whole, do not apply to standard biological uses of the part concept. Glenham recognizes the difficulty of defining parthood very early on his proposal, the parts of a mechanism must have a kind of robustness and reality apart from their place within the mechanism. It should, in principle, be possible to take this part out of the mechanism and consider its properties in another context. Yet even this is perhaps too strong, given that some parts of a mechanism might become unstable when removed from their mechanistic context. Later, Glendam states that properties of a part must be stable in the absence of interventions, or that parts must be stable enough to be called objects. This notion is perhaps too strong to accommodate the more ephemeral parts of some biochemical mechanisms or the mechanisms of natural selection. Causings. Mechanists have disagreed with one another about how to understand a cause in causal mechanism. New mechanists have in general been at pains both to liberate the relevant causal notions from any overly austere view that restricts causation to only a small class of phenomenon, and to distance themselves from the Humean regularist conception of causation common among logical empiricists. 4 ways of unpacking the cause in causal mechanisms have been discussed: conserved quantity accounts, mechanistic accounts, activity accounts, and counterfactual accounts. It should be noted that some mechanists have evolved in their thinking about causation. Conserved quantity accounts. According to transmission of accounts, causation involves the transmission and propagation of marks or conserved quantities. The most influential form of this holds the two causal processes causally interact when they intersect the space-time and exchange some amount of conserved quantity, such as mass. In this view, causation is local. The process must intersect, and singular. It is fully instantiated in the particular causal process, though the account relies on laws of conservation. Although this view is inspired many in the new mechanics, and although it shares their commitment to looking towards science for an account of causation, it has generally been rejected by new mechanists. The view has been unpopular in part because it has little direct application to the non-fundamental sciences such as biology. The causal claim biologists must make usually don't involve explicit references to conserved quantities, even if they presuppose such notions fundamentally. Furthermore, biological mechanisms often involve causation by omission, prevention, and double prevention. That is when a mechanism works by removing a cause, preventing a cause, or inhibiting an inhibitor. Such forms of causal disconnections are ubiquitous in the special sciences. Mechanistic accounts. Glenham sees causation, at least non-fundamental causation, as a derivative from the concept of mechanism. Causal claims are claims about the existence of a mechanism. The truth maker for a causal claim at one level of organization is a mechanism at a lower level. In short, mechanisms are the hidden connection Hume sought between cause and effect. Likewise, Selman Doe account Glenham's view is singular. Particular mechanisms like link particular causes and particular effects. This view has been charged with circularity. The concepts of mechanisms and illimitability contains a causal element. However, Glenham replies that many accounts of causation share this flaw. Furthermore, he argues that for at least all non-fundamental causes, a mechanism clearly explains how a given cause produces its effect. Whether the analysis succeeds depends on how one deals with the resulting progress. As Glenham notes, the decomposition of causes into mechanisms might continue infinitely, in which case there's no point arguing about which notion is more fundamental, or the decomposition might ground out in some basic lowest level causation notion that is primitive and so not analyzable into other causal mechanisms. The latter option must confront the widely touted absence of causation in the theories of fundamental physics at very small size scales. Classical conceptions of objects and properties no longer seem to apply, making it difficult to see what content is left to the idea that there are mechanisms at work. Activity-based accounts. Still other mechanisms such as Bogan and Machimer embrace the Anscombian non-reductive view that causation should be understood in terms of productive activities. Activities are kinds of causings. Defenders of activity-based accounts eschew the need to define the concept, relying on science to say that activities are what features they might have. This view is a kind of causal minimalism. Whether any activity occurs is not a matter of how frequently it occurs, or whether it would occur always or in the most part in the same conditions. This account has been criticized as vacuous because it fails to say what activities are to account for the relationship of causal explanatory relevance, and to mark an adequate distinction between activities and correlations. Glenham argues that these problems can be addressed by recognizing that activities in a mechanism at one level depend on a lower level mechanism. Counterfactual accounts. Lastly, some mechanists, particularly those interested in providing an account of scientific explanation, have gravitated towards a counterfactual view of causal relevance, in particular to manipulationist view expressed by Woodward. The central commitment of this view is that the models of mechanisms describe variables that make a difference to the value of other variables in the model and to the phenomenon. Difference making in this manipulationist sense is understood as a relationship between variables in which interventions on cause variables can use to change the value of effect variables. Unlike the views discussed above, this way of thinking about causation provides a ready analysis of explanatory relevance that comports well with the methods of testing causal claims. Roughly one variable is causally relevant to a second when there exists an ideal intervention on the first that changes the value of the second via the change induced on the first. The view readily accommodates emissions preventions and double prevention situations that have traditionally proven troublesome for production type accounts of causation. In short, the claim that C causes E requires only that ideal interventions on C can be used to change the value of E, and not that C and E are physically connected to one another. Finally, this view provides some tools for accommodating higher level causal relations and the non-accidental laws of biology. On the other hand, the counterfactual account is non-reductive, like the mechanistic view, and inherits challenges faced by other counterfactual views, such as preemption and overdetermination, which are common in biological mechanisms. Organization. The characteristic organization of mechanisms is itself the subject of considerable discussion. Organization and aggregativity. Wimsatt contrasts mechanistic organization with aggregation, a distinction that mechanisms have used to articulate how the parts of a mechanism are organized together to form a whole. Aggregate properties are properties of wholes that are simpler sums of the properties of their parts. In aggregates, the parts can be rearranged and intersubstituted for one another without changing the property or behavior of the whole. The whole can be taken apart and put back together without disrupting the property or behavior of the whole, and the property of the whole changes only linearly with the addition or removal of parts. These features of aggregates hold because organization is relevant to the property of the whole. Wimsatt thus conceives organization as non-aggregativity. He also describes it as mechanistic form of emergence. Mechanistic emergence is ubiquitous. Truly aggregate properties are rare. Thus, mechanists have tended to recognize a spectrum of organization with aggregates at one end and highly organized mechanisms at the other. Indeed, many mechanisms studied by biologists involve parts and causing all across the spectrum. Varieties of organization. Following Wimsatt, mechanists have detailed several kinds of organization characteristics of mechanisms. A canonical list includes both spatial and temporal organizations. Spatial organizations include location, size, shape, position, orientation. Temporal organizations include the order, rate, and duration of the component activities. More recently, mechanists have emphasized organizational patterns in mechanisms as a whole. Bechtel, for example, discusses how mathematical models and dynamical models in particular are used to reveal complex temporal organizations in interactive mechanisms. Some argue that dynamical models push beyond the limit of the mechanistic framework. Others argue that dynamical models are in fact often merely descriptive, non-explanatory models, or alternatively, that they're used to describe the temporal organizations of mechanisms. Mechanists have also recently borrowed from Milan's work on network motifs, repeated patterns in causal networks to expand the vocabulary for thinking about abstract patterns of organization, understanding how parts compose wholes likely to be a growth area in the future of mechanistic framework. Modularity. Woodward's counterfactual definition of a mechanism, which is indirectly specified via an account of mechanistic models, as well as descendant elaborated by Menzies 2012, requires that models of mechanisms be modular. This means roughly that it should be physically possible to intervene on a putative cause variable in a mechanism without disrupting the functional relationship among the other variables in the mechanism. In terms of structural equation models in particular, this means that one should be able to replace the right hand of an equation in the model with a particular value, set the left-hand variable to a value without needing to change any of the other equations in the model. This is intended to formally capture the sense in which the mechanism is composed of separable interacting parts. Steele appeals to a somewhat weaker form of modularity in its probabilistic analysis of mechanism, one that follows directly from Simon's ideal of nearly decomposable system. On Simon's view, the parts of a mechanism have more and stronger causal relations with the other components of the mechanism that they do with items outside the mechanism. This gives mechanisms and parts of mechanisms a kind of independence or objecthood defined ultimately in terms of the intensity of interaction among components. Grusch, following Haugland, develops an idea of modularity in terms of the bandwidth of interaction, where modules are high bandwidth in their internal interactions and low bandwidth in their external interactions. On this view, modularity is not an all or none proposition, but a matter of degree. Mechanisms are only nearly decomposable. Craver argues that such a generic notion fails to account for the relevance of different causal interactions for different mechanistic decompositions. What counts as part of a mechanism can only be defined relative to some prior decision about what it takes the mechanism to be doing. Jointness. Fagan emphasizes the interdependent relationship between parts of a mechanism. Components in a mechanism, she points out, often form a more complex unit by virtue of their individual properties that unite them, their meshing properties. The complex units then figures into the mechanism's behavior. This interdependent relationship, jointness, is exemplified by the lock and key model of enzyme action. Fagan applies this notion to research on stem cells, but argues that it is a general feature of experimental biology. And levels. Many mechanists emphasize the hierarchical organization of mechanisms and the multi-level structure of theories in the special sciences. Antecedents of the new mechanism focus almost exclusively on the etiological causal relations. However, the new emphasis on mechanisms in biology and the special sciences demand an analysis of mechanistic relations across levels of organization. From a mechanistic perspective, levels are not monolithic divides in the furniture of the universe, nor are they fundamentally a matter of size or the exclusivity of causal interactions within a level. Rather, levels of a mechanism are defined locally within a multi-level mechanism. One item is at a lower level of a mechanism than another when the first item is part of the second, and when the first item is organized spatially, temporally, and actively with the other components such that together they realize the second item. Thus, the mechanism of spatial memory has multiple levels, some of which include organs, such as the hippocampus generating a spatial map, some of which involve the cellular interactions that underlie map generation, and some of which involve the molecular mechanisms that underlie those cellular interactions. A Mark, God bless. Stable and ephemeral mechanisms. Finally, mechanisms have found it necessary to distinguish between stable mechanisms, which rely fundamentally upon more or less fixed arrangements of parts and activities, and ephemeral mechanisms, which involve a process evolving through time without a fixed spatial and temporal arrangement. The timekeeping mechanism of a clock, for example, is a relatively stable assemblage of the components in relatively fixed locations that work the same way, with the same organizational features each time it works. Ephemeral mechanisms, in contrast, involve a much looser kind of organization. Items still interact in space and time, but they do not do so in virtue of robust, stable structures. Many chemical mechanisms in a cell are like that. Ephemeral mechanisms are surely a primary focus of historical sciences such as archaeology, history, and evolutionary biology. What mechanisms are not in what are not mechanisms? The term mechanisms has been used in many different ways to express many different ideas. The new mechanist appropriation of the term is thus likely to cause unhelpful associations, and their liberalizations of the term is likely to raise worries that the notion of a mechanism has thereby been trivialized. Here we first distinguish the new mechanisms from other doctrines with which it shares both name and family resemblance. We then discuss some things to which the new use of the term mechanism does not apply. What mechanisms are not? New mechanists have explicitly eschewed the following association with the term mechanism. Mechanisms are not necessarily deterministic. Mechanisms might be stochastic if, for example, they are composed of stochastic activities, or in a more mundane sense, one consistent with determinism, because it is always possible for one or more factors to interfere with the working of a mechanism. One of the parts might be broken, or an unexpected preventer might interfere with the operation of a mechanism. The truth or falsity of determinism and its relevance to the understanding of the special sciences is an independent issue from the question of whether something is a mechanism. Appeal to mechanisms is not necessarily reductionistic. Mechanisms are often described as multi-level, with activities at different levels being equally essential to how mechanisms work. Mechanistic explanations might look up, down, or around depending on the choice of an explendum and the presuppositions of the explanatory context. Mechanists might be reductionist or anti-reductionist. That said, many mechanists opt for some form of explanatory anti-reductionism, emphasizing the importance of multi-level and upward-looking explanations without rejecting the central ideas that motivate the broadly physicalist world picture. Not all mechanists are machine. Not all mechanisms are machines. Machines are human-made contrivances with each part added and organized by a designer to perform a function. Biology and social mechanisms, in contrast, are products of evolution, broadly construed, and so display ornate forms of organization in comparison with contrivances. One machine might contain multiple mechanisms. Machines are also capable of being both active and passive. Mechanisms, in contrast, have a productive aspect and are always doing something. Mechanisms are not necessarily sequential or linear. Mechanisms can have feedback loops and cycles wherein the output of the mechanism or components in turn influences the input of the mechanisms or components of subsequent iteration. Also, the interaction among components in a mechanism need not be desirable by a linear equation. Mechanisms are not necessarily localizable. Components of a mechanism might be widely distributed and might violate our intuitive tutored sense of the boundaries of objects. The assumption of localization is often an important heuristic in the search for mechanisms. However, this heuristic often must be abandoned as the mechanism's organization reveals itself. Mechanisms are not limited to push-pull dynamics. Descartes' mechanisms had this feature, but as noted above, the new mechanism explicitly liberalizes the notion to account for other kinds of causing. Mechanisms are not just fictions, metaphors. When a scientist says that there is a mechanism that makes proteins in living organisms, he is not just using a machine metaphor, rather is saying that there are in fact parts and activities organized in living organisms such that they produce proteins. What are not mechanisms? One might object that there's nothing left of mechanisms once it sheds these historical associations. One might suspect that it's been trivialized. The idea of mechanisms is central to part of the explanatory ideal of understanding the world by learning its causal structure. The history of science contains many other conceptions of scientific explanation and understanding that are at odds with this commitment. Some have held that the world should be understood in terms of divine motives. Some have held that natural phenomenon should be understood teleologically. Others have been convinced that understanding the natural world is something more than being able to predict its behavior. Commitment to mechanisms as a framework conception is commitment to something distinct from and for money exclusive. These alternative conceptions, if this appears trivial rather than a central achievement in the history of science, it is because the mechanistic perspective now so thoroughly dominates our scientific worldview. Yet there are many ways of organizing phenomenon besides revealing mechanisms. Some scientists are concerned with physical structures and their spatial relations without regard to how they work. An anatomist might be interested in the spatial organization of parts within the body with a minimal interest in how those parts articulate together and do something. Many scientists build predictive models of systems without any pretense that the models in fact reveal the causal structure by which the systems work. Sometimes scientists are concerned with taxonomy, sorting without regard to how the sorted items came about or how they work. Finally, in many areas of science, there is a widely recognized and particularly significant distinction between knowing a cause and an effect and knowing how the cause causes the effect. This is not so much an ontological difference as it is a difference in the grain with which one seeks to understand a system's causal structure. In short, there are many framework concepts in science, and not all of them can be assimilated to mechanisms. But what the critic might push forward does not count as a mechanism. Here are some contrast classes. Entities or objects are not mechanisms. Mechanisms do things. If an object is not doing anything, there is no phenomenon, then it's not a mechanism. Correlations are not mechanisms. Mechanisms explain at least many correlations, and many correlations can be used to characterize causal or mechanistic relations, but correlations themselves are not mechanistic. The same can be said of mere temporal sequences of events. Inferences, reasons, and arguments are not mechanisms, though there are mechanisms or of inference and reasoning. What makes something an inference or A reason is logical relation and not merely a causal relation between premise and conclusion. Symmetries are not mechanisms. Many kinds of symmetry are of a fundamental importance in different areas of physics. Translational symmetries, rotational symmetries, these are features of physical systems that are highly general facts or assumptions, not mechanisms. Fundamental laws and fundamental causal relations are not mechanisms. If a law or causal relation is fundamental, then by definition there's no mechanism for it. Relations of logical and mathematical necessity are not mechanisms. Such truths hold in all possible worlds and so do not depend for their truth on facts about causal structure of the world. This is not an exhaustive list of non-mechanisms or non-mechanistic framework concepts, yet it demonstrates that even the liberalized concept of mechanisms is neither vacuous or trivial. Philosophical work to be done. Much of the early mechanical philosophy is focused on the special sciences such as neuroscience and molecular biology. In the years since, philosophers have extended the mechanistic framework to other scientific disciplines such as cell biology, cognitive science, neuroeconomics, organic chemistry, physics, astrophysics, behavior genetics, and phylogenetics. Philosophers continue to test the limits of this framework with the expectation that alternative organization frameworks might play central roles in other sciences. For example, a debate has emerged in the philosophy of biology over whether or not natural selection is a mechanism. Similar debates have emerged concerning mechanistic explanation in cognitive science. One area that has received particular attention is the effort to understand computational mechanisms. On some account, computational mechanisms form a proper subclass of mechanisms that can be defined explicitly in terms of the kinds of entities, properties, and activities involved in mechanisms in that class. According to this view, computational mechanisms are mechanisms that have the functions to manipulate medium-independent vehicles in accordance with a general rule that applies to all vehicles and depends on the inputs for its application. Digital computers are distinctive in that their vehicles are digits. Proponents of this account hope to demarcate computing mechanisms from non-computing mechanisms by appeal to the distinctive components proprietary to computing mechanisms. This view contrasts with both a semantic view, according to which computation is essentially a matter of manipulating symbols or representations, with a perspectivalist view, according to which whether a mechanism counts as computing is a matter of whether it is so described. Philosophers of the social sciences have also emphasized and debated the importance of mechanistic knowledge. In that context, appeals to mechanisms are intended to remedy the relative uninformativeness of social or macro level explanations of social phenomenon, such as widespread norms, persistent inequalities, network and institutional structures, by insisting that these explanations ultimately be grounded in mechanistic details about individual agents and actors, their desires and motivations, and importantly, their relations to one another. The emphasis on relations among actors distances this mechanistic view from methodological individualism. Mechanicists in the social sciences have also tended to shy away from grand overarching theories and towards more local explanations. Scientific knowledge grows by adding items to a toolbox of mechanisms and showing how items from the toolbox can be combined to provide an explanation for a particular phenomenon. Explanation from formal analysis to material structure. The covering law model of explanation was the centerpiece of the logical empiricist conception of science. According to that model, explanations are arguments showing that events to be explained, the explendum event was to have been expected on the basis of laws of nature and the antecedent and boundary conditions and the explendums. For advocates of the covering law model, the philosophical problems of explanation are thus largely a matter of analyzing the formal structure of explanatory arguments. Mechanists, in contrast, insist explanation is a matter of elucidating the causal structures that produce, underlie, and maintain the phenomenon of interest. For mechanicists, the philosophical problem is largely about characterizing or describing the worldly or ontic structures to which explanatory models, including arguments, must refer if they are to count as genuinely explanatory. Mechanists typically distinguish several ways of situating a phenomenon within the causal structure of the world: etiological and constitutive explanations. Many mechanists recognize two main aspects of mechanistic explanation: etiological and constitutive. Selman describes them as two different ways of situating an explendum phenomenon in the causal nexus. Etiological explanations reveal the causal history of the explendum phenomenon, as when one says virus explains a disease. Constitutive explanations, in contrast, explain a phenomenon by describing the mechanism that underlies it, as one says brain regions, muscles, and joints explain reaching. Philosophical arguments against the covering law model often focus on its inability to deal with causal etiological explanations. The model failed to deliver the right verdict on a variety of problem cases precisely because it attempted to provide an account of explanation without any explicit mention of causation. New mechanists extend these kinds of criticisms to the covering law model of intertheoretic micro-reduction. According to the covering law model of reductive explanation, a theory about part reduces and so explains a theory about wholes when it is possible to derive the second from the first, given a bridge law that to connect the two. Some mechanists argue that covering law model of constitutive explanation has problems analogous to those that beset the covering law model of etiological explanations. Action potentials cannot be explained by mere temporal sequences of events utterly irrelevant to the phenomenon, but one can derive a description of the action potential from a description of such irrelevant phenomenon. Action potentials cannot be explained by a mere pattern of correlation that are not indicative of an underlying causal relation. Irrelevant byproducts of a mechanism might be correlated with the behavior of the mechanism, even perfectly correlated, such that one could form bridge laws between levels, but would not thereby explain the relationship. Merely finding a neural correlate of consciousness, for example, would not and is not taken by anybody to constitute an explanation of consciousness. So mechanists argue that micro-reductive explanations must satisfy causal constraints just as surely as etiological explanations must. The covering law model also fails to distinguish models that are merely redescribe the phenomenon in general terms from explanations that, in addition to predicting aspects of the phenomenon, reveal the mechanisms that produce it. New mechanists also argue that the covering law model fails to distinguish predictively adequate fictional models from explanatory models. Finally, mechanists argue that the inner rhetoric model of reduction fails to capture an important dimension of explanatory quality, depth, and implication of the covering law model is that any true law statement that allows one to derive the explendum law with suitable corrections and assumptions will count as a complete explanation. Yet it seems one can deepen an explanation by opening black boxes and revealing how things work down to whatever level one takes as relatively fundamental for the purposes at hand. Such criticisms suggest that the covering law model of constitutive explanation is too weak to capture the norms of explanation in the special sciences. Other mechanists have argued that the covering law model is too strong. Philosophers of biology have long argued that there are no laws of the sort the logical empiricists described in biology and other special sciences. One might conclude from this that there are no explanations in biology, but such a radical conclusion is difficult to square with the obvious advances in understanding protein synthesis, action potential, cell signaling, and a host of other biological phenomena. In such cases, one finds that scientists appeal to mechanisms to do the explanatory work, even in cases where nothing resembling a law appears to be available. Constitutive relevance. With increased attention to constitutive relevance, mechanisms revealed the need for an account of a constitutive relevance, a principle for sorting relevant from irrelevant factors in a mechanism. A system exhibiting phenomenon is composed of many different entities with various properties engaging in a myriad of activities organized together. One central research program is to say which of these entities, activities, and organizational features contribute to the phenomenon and which do not. In a sense, this is a challenge of defining the boundaries of a mechanism, of saying what it is and is not in the mechanism. These proposals have been considered. The first, the mutual manipulability account, understands the constitutive advances in terms of the experimental manipulators used to test interlevel relations. According to this account, if it can be shown that the putative components are contained within the system, then some ideal interventions on the putative components change the phenomenon, and that some ideal interventions that is sufficient to establish the phenomenon is a component in the mechanism. The notion of an ideal intervention is this account is explicitly indebted and proposed extension of Woodward's theory of causal relevance to the constitutive domain. A concern with the mutual manipulability account, though, is that it is the best an epistemic guide to a constitutive relevance, not an account of what constitutive relevance is. The account offers at best sufficient conditions of relevance Also, the notion of an ideal intervention borrowed from Woodward's account of causal relevance cannot be applied straightforwardly to constitutive explanations. An ideal intervention of a system cannot intervene on both the independent and dependent variables at the same time. However, when one intervenes to make the system behavior, one invariably also intervenes on the components of the system. And when one intervenes on the components of the system's behavioring, one also intervenes on the system's behaviorings because the components are related as part to whole. They're not independent, and so require another way to think about ideal interventions. The second proposal offers a regularity account of constitutive relevance models on Mackey's notion of understanding a cause as an insufficient but non-redundant part of an unnecessary but sufficient condition for the effect in question. On this account, a constitutively relevant component is an insufficient but non-redundant part of an unnecessary but sufficient mechanism for a given phenomenon. Allow that any number of mechanisms might suffice to bring about the system's behavior. Each possible sufficient mechanism is then unnecessary for the behavior. Even each of these mechanisms is made of components, none of which alone is sufficient to produce the behavior of the mechanism as a whole, but each of which is necessary in the context of the mechanism for the system to do the behavior. So this account presupposes the idea of being necessary in context, and one might reasonably worry about sorting accidentally correlated mechanisms that in fact make different systems behaviors. A third approach to a constitutive relevance dispenses with the interlevel framing enforced by a mutual manipulability account and attempts to analyze relevance using causal notions only. According to the accounts of this sort, constitutive relevance is kind of causal betweenness. If a system's behavior is understood as an input-output relationship of some sort, then a mechanistic relevance could be understood as being a necessary link in the causal chain between the input and the output. The putative interlevel experiments in the mutual manipulability account can then be recast at different kinds of unilevel causal experiments. Romero provides a helpful framing of these issues and offers the novel suggestion that putatively high-level interventions are in fact handed interventions relative to their lower-level components. Mechanisms and models. The philosophical literature on mechanisms also overlaps with the philosophical literature on scientific models. Here we distinguish mechanical models from models of mechanisms, and we discuss varieties of non-mechanical models. Characterizing completeness. Glenham proposes a definition of a mechanical model as follows. A mechanical model consists of a description of the mechanism's behavior, the behavioral description, and a description of the mechanism that accounts for the behavior, the mechanical description. Such models can be represented in many different ways. They're evaluated in terms of their ability to predict the features of the phenomenon and in terms of the mapping between items in the models and the entities, activities, and organizational features in the mechanisms. Glenham emphasizes that there's no hard line between complete and incomplete models. Rather, models are continually in the process of articulation and refinement. Whether a model is complete enough is determined by pragmatic considerations. The last point is related to Darden's distinction between mechanism schemas and mechanism sketches. In discovering a mechanism, it is often crucial to identify gaps that have to be fulfilled in one's model. While no model is ever complete, in the absolute sense, some models have lacunae that may be filled before the model is complete enough. Mechanistic schemas are abstract descriptions of a mechanism that can be filled in with details to yield a specific type of token mechanism. A mechanistic sketch is an incomplete representation of the mechanism that specifies some of the relevant entities, activities, and organizational features, but leaves gaps that cannot yet be filled. Black boxes, question marks, and filler terms such as activate, cause, or inhibitor hold the place for some entity, activity, or process yet to be discovered. The distinction between sketches and schemas is a matter of completeness. Schemas are more complete than sketches in the sense that a sketch omits one of the more stages of the mechanisms that have to be understood if one really wants to solve one's discovery problem. Mechanists also emphasize the distinction between how possibly schemas and how actually enough schemas A how possibly schema describes how entities and activities might be organized to produce a phenomenon. A how possibly model is hypothesis about how the mechanism works. Such models might be true enough or false. A true enough how possibly model is, though we may not know it, also a how actually enough model. How actually enough schema describes how entities and activities are in fact organized to produce the phenomenon. The term how actually enough captures the idea that the requisite accuracy of a mechanism model may vary considerably from one pragmatic context to another. A false how possible model is merely a how possibly model, just so stories are merely how possible models. Used in this way, the term how possibly model is similar to the term hypothesis. It is entertained as a possibility, but not necessarily endorsed. Abstractions and idealizations. In contrast to mechanisms, schemas, and sketches, some models of mechanisms work not by describing all of the parts, causal interactions, and organizational features, but rather by abstracting away from such potential obfuscating details. In such cases, idealizing assumptions can be introduced to bring the relevant features of mechanisms most clearly into view. Infinite populations, fictionless planes, perfect geometric shapes are presumed in order to strip the model of detail that does not matter for or would not obstruct the intended purposes of the model. Critics of the new mechanical philosophy have pushed on the importance of abstraction in science, drawing attention to the above discussions of completeness. The goals of completeness and accuracy are taken to conflict with the common practices of being satisfied with models that sacrifice details and truth for clarity and generality. The normative distinction between a schema and a sketch, for example, seems to suggest that science progresses by moving from incomplete to complete models, and the distinction between how possibly and how actually enough likewise seems to privilege accuracy over other goals of modeling, which often require distortion and falsity. Yet mechanisms can surely allow that not all models of mechanisms are mechanical models or mechanistic schemas. Often other sorts of models are useful for isolating central aspects of mechanisms functioning. Dynamic models, for example, can be used to characterize the temporal dynamics of a mechanism. Network models can be used to characterize patterns of a connectivity regardless of what units are connected and regardless of what kinds of connections one is particularly interested in characterizing. Minimal models can be used to capture something fundamental about the dynamics of a broad class of mechanisms that share no entities and activities in common. A model of a mechanism is a model that describes a mechanism. It need not be a mechanical model or a mechanism schema in the above sense to play that role. Some mechanisms reserve the term mechanical models for models that describe the entities, activities, and organizational features of a system. According to Glenham's account, a mechanical model that leaves out some relevant features is ipso facto incomplete and sketchy. One specific instantiation of this debate concerns the explanatory force of functional models in psychology. Piccinini and Craver argue that such models should be understood as mechanistic sketches. Black box models to be evaluated and filled in as details about the underlying mechanism are discovered. Black box models are incomplete in virtue of leaving out details about the underlying mechanism, and those models ultimately depend for the explanatory force on the premise that the functional models do, in fact, correspond to how the mechanism works. One might talk about mechanistic explanations in the way that abstracts from the kind of model used to describe the mechanism. The commitment to mechanistic explanation is not a commitment about the form of a model, but rather a commitment about what such models must represent, namely causal and mechanistic structures. Models are explanatory virtue of the fact that they represent the causal mechanistic structures that produce, underlie, or maintain the phenomenon. They're non-mechanistic if they refer to some non-causal, non-mechanistic kind of relation. Philosophical work to be done. To date, much of the work on mechanistic explanation has been driven by the goal of providing a descriptively and normatively adequate theory of mechanistic explanation. Some claim that there are kinds of explanations that rely very little on precise understanding of the mechanistic details of a system, or that they work fundamentally by removing all such details from one's model. Resolving such debates will require being very clear about precisely what one expects out of a philosophical theory of scientific explanation and what one takes a scientific explanation to be. Researchers are required to understand the diverse representational forms that scientists use to represent mechanisms and to understand how the role of idealization in mechanistic explanation. Further work is also required to limit the boundaries between mechanistic explanation and other putative varieties of explanation, and to say as precipitously as Hempel or the causal mechanical theory what a model must do to count as explanatory and precisely how good explanations are to be distinguished from bad. Metaphysics of mechanisms. In this section, we review some of the ways which the concepts of mechanism has been used in diverse areas of metaphysics. Of all the areas that we have discussed, this is likely the most in need of future development. Here we discuss the relationship between mechanisms and laws, emergence, realization, natural kinds, and functions, token mechanisms, type mechanisms, and laws. In much of the early literature on mechanisms, mechanisms are contrasted explicitly with laws of nature. This contrast clearly grew out of emerging consensus in philosophy that there are few or perhaps no laws of biology. The empirical generalization one finds in biology tends to be hedged by Ceteris Paribus clauses, which, whether they hold or not, depend on the background condition that might not hold on and on conditions internal to the mechanisms that might fail. These generalizations, in short, are mechanistically explicable. What necessity they have derives from a mechanism. Mechanisms thus seem to play the role of laws in the biological sciences. We seek mechanisms to explain, predict, and control phenomenon in nature, even if mechanisms lack many of the characteristic definitive of laws in the logical empiricist framework, such as universality, inviolable necessity, or unrestricted scope. One specific strand of this discussion emerged from the considerations of Weber's argument that biology is heteronymous, that it ultimately borrows explanatory power from the laws of physics and chemistry. Weber uses Hodgkin-Huxley's model of the action potential as an exemplar of the reducing biological phenomenon to physical laws. Craver responds that the explanatory force of Hodgkin-Huxley's model in fact requires a grasp of the distinctly biological properties of ion channels, which properties were black boxed in Hodgkin-Huxley's total current equation. Yet by the contrast between laws and mechanisms has not always been entirely clear. Some, such as Bogan, McLemore, and Glenham, emphasize that causes and mechanisms are at base singular, not generally or universal. Therein, building on the work of Mitchell, objects that mechanisms cannot replace laws of nature in our conceptual understanding of explanation and the metaphysics of science. Scientists rarely investigate token mechanisms, one might think, but are much more interested in types. And once one starts talking about types of mechanisms, one is back on the business of formulating general regularities about how mechanisms work. So it would appear that the concept of mechanism cannot supplant the work that generalization was supposed to do, but requires the idea of regularity, and so something akin to the laws if it is to do the explanatory work. Mechanisms, levels, and emergence. Work on mechanisms has also helped to clarify the idea of levels of organizations and its relations to other forms of organizations and non-mechanical forms of emergence. Many mechanists follow Simon, emphasizing that biological systems are hierarchically organized into near decomposable structures, mechanisms within the mechanisms within mechanisms. Using the parable of Tempest and Hoare, and Simon, 1962, argued that a watchmaker who builds a hierarchy of decomposable watches will make more watches than one who builds holistic watches. This parable led Simon to the conclusion that evolved structures are more likely to be nearly decomposable into hierarchically organized, more or less stable structures and substructures. Some have objected that the story is misleading because evolution does not construct an organism from scratch piece by piece. Steele, building on the work of others, therefore attempts to reconstruct this argument in a way of showing that evolved systems are more likely to be modular systems made of independently manipulatable parts, can quarantine the effects of changes to specific parts, giving them added flexibility to make local changes without causing catastrophic side effects. The near decomposability of mechanisms is directly related to the idea that mechanisms span multiple levels of organization. The behavior of the whole is explained in terms of the activities and interactions among the component parts. These activities and interactions are themselves sustained by underlying activities and interactions among component parts, and so on. Craver defines levels of mechanisms in terms of the relationship between the behavior exhibited by a system and the activity of some component part of the system. Of this account, component parts activity is at a lower level of mechanistic organization than the system's behavior if and only if the component part is a part of the system and the component part activity is a component of the system's behavior. In short, to say that something is at a lower mechanistic level than the mechanism as a whole is to say that it is working part of the mechanism. Though the term level is used in many legitimate ways, levels of mechanism seems to play a central role in structuring the relationships among many different models in contemporary biology. One implication of this view of levels combined with certain familiar assumptions about causal relations is that there can be no causal relations between items at different levels of mechanisms. There can be causal relations between things in different sizes, and there can be causal relations between things described in very different vocabularies, but again conjoined with certain assumptions about temporal symmetry of cause and effect and the independence of cause and effect. There cannot be causal relationship between the behaviors of a mechanism and the activities of the parts that jointly constitute that behavior. Claims about interlevel causation, which are ubiquitous in the scientific literature, are best understood either as targeting the different sense of levels or concerning levels of mechanisms, as expressing hybrid claims combining constitutive claims about relationships between the behavior of the mechanism as a whole and the activities of its part, and causal claims concerning relationships between things not related as part and whole. As noted above, the fact that phenomena at higher levels of mechanisms depend upon the organization of components, parts entails that the properties activities of wholes are not simple sums of the properties activities of the parts. Levels of mechanisms can thus be contrasted with levels of mere aggregation. Because the whole is greater in this sense than the sum of the parts, some have found it appropriate to describe this as a kind of emergence. Mechanistic or organizational emergence, thus understood as ubiquitous and banal, but extremely important for understanding how scientists explain things. Also familiar as epistemic emergence, the ability to predict the properties or behavior of wholes from properties and behaviors of the parts. Epistemic emergence can arise as a result of ignorance, such as failing to recognize the relevant part, or from failing to know how different variables interact in complex networks. It might also result from limitations on human cognitive abilities or in current generation representational tools. The practical necessity of studying mechanisms by decomposing them into component parts raises the epistemic challenge of putting the parts back together again in a way that actually works. The mechanistic emphasis on mechanistic organizational and epistemic emergence contrasts with their desire to distance themselves from spooky emergence. Spooky emergence would involve the appearance of new properties with no sufficient basis in mechanism. It is not clear that the emergent properties are properly said to be properties of the necessary mechanism, and it is not clear in what sense the emergent property is emergent rather than a fundamental feature of the causal structure of the world. In such forms of emergence are altogether distinct from, and so gain no plausibility from, verbal association with organizational mechanism and epistemic emergence. Aquarium TV, God bless, good to see you. Mechanisms and realization. Because the framework concept of a mechanism is so useful for the thinking about levels and explanation in the sciences, some scholars have sought in the notion of a mechanism a way of fleshing out the ontological relations of realization. According to the flat view, realization is a relationship between different properties of one and the same thing. The subset view, which holds that a property 1 realizes property 2 when the causal powers distinctive of property 2 are a subset of the causal powers distinctive of property 2, is an example of the flat view. Property 1 and 2 are both attributed to the same thing. The dimension view describes realization as the relationship holding between the properties of wholes and the properties of the parts in their organization. This view of realization comports with the explanatory aims of the special sciences and fits nicely with the evidential basis of which interlevel claims are grounded. Gillette has since expounded this notion to handle the realization of objects, properties, and processes. Mechanisms and natural kinds. Mechanistic theories of natural kinds developed out of Boyd's homostatic property cluster view. The homostatic property cluster view is a theory of natural kinds designed to work in domains with high individual variability. The homostatic property cluster view is offered as a third way between essentialism and nominalism about kinds in the special sense. According to this view, a natural kind is characterized by a cluster of property that is regularly co-occur and similarity generating mechanisms that explains why the properties in one tend to co-occur. In short, kinds are property clusters explained by mechanisms. The view of a natural kind has been deployed to argue for taxonomic revisions, for example, in the biology of human emotion, the structure of concepts, and the taxonomy of psychiatry. A putatively single kind is split into multiple kinds because it is discovered that the distinct properties in a property cluster are explained by distinct mechanisms. This view of kinds can also be used to make sense of kinds that are historically transient and, in some ways, the product of human attitudes, and so socially constructed. In this straightforward sense, perhaps race is like this. Mechanisms and functions. Emphasis on the importance of mechanisms is historically associated with the rejection of teleology and formal causes. Yet, contemporary biology and many other special sciences, despite the widespread acceptance of the mechanistic framework concept, continue to make use of the concept of function, a teleological notion. How is the notion of function to play in contemporary science related to the concept of mechanism? Graver, following Cummings, argues that functional description is a perspectival means of situating some part within a higher level mechanism. According to this view, teleology is not a feature of the world so much as it is imposed upon it by intentional describer. Garson, following Wimsatt, Wright, and Neander, argues that functions are effects of an item that are part of an etiological explanation through selection, learning, or reinforcement for why the item is present. As such, functions are reduced to causal histories. In the third view, Mele and Piccinini argue that teleological function of an item is contribution to the goals of the organism, which may be objective or subjective goals. Like Garson, Mele, and Piccinini hold that functions are objective, not observer relative. Unlike Garson, however, they're not grounded in the etiology of an item, but in their current contribution to survival of reproduction, the objective goals of organisms, or to what the organism itself desires, the subjective goal of organisms. Philosophical work to be done. What must the world be like for this mechanistic perspective to be accurate? Clearly, there are many ways of answering this question from differing metaphysical starting assumptions, and clearly, many metaphysical starting assumptions rule this world picture out as illegitimate. The clearest path forward, it would seem, is to work out precisely what one must be committed to in holding that the world is composed of a hierarchy of mechanisms, and precisely what of that can be recovered on the basis of different starting assumptions. That said, not all applications of the mechanism framework require fully articulated metaphysics. Work on discovery and explanation might proceed perfectly well without embracing any particular metaphysical world picture. Philosophers with different interests, discovery, explanation, testing, reduction, emergence, and so on, are likely to elaborate on the concept in different ways. There is every reason to doubt that the idea of a mechanism can be given a one-size-fits-all metaphysical analysis that will adequately address the diverse philosophical ends to which the concept is being deployed. Relations between scientific disciplines, from theory reduction to mechanism integration. Theory reduction. According to Nagel, 1961, reduction is a species of covering law explanation. One theory is reduced to another when it's possible to identify the theoretical terms of the first with those of the second, to literally derive the first from the second. On the assumption that scientific disciplines and theories correspond to one another, reduction serves as a model of interdisciplinary integration as well. Mechanist objection to the covering law model of constitutive explanation. Micro-reduction, discussed above. Here the focus is rather on how distinct disciplines of science are integrated. On the Nagel view, reduction is an interlevel relationship. It is also a relationship between theories. Theories about phenomena at a higher level are reduced to derive from theories about phenomena at a lower level. Finally, the relationship is formally specified and has little to do with either the content of the theories or the material structures those theories described from the mechanistic perspective. Each of these features of the Nagel model is problematic. Mechanism integration. First, mechanists criticize the idea that reduction should be understood primarily as a relationship between theories. In integrating their results, scientists are not simply building theories simpliciter, they're building theories about mechanism. Mechanisms can perhaps be described using formal accounts of theories. Perhaps they can be axiomatized in predicate logic or reconstructed set theoretic predicates, but such formal accounts of the structures of scientific theories gloss over the mechanistic structure crucial for understanding how these theories are constructed and evaluated. Mechanists also challenge the idea that disciplines are related by the way of the relationship between their theories. Darden and Moll, 1977, argue that disciplinary fields often integrate their findings through the construction of interfield theories, appealing to a diverse material relationships between items in different fields. Domains, relations such as cause and effect, parts and whole, and structure and function. Darden and Moll did not offer a general account of interfield theories, but Bechtel presently suggested that such theories often take the form of descriptions of mechanisms. The mechanistic approach also has been claimed to have many advantages over reduction for thinking about interlevel forms of interdisciplinary integration. First, it provides a straightforward way to interpret the talk of levels. Second, it offers a significantly more insight into what interlevel integration is, into the evidential constraints by which interlevel bridges are evaluated, and into the forces driving the coevolution of work at different levels, constraints of the parts, the causal interactions, and their spatial, temporal, and hierarchical organizations all help to flesh out interlevel integration. Finally, mechanists repeatedly recognize the need to not only look down to the constitutive mechanisms responsible for a given phenomenon emphasized by classical reduction models, but also to look up and around to the context within which the phenomenon is embedded. Interlevel integration is an effort to see how phenomena at many different levels are related to one another. Mechanists have developed several extended examples of the many forms of mechanisms integration pursued into mechanistic research programs. Darden, for example, suggests that philosophers in the grip of classical reduction fundamentally misunderstood the relationship between Mendelian and molecular genetics, while reductionists see it as an instance of interlevel explanation. She argues it is in fact a case in which different scientists worked on different parts of a mechanism that are etiologically, not constitutively related to one another. Mendelian genetics did not reduce to molecular biology, rather classical genetics and molecular biologists integrated their work by focusing on different working entities in the subsequently operating chromosomal and molecular hereditary mechanisms. Examples have also been drawn from the discovery of mechanisms in protein synthesis and cell biology. Craver uses examples from the neuroscience of memory to explore how multi-level integration does and ought to proceed. In each case, the search for mechanism serves as an abstract scaffold onto and around which the findings of diverse scientists converge. Integrated pluralism. The mechanistic perspective tends to emphasize integrated pluralism in scientific research. The goal is not to explain the less fundamental in terms of the more fundamental in a stepwise relating of monolithic theories at one level to monolithic theories at another. Rather, such scientific achievements are collaborative and piecemeal, adding incremental constraints to the emerging picture of how a mechanism works, both at a level and across levels. The many scientific disciplines that investigate a phenomenon pluralistically coexist and co-inform one another by integratively contributing to the etiological, constitutive, and contextual mechanistic explanations of the phenomenon. Philosophical work to be done. The Nagel model of theory reduction offers a clear vision of the unity of science. According to the model, the unity among scientific disciplines is achieved by reducing theories of higher level disciplines to theories of lower level disciplines. Integration in that vision is understood as progress towards a grand unified body of scientific knowledge. For a mechanist, in contrast, integration is piecemeal, local, and pluralistic. What sort of unity could such an integration sustain? The question plays out in a back and forth between Lagino and Taberry concerning disciplinary relations in the behavioral science. Taberley argues the discipline is as disparate as neurobiology and quantitative genetics could pluralistically coexist and co-inform one another's causal explanations of complex behaviors by way of mechanism integration. Longino counters that Taberley's pluralism is only a moderate sort because the push for integration ultimately is a push for unification. Sullivan also challenges the push for mechanistic integration. She argues that there are significant barriers to the kind of integration mechanisms envision. Different laboratories use different experimental protocols to study what they assume to be the same phenomenon. However, these different protocols often, in fact, target different phenomenon, so the integration achieved by combining results is only illusory. The discussions are symptomatic of a more general philosophical question faced by mechanists. How are mechanism integrations actually achieved as opposed to just asserted? And what is the relationship between mechanism, integration, and unification. The new mechanical philosophy stands to benefit from future efforts to situate mechanistical integration into a more general philosophical views of integration and pluralism. Discovery from aha moments to discovery strategies. Discovery via aha moments. What can philosophers say about the scientific discovery? Many logical empiricists had a simple answering: nothing. According to Popper, for example, philosophers can illuminate the epistemology of testing, but they can say nothing of the substance about how scientists generate the ideas to be tested. Such aha moments of creativity are the province of psychology, not philosophy. Reichenbach distinguishes the context of discovery from context justification, the context distinction. The process of scientific discovery was thus largely off limits to philosophers. Not all philosophers of science agreed. Hansen, for example, articulated a logic of discovery involving abductive inferences from anomalous data to new hypotheses designated to account for them. Others focused on methodologies of discovery that could either allow one to rationally reconstruct why something was discoverable at a given time, or to explain why a new hypothesis is considered promising and worthy of further investigation. Earlier contributions to the new mechanical philosophy followed this path and characterized investigative strategies scientists use to discover mechanisms. Discovery via strategies. Bechtel and Richardson's Discovering Complexity is organized around flowchart representation choice points in the discovery of a mechanism. The process of searching for mechanisms begins with a provisional characterization of the phenomenon, then follows strategies of localizing the mechanism within the system and decomposing the phenomenon into distinct subfunctions. Localization of functions involves determining which of these subfunctions of the system is performed by which part. Bechtel and Richardson further characterized the use of excitatory and inhibitory experiments to obtain these kinds of information. Bechtel and Abramson added a subsequent stage in which scientists recompose what they have learned about the functional parts by putting them back together to produce the phenomenon in question. Darden also emphasizes mechanisms as an important framework in the concept of scientific discovery. In the discovery of protein synthesis, jointly investigated by molecular biologists and biochemists in the 1950s and 60s, scientists didn't simply have an aha moment. Rather, they developed strategies for revealing how a mechanism works. Darden characterizes the process of mechanistic discovery as an extended piecemeal process with hypotheses undergoing iterative refinement. The process occurs via the construction, evaluation, and revision of mechanism schemas in light of observational experimental constraint. Darden's construction strategies are strategies for generating new hypotheses about a mechanism. In addition to decomposition and localization, Darden shows that scientists often borrow a schema type from another area of science, as when selection type mechanisms were borrowed to understand how the immune system works, or assemble a mechanism from known modules of functional activities, modular subassembly, as in common in biochemistry and molecular biology. Sometimes scientists know one part of the mechanism and attempt to work forward or backward through to other parts and activities. In the discovery of the mechanism of protein synthesis, for example, molecular biologists work forward from the structure of DNA to figure out what molecules could interact with it, forward chaining, and biochemists work backward from proteins to figure out what chemical reactions would be necessary to create them, backward chaining. They met in the middle at RNA. Protein synthesis is now understood to involve transcribing DNA into RNA and then translating RNA into proteins. Far from being philosophically inscrutable, Darden points out that scientists use what they knew about the working entities and activities in the mechanisms to infer what could come next or before in the mechanism of protein synthesis. Evaluation strategies for Darden involve constraint-based reasoning to limit the contours of the space of possible mechanisms for a given phenomenon. Other scientists reason about how a mechanism works by building off basic findings concerning the spatial and temporal organization of its parts. Darden and Craver also discuss experimental strategies for learning how a mechanism works. These strategies reveal how different entities and activities in a mechanism interact, and are organized together. For example, one might intervene to remove a putative component to see if and how the mechanism functions in its absence, inhibitory experiments, or they might stimulate that component to see if it can drive the mechanism to modulate its behavior. Or one might activate a mechanism by placing it in the precipitating conditions for the phenomenon and observe how the entity or activity changes as the mechanism works. Craver discusses these under the headings of interlevel experiments. Craver and Darden also discuss more complex kinds of experiments for learning what sort of entity or activity contributes to a process and for learning more complex features of a mechanistic organization. Deteri explores the use of robotic simulations for the purposes of testing mechanisms. They discuss how assumptions are built into robotic models and how experiments can also be designed to reveal how mechanisms work. This work extends to the mechanistic framework into areas of biorobotics and reveals a set of strategies distinct from those explored in Darden's work. Rather than focusing on the process by which some mechanism schemas are constructed, evaluated, and revised, Steele focuses on the question of how one extrapolates from a sample population or a model organism to the structure of a mechanism in the target. After developing a probabilistic account of the mechanism, Steele considers how researchers get around what he calls the extrapolator circle, determining how could we know what the model and the target are similar in causally relevant respects without already knowing the causal relationship in the target. Steele breaks the extrapolator circle by developing a mechanism-based extrapolation strategy, the strategy of comparative process tracing. Once a mechanism for some phenomenon has been elucidated in a model, scientists then compare key strategies, particularly downstream stages in the model with the stages in the target, paying particular attention to the points in the process where differences are most likely to arise. The greater the similarities of the entities, activities, and organizations of the mechanisms and the populations, the stronger is the basis for extrapolation. The greater the differences, and the weaker the basis. Mechanistic evidence in medical discoveries. Discoveries in medicine is another domain where the mechanical philosophy has been applied. More recently, philosophers interested in evidence-based medicine have been probed the relationship between the two types of evidence in the health system. Russo and Williamson argue that both types of evidence are necessary to justify causal inference. The correlational evidence establishes that there is a difference-making relation between some cause and some effect, while the mechanistic evidence establishes how exactly the cause produces the effect. The Russo-Williamson thesis. Philosophers have since refined the Russo-Williamson thesis, pointing out, for instance, the type of evidence could refer to different methodologies for gathering evidence or to different objects of evidence. Difference-making methodologies include observational studies and randomized controlled trials, while mechanistic methodologies include interventionist experiments. Likewise, the object of evidence could be the evidence of an associated difference, or it could be the evidence concerning the mechanism linking the cause and effect. Evidence-based medical hierarchies, which rank different kinds of evidence in terms of the epistemic strength, tend to prioritize evidence from difference-making methodologies, such as randomized control trials and meta-analysis, over mechanistic evidence. In reply, these philosophers argue that the different types of evidence are on a par, each with its own strengths and weaknesses, and advocate for integrating difference-making and mechanistic evidence, a sentiment which aligns with the emphasis of mechanistic integration. Philosophical work to be done. Many mechanists have explored the strategies that scientists use in discovery. Bechdel and Richardson attended to decompositional and localization. Darden and Craver highlighted forward and backward chaining. Russo and Williamson emphasized drawing on both difference-making and mechanistic evidence. These strategies were found in specific experimental services such as neuroscience and molecular biology. So one task for philosophers moving forward is to assess whether or not similar strategies exist in other sciences, especially those that operate outside the traditional laboratory, both in the human sciences and physical sciences. We also expect tremendous development to come from bridging the gap between the qualitative accounts of mechanisms and mechanistic explanation development in the new mechanism and quantitative theories of discovery from the discipline of machine learning and causal modeling. The latter offers tools to mine correlational data for causal dependencies. Such tools might escape qualitative historical approaches and might in fact go beyond the common strategies that scientists traditionally use. Such tools also offer a means to assess discovery strategies by exploring the conditions under which they succeed and fail and the efficiency with which they deliver verdicts on causal hypothesis. In conclusion, the new mechanical philosophy and more generally attention to the framework concept of mechanism has been expanded rapidly over the last 2 decades, bringing with it a new orientation towards a wide range of issues in the philosophy of science. Yet it is clear that many of the major topics are only beginning to develop, leaving a lot of work for scholars to elaborate on the basic commitments of this framework and to consider what it means to do science outside of that framework. The near future is likely to see continued discussion of the implications and the limits of this framework for thinking about the science and scientific practice. Okay, so almost 6 hours, a lot of information. We'll see if next week or the week after, I have like 13 more things that I picked out, and I could pull out more. There's so many of them, and but I'm gonna do 10 of these. Do these readings, and like I feel that I've definitely rounded the curve, like in terms of like a real strong understanding of the philosophy of science. There's still more to talk about, so we will continue, and you hope this is useful to people. Anyone watching this gain from it. It's my honor to provide a service to the general public. Well, just my general education, my due diligence. People have been following my work. Hopefully can see some elements of the multiple truth hypothesis coming together, but still a lot of work. So let's keep at it, and you'll see you with Week in Review on Sundays, and hopefully next week I'll have another, although it might be every other week, and then we're going to move into metaphysics. So God bless. Thanks for tuning in. Reach out, social media, and stay tuned for the last 3 parts of this, and then we're going to move into metaphysics and Week in Review for anything else. Anyone wants to talk about other issues. I try to keep this stream like pure to the topic. So, just reach out on other platforms if you want to talk about other things. So God bless. Take care.